morning, Ranjan.
Hello, you're doing fine.
Hi. Good morning.
Good morning. Good morning. Thank you for coming in time. So sorry for troubling you to come back very much on time.
Yeah. Thank you. Thank you.
And Ranjan, everything is okay. I think I can see your slide also.
Okay.
We'll just wait 1 or 2 minutes because the other sessions, parallel session or the common session may be still going on. So when that is over, Icee host will inform us.
Sure. So I have enough time, so there's no problem in waiting.
Okay.
Yeah, thank you.
How are everything there in Singapore?
Singapore, things are fine. Things are under control.
You did not have much lockdown or things like that? Everything was very much...
Not much. So life here all looks almost normal.
Okay. Please note that you would not see many audience here because most of the participants will be attending from the another link. So you will not see them. They will only listen to you. After the end of the talk, Dr. Sandeep Thara, you just look for the chats which may be there. You will have to look for the chats. So the participants may ask any questions from the under the chat window. Then you will have to take it.
Pick up a few questions from the chat. A few important questions within the stipulation.
Yeah. That's right. That's correct.
And as much as time, Professor, me to ask as many questions.
Yeah.
Good luck.
Thank you. Yeah.
So, Professor Joseph, you give me signal when I can start really.
Yeah, I will do. Definitely. Icee table, can we start?
Yes, sir, we can start now.
Okay, good. Thank you.
So,
I will
good morning.
Dr. Sandeep, I will just welcome you and then you can start right after that.
Okay. Thank you.
So, welcome everybody for the day 2 of the Icee 2020. And this is the 4th session within nanophotonics and plasmonics session. I'm welcoming you all to today's session. And I also noticed that Professor Vishnupal and Professor Kehar Singh are also here to attend the talk. And also notice that today we do have small change in the order of presentation. And first we will have the invited talk by Dr. Ranjan Singh, after which 2 oral presentations will be held because Professor Bijoy Krishnadas is unable to join at 11:30. So he will be joining at 12:30. And rest of the presentations will go as usual. There will be an interchange between one invited talk and the 2 oral presentations. So let me welcome our chair of this session today, Dr. Sandeep Khara from IGCAR, and he also is a professor at Homi Bhabha National Institute, and he did his PhD from NPL New Delhi, and he has also done research, visiting professor work at the University of Valencia, Spain, and the Technical University of Chemnitz in Germany, and also from Institute of Atomic and Molecular Sciences Academy in India and Taiwan. And he is well known for his work on NSOM, chip enhanced Raman spectroscopy, etc. So, with this much contribution in research, we are very happy to be with you. We ask the chair for your So, please, I welcome Dr. Sandeep Khara to chair the session today. Please, Sandeep. Thank you.
Thank you for your nice introduction. And also, we are sorry to Professor Singh. He is waiting for long, and extremely kind for being patient with us. So he is a fabulous carrier, though he is actually, we must just be proud that he has been totally Indian, trained in India. He did his BTech and MS, and I had his one MS and also MS from SkillSat and BTech from Bangalore University. And then he did his PhD from Oklahoma State University and PDF in a Los Alamos National Laboratory, US. And he is now having, he got several award. I mean, that is SMPS, SPMS Awesome Award from both 2018 and 20. Award in the same forum in 2017. He is a guest editor of Advanced Optical Materials, which is a very prestigious journal, as we always target for, and we always fail. Many of us always fail. And his contribution is mainly metamaterials, which is a very, very interesting subject. I will not say interesting. Interesting is a slightly different word, but it is a subject of great interest at present moment, with his keen interest in the terahertz, plasmonics, and biosensing, etc. And I welcome him without keeping him much in wait for its talk towards 6G communications with logical photonics. Thank you very much.
Thank you, Professor Dhara, for such an elaborate introduction. I would like to thank Professor Joby Joseph and Sunil Kumar from IIT Delhi for giving me this opportunity to come and give a talk. This looks like a very prestigious conference with the involvement of, I think, IIT Delhi, IIT Kanpur, and Indian Institute of Science. And I looked at the speaker list, and you really have an illustrious set of speakers and also illustrious set of organizers. So thank you very much for organizing this conference during these difficult times. And today I'm going to share some of our recent activity on terahertz wave as a carrier frequency towards 6G communications. So I know that it could sound a bit early to talk about 6G communication, as we are just witnessing only the advent of 5G communications globally. But nonetheless, 5G is here in 2020, and 6G will be there in 2030, and we need to get ready for that. So as you see here, that roughly every 10 years, we have a new generation of mobile communication. And every generation of mobile communication brings in its own disruptive use cases and has changed human lives and societies forever, the way we live our lives. Now, some parameters to note as every generation changes, and some important parameters to note are carrier frequencies that carries the bits of information and the data transmission rates. So like I said, we are looking at the advent of 5G, where the carrier frequency is less than 100 gigahertz. About, I think the maximum carrier frequency ranges from 40 to 60 gigahertz. And the peak data rate transfer that is targeted is about 1 to 10 gigabits per second. Now, 10 years from today will be here. And this carrier frequency has to go above 100 gigahertz. And above 100 gigahertz is a regime which is basically undeveloped. So right now, even at 5G, we are using conventional millimeter wave concepts, but the convention millimeter wave concepts will not apply when we go above 100 gigahertz and get ready for 6G communications. So beyond 100 gigahertz regime is also known as terahertz regime. So here is the electromagnetic spectrum. You can see that this is 100 gigahertz, and beyond 100 gigahertz, so in between microwaves and infrared, is this huge bandwidth from 100 gigahertz to about 10 terahertz. And it is this untapped bandwidth that will be tapped or that will be utilized in the future generation communications, and we need to get ready. So talking about transistors and power amplifiers above 100 gigahertz, those are extremely lossy and extremely rare. So gallium nitride has made a lot of waves at about 95 gigahertz. It has amazing power conversion efficiencies. So it's a great technology that several people are trying to push. But basically, I think everybody understands that above 100 gigahertz is a regime where electronics starts to become very lossy, and we need to come up with some innovative solutions. And photonics could be a nice route to complement some of the losses that electronics is facing. And I will talk to you about what exactly are we doing in terms of terahertz photonics to complement the electronics at such high frequencies. Now, the advantages are the huge bandwidth, extremely high peak data rates. So I think for 6G, these standards are not yet defined, but for 6G, the target will be to touch 1 terabit per second of peak data transfer rates and extremely low latency. By low latency, what I mean is data downloading or data uploading speeds will go below 1 millisecond. Now, as we all know that we have billions of IoT devices now connected through internet, and those devices are all the time generating data. And if we want real-time processing of data and then some decision making to take place through AI and cloud computing, then a high-speed link becomes extremely important. Um, Such as, an example of an autonomous car that it needs to sense data real time, do computation in real time, and take decisions. So therefore, high-speed links would be extremely important, and it's going to affect all spheres of our life, as highlighted here. Somehow everything is now going to cloud, and we should be able to communicate all of these uh, different use applications should be able to communicate with cloud at extremely high speed. And that's where terahertz carrier frequency or teracom could be of tremendous help. Just to give you an example that here is a terahertz radio link. So you see that this is one tower and this is another tower. Both of these towers um, have optical fiber reaching uh, up to this tower, and then we can use some electronics such as a UTC PD. I mean, it's a form of a diode where you can use difference frequency at about telecom wavelengths and generate terahertz waves, and then you can use Schottky barrier diodes as detector to convert the terahertz optical signal um, back into electrical signal. So these short terahertz links in extremely difficult terrains would be extremely important. Um, and and what I'm also trying to show you here is that these short terahertz links are perfectly complementary with the existing fiber network. Um, in terms of use cases, I think a lot of us here already know, so I don't need to go into details of this. So smart homes to autonomous vehicles to industrial automation, robotics, and aviation, everything will see a huge change as we enhance the information bitrate transfer speeds. Now, those were some very broad application cases. Terahertz wireless links would be particularly important for short range communication. I mean, uh, just in terms of generating terahertz and generating high power terahertz waves is extremely challenging. Therefore, how long range terahertz links could be established depends completely on how high power sources we can innovate. So here is just an example of a chip-to-chip communication over a length scale of up to 10 meters that we are trying to develop in my group. Um, in terms of the major players that are interested in this type of technology, it ranges from Broadcom to Infineon to Google to Amazon, and very specific application wise, just to give you an example here, as most of you know that fiber can support data speeds of 300 terabits, up to 300 terabits per second. And the challenge really is how to massively offload data from optical fiber, tending to up to the speeds that optical fiber can support data rates. So here you see that this is a terahertz plug, and here is a user. If we can establish a terabit per second link, then you could download data at few terabits per second of speed. So I think there's a real technological gap in terms of let's say developing modems that could match the data speed of fiber, and I think Terra's waves could bridge some of the gap in terms of massive offloading of data from fiber itself. Just to give you one example, another example is a super immersive telepresence. So let's say if you want to watch a movie or just have a meeting on an ultra high definition television, then each pixel has to be fed by bits of data. And each pixel determines the sharpness of your images, and higher your data stream is, the better images you'll be able to see in terms of using ultra high definition television. This is an example of a data center. So currently data centers, they are all connected by LAN cables, but if we could establish terabit per second links, then you get rid of those LAN cables. So this is just an example of a TBPS link. Something similar with the autonomous vehicles, they need to communicate real time with all the other objects in environment. And even these short links, if we could make it high speed links, then they could be of great utility. Now, so what new science are we trying to apply to solve some of these problems? So we take inspiration from an idea of a topological insulator. So what are topological insulators? So basically, if you think of this system as a 2D material system, here you see that this material conducts electricity only at the edges, only at the edges. And in the center, all of this portion is an insulator. So, so this conduction electrons, they do not have any state to backscatter, and they do not scatter into the bulk. So which means that if this electron sees a defect somewhere in its path, it has the capability to go around it. And this propagation at the edge is resistance free. So there is basically no backscattering. So topological insulator is this excellent idea of a material that is basically an insulator in the bulk and conducts only through the surface states. And conduction is robust against all types of defects. So Duncan Haldane, who proposed the topological phases, got the Nobel Prize in 2016. And here are some other major contributors in terms of experiments itself. Um, just to go a little bit deeper into what is the idea of topological insulator, you can see if you consider a 2D lattice here, this dispersion or the band diagram shows the behavior of an insulator, where you see that the two bands are separated by a large distance. And then when you cool this 2D lattice system down to temperatures and apply extremely large magnetic field, you see an opening up of this very nice quantum state. So what happens is that the electrons start to precess, and there is no transport in this part of the material. Transport occurs only at the edges. And this effect is known as quantum Hall effect, for which the Nobel Prize was awarded in 1980s itself. Um, so, so all the physics of topological insulator is there in this particular state right here. Now you can see that the electrons have a particular slope that represents a group velocity, which tells you that something is moving, pointing towards the transport, the edge transport of the electrons itself. And these electrons do not have states to backscatter. They do not have the permission to go back. And even if there is any perturbation in this system, as long as the perturbation is big enough to touch both of these bands, almost nothing happens. I mean, the conduction is resistance-less, even if there are defects in the system. Now, so this is quantum Hall effect. What is different in modern topological insulator uh, is the question. So all the physics that is here is also there in modern topological insulators, but there's no magnetic field. You don't need any high magnetic field to be applied. This quantum state comes from band inversion due to strong spin orbit coupling in the material itself. Um, so therefore, this becomes a very, very important system with all these unique features of no backscattering, no scattering into the bulk, and no. So basically, quantum Hall effect needs very high external magnetic field, but modern topological insulators do not need external magnetic field and could excite the topological quantum state just due to the strong spin orbit coupling. Now, all of these ideas that I spoke about exist in fermionic systems. How do we get to create something like this in photonic systems? So people came up with some very smart strategies. Um, and of course, I mean, our group was not the first group. There are other people around the world from MIT, the group of Marin Soljacic and Duncan Haldane himself came up with a very initial proposal of how to see these topological like quantum states in photonic systems. And some of the strategies that became clear over time is you somehow first create a honeycomb lattice and then break the inversion symmetry of the lattice. and that could give you a quantum-like dispersion state. So what I'm describing here is a Valley Hall effect, which gives valley-locked robust propagation and also opposite Berry curvature at the two valleys, which are basically the K and K dash band. So this is the hexagonal lattice. Now, what you see here is a silicon substrate about 200 micron thick, and triangles are the holes punched into the silicon substrate, and the hexagonal lattice is here. This is the hexagonal lattice. Now, the two side triangles is the symmetric breaking process, which we call as the breaking up of the inversion symmetry of the system. Now, if the two triangles are identical, then in a C6 symmetry lattice, you can create a Dirac-like dispersion. What you see here, the omega k diagram here is the photonic band structure, and here you create at k point and the k dash point, you create a Dirac-like behavior here. And now when you break the inversion symmetry by making one triangle small and the other triangle relatively larger, you open a band gap. Okay, so this opening up of band gap literally depends on the difference in the geometry between the two triangles. And now we need to create a quantum state within this band gap. And when you bring two opposite types of the geometry, you can literally create a domain wall right here. And once you create a domain wall, you get a nice quantum-like state in the dispersion of this photonic crystal itself. Now you can see that in type A, the big triangle is erect, and in type B, the big triangle is inverted. And once you bring these two types together, you create this nice linear dispersion. So this linear dispersion is locked to the K valley, and this negative slope dispersion is locked to the K dash valley. Now, the group velocity is positive for this positive slope, and it's negative for the negative slope. And what you see here is basically the magnetic field of photons propagating in the forward direction. So this slope would show the photons propagating in the forward direction, and this slope shows photon propagating in the opposite direction. Now here are our experimental results. So what you do is the domain wall that I showed, you can just twist it with several sharp bends. And so here is, you couple the wave in, the terahertz wave in here, and it can go through these nice, extremely sharp bends, and there are 10 bends here. So you in-couple the wave here, and you out-couple the wave here. And this is the experimental setup. So the zoomed portion of this coupler is what I show here. And this is this particular edge. Now these bends, they are either 120 degrees or 60 degree in bend. And these sharp bends actually are analogous to defects in electronic systems. And if you look at the data, so let's say you have a straight domain and a domain with these 10 bands, you can see that the transmission is identical for straight band and for the 10 band system here. Now, this is the gap that was created by symmetry breaking. And you can see that the bandwidth is about 25 gigahertz. So this is this edge is 320 gigahertz. And of course, when you use this band in communication, the communication data bit rate is limited by this particular bandwidth itself. And without any topological interface, you see that the propagation in this particular band is extremely low and noisy. Now, we did some encoding of this carrier waves and could achieve about 11 gigabits per second of communication rate. And this is only for on-off keying. So we already achieved about 75 gigabits per second by using complex modulation scheme. Now for this on-off keying, here is the eye diagram, which shows you the nice 0-1 bits. And this is just an example of ultra high definition TV in the background. And here is the setup basically where our silicon device is right here, the photonic crystal device. And this is the zoomed version of the device where you can see the nice bends in the device itself. Here I am just showing you a comparison with conventional photonic crystal system, where you see that the signal is lost after 1, 2, and 3 band. Whereas in a topological photonic crystal, the signal or the photon transport is so robust in the forward direction that it could survive up to 10 bands. This is just a loss comparison of the two devices. And sort of shows the promise of topological ideas in photonics. Now, why these bends are important is you can reduce the size of the chip itself if the chip can afford to have bends to route photons. What these bends also allow is multiplexing of signals. You can design different types of splitters with several bends on the same chip. By using this idea. This is our sort of our dream chip where we are trying to develop other topological counterparts such as a Y splitter, an add drop filter, a terahertz modulator, a delay line to just slow the wave, and along with a terahertz source. So the idea really is to build a topological silicon-based transceiver um, along with an interconnect. So what I showed you is just an example of a waveguide or an interconnect that could be used to connect the transmitter and receiver on a transceiver itself, or could also be used on connecting two core processors, potentially in our cell phones. I would like to conclude my talk by showing you the opportunities that exist in 5G and beyond 5G technologies. So Qualcomm has come up with this number of $13.2 trillion economy. And I think a lot of big players, big companies in the world are trying to have some share in this market. I would like to acknowledge my collaborators from Osaka University, Professor Fujita and Professor Nagatsuma. Iha was the lead author on this Nature Photonics paper that we published, and the other guys who contributed very heavily. I would also like to acknowledge the funding agencies that supported this work. Here is my group at NTU. This is, I think, looks like a happy set of people. We are also looking for good PhD students to drive this 6G project. So people in the audience who are interested in photonics, so we are looking for engineers to physicists, people who can work on concepts of topology and also RF chip designers. Thank you very much for your attention.
Thank you, Professor Singh. Am I audible?
Yes, you are.
Yeah. So thank you for a very excellent talk. There are two aspects of it. It's professionally very time. It is very maintained. He maintained the very nice timing while keeping the all intricacy of the subject, including the such a technologically sophisticated area. He has not left a simple bit of the physics, I would say, underlying physics in between it, including its technology. And I'm really impressed that how symmetry breaking in materials which are very fundamental aspect of physics has been technologically applied with the right kind of material and being used for the best technology. And there I must put on one simple of my word before any question comes in, that it is really marvelous to see how science, the basic science really can drive the technology. It's not the technology which drives the basic science. Still, it is much ahead of the technology. Thank you very much. So I'll welcome any questions, but I'm not finding any questions. Is there any other questions from the other members or from the participants?
Hello, Ranjan.
Sure.
I have one question. Very excellent talk. Very happy to hear you.
Thank you.
Just one question, that your fabrication method you will be following for the chip fabrication, it will be EBM, right?
So the length scales that I'm talking about here is about few tenths of microns. So simple photolithography is enough for this chip. Yeah.
And so what about tolerances and large area problems? You don't expect much because
so large area is not a problem, as the feature sizes itself is like tenths of microns, and it doesn't, I mean, terahertz wave at 1 terahertz, the wavelength is about 300 micron. So it's not very sensitive to the defects in the material itself. And the material here is silicon. As long as you have high resistivity silicon, it's very, very friendly to the propagation of terahertz waves.
Thank you.
So I don't find any questions in the chat session, and hope that your people will send it in email, because it is a fairly difficult subject from the technological point of view. Not in the technology, from the application of the basics which you have applied. I'm very much interested and really very much impressed to see that how such a simple, not simple, I will say material wise very simple, though physics wise very intricate subject is grasped by you and have been used for a very, very advanced technology. And I'll just definitely, I work a little bit on this field, but a little bit away of it. But I'll just try to impress all my other colleagues who is working in this field or aspiring for this field. Thank you very much for joining us and giving us such a eloquent talk.
Thank you very much. Thank you all. Bye-bye.
So we have next Praveen Kumar, I think is already here. Yeah, Praveen Kumar is there. Praveen Kumar, you can share your screen. You can start.
Yes, sir.
Yeah.
Sir,
Sandeep, yeah, you
is
can.
my screen visible?
Yeah.
Yes, it is visible.
Yeah, it is visible, and I think Professor Dr. Praveen Kumar, he is from IIT Patna, and his talk will be on generation of singular beams using electrically addressed liquid crystal spatial light modulators. So I welcome Praveen Kumar without losing much of time, because your time is very less. You can start your talk.
Yes, sir. Hello, everyone. I am Praveen Kumar, and the title of my presentation is Generation of Singular Beams Using Electrically Addressed Liquid Crystal Special Light Modulator. So the outline of my talk is I'm going to discuss about the optical singularity and the singular beams, and then I will discuss about a method to generate these types of beams using a special light modulator. So I will start with optical singularity. So in optical singularity is basically referred to a point in optical field where some parameters become undefined. And for example, these parameters may be phase, polarization, or others. And these properties we study under the topic singular optics. Okay, and this phenomena of singularities occurs in many other natural phenomena as well. The most commonly used singularities are phase singularity and polarization singularity. So, and these singularities occurs in optical field which has spatial inhomogeneity. This means that in a transverse plane, the means phase and polarization of optical fields are different at different spatial points. And the Poisson singularity is basically because of the vector nature of light, because it has two components in orthogonal components. So Poisson singularity is basically is because of the vector nature. Now phase singularity. So this type of singularity occurs when the light beam has a helical wavefront. It means that light, as we can see in this picture, that when the light has a spiral wavefront, and at the center along the beam axis, we can see that there is a singularity point, and because of this singularity point, the intensity becomes zero along its axis. Now coming to polarization singularity. Uh, so polarization singularity occurs when the distribution across the Poisson distribution across the optical field is non-uniform, and actually this polarization is mostly defined, is characterized by the polarization ellipse, and we have two parameters. One is the uh, polarization azimuth, and other is the ellipticity angle. Using these two angles, we can define the polarization ellipse. And the polarization singularity mostly occurs when these parameters becomes undefined. So in the picture shown in the bottom, we can see a polarization distribution, a picture of a polarization distribution. So it shows that most of the polarization states are linear, and at the center, uh, and at the center here, we can see that we are not able to define the polarization azimuth, and that's why we call it a polarization singularity. And when these types of beam, when we pass these types of beam through a polarizer, we can see different types of intensity patterns, and this shows the non-uniformness in the polarization distribution. So these we this there is a general name for these types of beam, which is singular beams. We are saying as singulars because these beams have optical singularities. Now there are two most commonly used singular beams. One is the vortex beams, and other is the vector vortex beams. The vortex beams is usually have a phase singularity, and these can be homogeneously polarized as well as inhomogeneously polarized, whereas these vector vortex beams, they have phase singularity and as well as the polarization singularity. Now the vortex beams, can be mostly described using LG modes, Lagrange modes, and they are the paraxial solutions of equation. So this is the electric field amplitude. Here we can, the last term, here it is a helical phase term. It shows that this LG beams also has a helical phase term, and that is the reason they also have a phase singularity. And the order of phase singularity is determined by the topological charge. This L is the topological charge here. So this is the picture presentation. So at different orders of charge, we can have different orders of helicity of the beam. Okay. And with the increased helicity, the dark intensity at the center also increases. Now, why these beams are important? It is because these types of beams carry well-defined orbital angular momentum. Okay, which I will discuss in further slides. Now, vector vortex beams. So in these beams are the superposition of the scalar vortex beams, and it can also be characterized by the superposition of LG modes. And this is a mathematical representation. Here we can see it is basically representing a Jones matrix of a vector vortex beams. So we can see that there are two LG modes in the orthogonal polarization basis. So and this shows the vector nature of these beams, and we can have different orders of topological charge, and which results in different polarization patterns. So these are some commonly used patterns. This is type 1, type 2, type 3, and type 4. So this shows the polarization distribution across the optical fields. Why these are important? As I mentioned, that these beams carry well-defined orbital angular momentum, okay, which depends on the topological charge, and this makes the singular beams very important. Okay, because as when we compare with the polarization states, polarization have only two orthogonal states. For example, left circularly polarized and right circularly polarized. So these two are the only orthogonal states. But OM can, in principle, can have many states, and this makes it suitable for very for high encoding, which increases the encoding capacity of any communication system if you will use that. It has also found applications in cryptography, and in other applications are in quantum optics. And since they have orbital angular momentum, they are also used for optical trapping of particles, and other applications are in optical imaging and metrology. So for these applications we need to develop efficient methods for realizing these beams. So which makes me to come to this topic, which is generation of vortex beams, how to generate these types of beams. Okay, so common method used is the special light modulators. Okay, so these are the electro-optic devices. So it has the ability to shape the wavefront of a light. Okay, so for example, I have a coming the incoming wavefront of laser is a plane. We can use the special light modulator to change its wavefront. Okay, and why and how we can do it? We can do it by selection of different computer generated holograms. For example, I need to, if I want to generate a vortex beams, the hologram should be of the phase distribution should be like this. It has a azimuthal phase dependence. So this we can use different types of holograms to generate different types of beams and different orders of vortex beams. Okay, so this has made this special light modulators a very popular device. And this picture shows some of the vector beams which I have generated. For example, these are the different phase profiles which we encode in the SLM, and corresponding we can these are the corresponding intensity. We can see the different orders of vortex beams. As the helicity increases, the vortex the dark intensity region is also increasing, which shows the higher values of orbital angular momentum in them. How to generate vector vortex beams? Which I discussed earlier, the generation of vortex beams, which is simpler, but the generation of vortex beams required more optics, because it in this case means it has a sense to superimpose two vortex beams here in the orthogonal Polarization basis. This makes the interferometric setup complex. Now, people have tried different methods to generate vector vortex beams, and different optical configurations have been reported. And one of the method which I am going to discuss here is the technique of dual phase modulation. And in this case, we have used a single SLM. Okay, and this is a non-interferometric technique, and I will discuss this. So this is the optical setup for generation of vector vortex beams. So this, since we have to modulate both the components of horizon basis, we need two modulations one by one. For example, I have input laser beam here. Okay, so we use a single SLM for modulation of both the bases one by one. In the first reflection, it modulates X component, and then again using the half-wave plate, we change the basis and we modulated the other component, and then we collected this in the output channel. So what makes this setup useful is here we are not using superposition of vortex beams. Instead, we are generating these beams by modulating different components at different times one by one. Okay, so and this is why this setup is more stable and more compact as compared to the interferometric setups. Okay, and of course, if there is no superposition required, we face very less problems in alignment. So it also has a less advantage of less alignment issues. Flexibility is because of the special light modulator. It is because by simply changing the different holograms, we can produce different types of vector vortex beams. Okay, so this picture shows one of the hologram which was encoded. So it can see we have two different phase profiles, one for X component and other for the Y component. So this hologram I have used for generation of a special type of vector vortex beams, which is azimuthally polarized. So this is the results. So we can see that this is a polarization distribution of a azimuthally polarized light, which we want to generate, and these are the results. We can see that this is the total intensity, and these are the intensity which we have captured, means which by changing the polarization orientation angles. So since it has a non-uniform polarization distribution, with change of the polarization transmission angle, you can see the intensity is changing. Okay, so this is the simulation intensity patterns. So we can verify the polarization singularity and its order also by this azimuth distribution. It shows that here it is the linearly polarized, so it has a azimuthal angle of 90 degrees, and it is here it is 0 degrees, so it is rotating. The azimuth angle of the polarization ellipse is rotating with around the singularity, so which can be verified using this distribution. Okay, so this shows that the azimuth is circulating from minus 90 to 90. So here at the center there is a polarization singularity point, and this shows the ellipticity. Since it is a vector field, there is no ellipse, all are linearly polarized, so the ellipticity distribution is uniform. Now methods can be also used to generate vector vortex beams which has a radial indices. Radial indices means there is a step jump of phase here, means it has a circular ring, and because of this step jump there is a circular rings also around the points. So we can generate different types of beams. For example, this shows a spiral polarized vector vortex beams, and this P is the radial indices and this L is the azimuthal indices, and this shows the higher orders, means for L equal to 1 and for higher order of azimuthal indices we can have different types of beams. So what in conclusion, what I discussed is we have shown that we can use special light modulators for generation of singular beams for different orders, and in particular the method of dual phase modulation. Okay, this provides a very convenient solution to realize vector vortex beams, and the method non-interferometric, and it uses a single SLM. So these two advantages. That's all. Thank you very much. Hello, sir.
Yes, thank you very much.
I'll be happy to.
Yes, yeah. Thank you very much, Dr. Kumar, for your excellent talk and keeping in time in program. Actually, there is not much questions. That is very not a very encouraging. So you have finished it within your time, given time of 15 minutes. If somebody asks questions, that is fine. Still, there is time for, I will say, 1 minute for questions if somebody asks questions. Because I'm not very familiar with the field, so I have no specific. So here also you are, I have a small question. Here also you are using the same topological property?
Yes, yes, sir. We are using this topological charge basically. Basically, it denotes the amount of orbital angular momentum which is contained in the singular beams, and we are quantifying the angular momentum by this topological charge.
Okay, that's what I heard. So it's very interesting. So thank you very much for joining us and giving your excellent research results. So now I'll look for the next speaker, Dr. Pandey. I hope that he is present.
Yeah.
So I'll welcome Dr. Pandey. He is from CSIR Central Electronics Engineering Research Institute, Pilani, where also I am little bit touched because I am a old alumnus of course BITS Pilani, and for my PhD and Academy of and also he is attached with another Innovative Research Academy of Scientific and Innovative Research, Ghaziabad. So he will be speaking on optimizing the quality factor of the metal-assisted guided mode resonance-based 2D structure through fill factor modulation. welcome Dr. Pandey.
Hello, thanks for having me.
Yeah, please. Yes, can you share your transparency? Yes.
Visible?
Still not. Now it is visible. Please go.
So good morning to one and all. So I'm Vipul Pandey from CSIR CD, and today I'll be talking about optimizing the quality factor of the metal-assisted guided mode resonance-based structures. So the talk is divided into 4 major sections. First of all, I'll briefly go through what is metal-assisted guided mode resonance. Then I'll go through the need for optimizing the quality factor. Then I'll talk about the design and methodology used in this research, and I'll conclude with the results and discussions. So moving on. So first of all, let us talk about metal-assisted guided mode resonance. So I believe most of us are familiar with the traditional guided mode resonance sensors, which are very well studied in the literature. So the metal-assisted guided mode resonance sensors put an additional component in the guided mode resonance sensors, in the sense that we now introduce a metal underlayer. As you can see here at the moment. So this additional metal layer underneath the guided mode resonance structure practically inverts the spectral response obtained from the traditional GMR sensor. So what happens is, as we incident the light, most of the light which is not at the resonant wavelength gets reflected back, and the light which get coupled on this slab waveguide region is eventually absorbed through the metal layer. So we get an inverted spectral response, as can be seen here. So moving on, why do we need to optimize the quality factor of this resonance? So kindly note that the resonance spectrum for this metal-assisted sensor is also similar to the GMR sensor, in the sense that it is also a Lorentzian response. And the need for quality factor arises when we are actually finding the detection limit of the sensing structure. So both of these are reflective index sensing structures. I will not go into this due to the lack of time. But as you can see, that the final detection limit of these type of refractive index sensors is dependent on the detector resolution divided by the bulk sensitivity, and the detector resolution is numeric maximum of the Lorentzian response. So in a sense, a quality factor can directly affect the detection limit of the sensing structure. So that is why there is a need to improve the quality factor. And in this study, we are looking at modulating the fill factor of the structure to see the effect on quality factor. So moving on. So these are the considered structures. So I've considered 2-dimensional metal-assisted guided mode resonance structures. And I have considered 2 periodicities, which is square and hexagonal. And you can also see right next to it. And the study is conducted for visible range of operation. So using these design parameters, I generate a spectral response, which is close to in the visible region. And I have used COMSOL multiphysics to simulate the results. And I'll be quickly moving to the results and discussion. So first of all, here are the computational domains, the cross-section view of the design geometry for the hexagonal structure and the square structure. Underneath it, we can see the TE and TM spectral responses. And B part is for the square lattice, and the C is the T and TM resonance response for the hexagonal lattice. And as you can see, the bottom region here is the metal layer, and the response is different from the typical CMR response because the metal region reflects all of the incoming light. So there is no electromagnetic field over here. So moving on, I calculated the quality factor for a variety of cases, which I have also represented through image. So as you can see, quick observations we made. So first of all, we can see that the quality factor for the design structures of the square are high as compared to the hexagonal lattice. Also, it is worth noting that as the fill factor increases, the quality factor is seen to be decreased. And this change is more apparent for the this hexagonal structures as compared to the square one. And in general, we can see that the highest quality factor is achieved, that is for the case of 0.4. And and as mentioned previously, the hexagonal structures are for the considered design parameters shown to offer inferior quality factors as compared to the square periodicity. And so other than that, you can the first graph is for the TM resonance mode, and the second graph is for the TU resonance mode. And as the variation of the overall quality factor with the change in fill factor is not that prominent for the TL. For the TU resonant mode, the quality factor changes significantly with the fill factor. So, and here are the references that we have used in the slides. So that's it, and I'll be happy to answer any questions. Thank you.
That's great. You have finished within well before the time, and in fact, you have used exactly. I'll tell you the time: 6 minutes.
No, so I tried to keep it before the time for the next presentation.
Yeah, that's really. I'm grateful to you because we are not. So any questions? Finding in any chat. I hope that.
Yes, sir.
Yeah.
Can I ask a voice question?
Yes, sir.
So you said that these GMR type of sensors, GMR, you are going to use it for sensors, right?
Yes, sir.
What type of sensors exactly these will be used for?
Oh, so
because you have a silicon nitride top layer, right?
Yes, sir. Yes,
so how are you going to use these as sensors?
So these are intended for biochemical sensing applications.
Right. So the biochemical sensing, so some reaction has to take place on the surface of the silicon nitride.
Yeah, for functionalization.
Right. So how are you going to functionalize nitride? Nitride is a problem in many.
Yes, sir. We have actually, sir. This is primarily intended for. This is an exploratory research, but the functionalization part we are still to go through.
I mean, I might add that you might want to plasma oxidize or something like that, a nitride surface, to create a very thin layer of oxide or something, or even do a hydrogen sort of thing on it to create NH groups and do the functionalization. I was hoping that you were going to talk a little bit about that when we were discussing this. Anyway,
this is,
no, so I understand what you're. Yeah, I understand. Thank you.
Thank you for your feedback, sir.
So great. Is there any other questions? If not, then I'll switch over so that we can really maintain time as a and get a good name. Then I'll switch over to the next talk. Professor Somo Mukherjee from IIT Mumbai. So can you good morning, Professor. Please. Yeah, so yeah, it is shared now. I hope that all other people are present and audible to me. So I'll be introducing Professor Mukherjee. He is really he has a coveted career. So Professor Mukherjee did his BTech in Instrumentation Engineering from IIT Kharagpur, my own alma mater, and then MS in Mechanical Engineering, Colorado University, and subsequently he did his PhD there from same US, but from the biomedical engineering, quite a widespread career in University of North Carolina, Chapel Hill, and then after his PhD, he joined IIT Mumbai in 1997, fairly same time when I joined my office at IGCAR, and now he is a chair professor in the Department of Bioscience and Bioengineering. He was the head of Center of Research in Nanotechnology and Science, which is a very prestigious set of or a research center in IIT Bombay. And he is also the Dean Students Affairs from 15 to 19, just got out of his responsibility. His research interests are sensors and instrumentations and wide-scale deployment in the resources content in the locals, medical and environmental application. That's one of the most required thing probably to modernize India and to put us in the world map. I believe this is the correct way of doing the research. And he is guiding more than 30 doctoral students. I mean, he has finished few and continuing more, and 60 master students. So as I told you, is a very coveted research career. And I wish that he is quite young and he will be contributing further for Indian research. So here his talk title is very simple. Start with the word simple optical fiber sensor with high sensitivity. Welcome, Professor Mukherjee, and you can start delivering. You are not audible. You have to unmute.
Sorry, Professor Dhara, really thank you. I mean, it was indeed a wonderful introduction on putting my work in perspective, and also putting the fact that I am an extremely multidisciplinary person, having done my various parts of the various degrees in different departments and disciplines, and that is something which I thrive on and I really enjoy. Thanks to the organizers, Professor Khare and Anuj and many other people who have given me the opportunity not only to talk in this symposium but another one which I did yesterday as well. It is a great pleasure and a great honor. And Professor Dhara, the introduction you gave was absolutely brilliant. Thank you for that. Let me get into this the simple optic. I don't really deal with very high tech processes, or sometimes I don't even go into very fundamental sciences. I actually employ other people's science and technology into making sensors which hopefully will be useful for the society. So let me say what I mean when I why is this not going down? Okay, of course, my research funded by Government of India, Tata Trust, IIT Bombay, and all. I mean, really thanks to them that I've been able to do whatever. And the beauty of it in IIT is that I do whatever I want to do in terms of research, and it does get appreciated. So let's get back to the word simple. Simple. So no high cost infrastructure. That means drag racings are out, LPGs are out, on-chip waveguides in terms of processes are out, and to the extent even a lot of different types of photonic crystals are also out. Because all of these need clean rooms and reasonably high-tech infrastructure. It's not that I don't work on those areas. I've worked on some of these, but I'm not going to talk about that at all in this talk. High sensitivity. So let us see what high sensitivity means. High sensitivity is actually sensitivity in tune with requirements. So actually, there is no point in detecting in picomolar levels when the relevant range is in nanomolars. Let me give you an example from a completely different side. When the doctors measure blood pressure, you say 120 by 80 or something like that. Okay, they really don't care whether it is 118 by 78 or something. But once it goes down to 70 or 110, they start caring. So if I make a meter for blood pressure which measures down to 1 millimeter resolution and all that, the doctors are seldom going to use it. They really want about a 5 millimeter mercury sort of resolution, which is and that has to be very correct, very reproducible. the sensitivity is actually very, very context sensitive. And typically, I would say that one order of magnitude below the required or the relevant levels is good enough. And of course, the sensitivity depends on cost. So optimization is the name of the game. Because the higher the sensitivity, typically higher the cost. So you need to optimize and make something which is high sensitive for the relevant context. So we want to develop sensors that can be fabricated easily and works reproducibly in a relevant range. I will start with optical biosensors because that gives a sort of feel as to what I'm going to talk about in the larger scheme of things. In these, there is, of course, there's the optically active surface, and there's an analyte which binds to it. And if I can sense the analyte binding immediately, it is called direct or label-free assays. If I have to put another probe molecule or something like that, which is labeled like a fluorescence, by fluorescence or chemicals or some bioluminescence or even nuclear, but then it becomes what is called a labeled biosensor. And of course, for ease of use in the field, a label-free biosensor is much, much more preferred. Although in various schemes, it is seen that labeled biosensors are more sensitive. But then again, whether we need that level of sensitivity is a question. So I use a very simple thing, which is called the evanescent wave absorbance. And what is a evanescent wave? When I'm talking in a photonics, symposium, I really don't have to explain what evanescent wave is. And when I'm talking in a photonics symposium, the bottom figure over here is going to be a complete anathema to people working in this domain, where I have mixed ray optics and wave optics together in the same diagram. And my physics friends always gives me a lot of abuse when I try to show this figure, but I show it nonetheless in order to say that with every total internal reflection event, there is an amount of power which leaks beyond the core, which is called the evanescent wave, and the depth of penetration and the power in the evanescent wave region depends very critically on the refractive index and the quenching coefficient at the core to the cladding or core to the outside interface. So if something gets bound to the core and it changes the refractive index or the quenching of the evanescent wave, then the light output which goes through the optical fiber changes. And that is the principle we use. The beauty of this principle is that nothing which is there in the bulk of the solution really affects the evanescent wave absorption too much, or the change of the evanescent power too much, because they have to come indeed very, very close to the surface in a nanometer range in order to affect it. So the bulk solution, so the light is not passing through the bulk solution. So therefore, the scattering events in the bulk solution does not affect the output, but the output is only affected by what is bound to the surface of the core. And that is something which we can control by using proper receptors and for the individual analytes that we want to detect. A very simple diagram of it will be something like this. I hope my cursor can be seen. It's a very weird pink colored cursor, very specifically designed for giving such presentations. So light is coupled into an optical fiber, and this here is a reaction chamber where the reaction takes place on the surface of the declad optical fiber, and the output goes to a spectrometer, or for that matter, it can be replaced with a simple photodetector. Now, the previous diagram was of a straight probe, but unfortunately, in straight probes, the depth of penetration is very low, and although it is quite suitable for that matter for small analytes, if we want to detect bacteria or things like that, then we have to increase the depth of penetration. Now, that not only for detection of larger molecules or larger things like bacteria, but if we increase the depth of penetration to some extent, not to like the order of microns or a couple of microns, something like that, but if we increase the depth of penetration or the evanescent wave power, that also gives us the possibility of increasing the sensitivity towards smaller analytes also. It is possible to increase the penetration depth by bending or tapering the optical fiber. Tapering proves to be a problem because the tapered fibers are more fragile than the bent fibers. So we typically rely on bent fibers for developing the sensors. It is very, and of course, the penetration depth increases almost 5 times from almost 169 or 180 nanometers to 612 nanometers and things like that. This was discussed by Khejwania and all in 1998. And I really thank Professor B.D. Gupta of IIT Delhi and his students who developed a basic theory of this on which I actually thrived by making the sensors which are applicable and relevant in today's context. In these event fibers, of course, as I said, that depth of penetration can be increased. And how do you bend the fiber? We started bending the fiber by using a simple candle flame. Now we have advanced to more technologically sophisticated. We use a butane flame for bending the fibers. Just dejacket the fiber, hold the fiber on top of the butane flame. These are, mind you, polymer clad silica fibers. So the polymer cladding gets melted and burnt off. At the same time, if you put slight pressure on the two ends of the fiber, it gets bent into a U shape. And my students and project staff are very adept at bending the fibers. And we have found that for the 200 micron core diameter fibers that we use, a 1.5 millimeter diameter of bending is the best optimized one. We started detecting this and we saw that we could, we started by detecting E. coli bacteria in water and we could detect down to about 1,000 E. coli per mil, which was a pretty good achievement at that time. However, 1,000 E. coli is actually pretty good achievement in the sense that if you want to really detect E. coli in the laboratory, you have to culture it for 2 to 3 days. Here, E. coli multiplies, E. coli doubles at every 20 minutes. So from 1 E. coli to about 1,000 E. coli cells, it is going to take 10 cycles of doubling. And that 10 cycles of doubling is going to take place in about 200 minutes, maybe 250 minutes, which is about 4 hours. So instead of 24, 48 hours, we reduced the detection time to 4 to 5 hours, which was an achievement in itself. But of course, we are not satisfied with that. We did some modifications and we could go down to 20 CFU per ml detection. And then we started off with a flowing sample of 5 ml volume, where we could actually detect a single bacterial cell per mil over a 5 ml volume. That means 5 bacterial cells. But unfortunately, the results of that was somewhat varied. In some cases, it was high, some cases it was low. So we could not really claim that, but we can definitely claim 10 CFU per mil, which was indeed reproducible and obviously extremely sensitive. If you look at the this was done about maybe 7 years back. Even today, this is one of the most sensitive, simple sensitive detection schemes for bacteria in water. But the biggest problem was all of these sensors were built with a 280 nanometer light, and the fiber was solarization resistant, of course. But 280 nanometer light and its detector were very costly. Actually, the company started blackmailing us in some way that they increased the price of the source like 5 times. So we decided we are going to try to get some better range of sources. And we started coating the optical fibers with gold nanoparticles. And gold nanoparticles, so what we are doing here is we are taking the evanescent wave and using the evanescent wave to elicit the localized surface plasmon resonance on the gold nanoparticles. When we did that, we found that these sensors, gold nanoparticle coated event fibers, were far more sensitive to refractive index changes than the bare fibers. And we could detect smaller molecules like proteins to a pretty low level. And this is somewhat dated. This is almost, again, this is almost like 8-10 years old. We could detect down to about 100 nanograms per mil of proteins. With E. coli, when we started doing E. coli, we could detect down to 20 CFU per mil, again, which is not too bad. And people did not before believe that gold nanoparticles will be able to detect E. coli in this way, but we proved through a paper in which was published in Plasmonics that even the LSPR field extends to a degree by which we can indeed detect E. coli cells. So we have explored antibody coating on U-bend fibers. Then we have done use dendrimer coatings which achieve 670 picomolars of protein sensitivity. We have used gold nanoparticles of fibers. But let us look at something else we worked on, which was using the conducting polymer called polyaniline. Polyaniline, everyone knows the name polyaniline. It is used in multiple types of sensors, electrochemical sensors particularly. Some people have seen that the polyaniline color changes due to the protonation, deprotonation, and the people use that for pH sensors. But can we use it for sensing something else? That is the question that was asked. Polyaniline does exist in 4 oxidation states: lithium emeraldine, emerald salt, and parniguanylene. And all of these changes state based on the protonation activity in the polyaniline. So we decided we are going to make a U-bend sensor and coat it with polyaniline and see what happens. The way we do it, we make the U-bend sensor, we dip it in alanine monomer, use ammonium persulfate to polymerize the polyaniline, which coats the U-bend part. And that indeed created nice coating on the optical fiber, and we had a polymer coated optical fiber for testing. And we could use this as a sensing device. As you can see over here, this is the polyaniline coating, an ACM picture of that. This is a cross-sectional study where we can see a thin layer of polyaniline on the surface of the optical fiber. It is about 20 to 40 nanometers thick. The interesting thing that we saw is that the chemical interaction might have an effect on the local charge distribution. So the idea is that can we use the fact that there is a charge distribution change when a receptor analyte binding event happens, and that charge distribution change, does it affect the polyaniline bulk optical structure, and use that as a sensor? And we found that that was indeed happening. We did a lot of studies on that. Actually, for that matter, this is an open question to any chemist, and I've asked my chemistry friends as to what exactly is happening. I'm not sure. When polyaniline is used with pH changes, obviously the protons go in and changes this stuff. Okay, changes the polyaniline backbone structure, and the optical change results. But if we have a receptor on the surface of polyaniline, and the receptor and an analyte comes and binds to the receptor, why is the polyaniline optical the property changing? The bulk polyaniline optical property is changing. Why is that happening? We still do not know, but we know that it happens, and that is why we could make it into a sensor. So we did this, and when we put some antibody on it, as you can see here, the absorbance kept on changing. It has not reached saturation. But we don't have to reach saturation. This is just the first step where the antibody is bound, and later on we are going to use this for antigen binding on the surface of it. And when we did that, we saw, depending on the antibody, we have a very, very sensitive sensor over here. We could detect down to 5 nanograms per mil of the antigen, or 37 picomolars for that matter, for the antigen This, I mean, you can imagine how simple a sensor this is. This is an optical fiber. You take it, you have a flame, you bend it, you put it in a jar of polyaniline, you put ammonium persulfate in it, take it out, dip it in glutaraldehyde, dip it in an antibody solution. Now you have a sensor ready. You can make it in your garage. You don't need a high-tech instrument lab for developing this sensor. And we had a sensitivity down to 5 nanograms per mil or 37 picomolars to the extent of that. Now, the beauty of this thing is that, so what is happening? There's a capture molecule on the surface of the polyaniline, and something is binding to it and changing the charge cloud around it, and that charge cloud is doing an indirect protonation, deprotonation of the polyaniline, thereby changing its optical property. So now the IgG molecules are all that are large molecules, hundreds of the kilodaltons. Can we actually do it with smaller molecules? Can the analyte molecule be smaller, or does it have to be very large only? Does it have to be proteins only? This we explored by trying to detect heavy metals in environmental samples. And what we did was we could detect. So now bovine serum albumin. The albumin is a reasonably large, actually reasonably small for that matter, biomolecule. It gets affected by lead ions. It gets denatured by lead ions for that matter. And if we put this bovine serum albumin on the surface of polyaniline, lead ions come and denature the bovine serum albumin, and that results in a charge cloud change. And we could detect down to 1 picomolar of lead ions in a solution. And for that matter, it was very selective to lead ions. It is much more selective to than the normal ions which happen in water, and even much more selective to the other heavy metals than occur in water. So as you can see, a very simple sensor detecting down to a picomolar of lead ions. Now, for copper ions, we did something else. We actually took a immunoglobulin molecule or a antibody molecule and cut it up. And cut it up meaning there is the Fab and the Fc fragments. We cut it up in the Fab and Fc fragments, threw the Fab fragments out, took the Fc. The Fc fragment had these SH groups which were exposed, and those copper binds to that very well. We used 3 techniques of cutting up the antibody molecules. Heat, we used a reducing agent, and we used UV. The UV proved to be the best actually, with a 30-minute irradiation. I mean, we did some studies on that. But more importantly, look at these results where we can, it is much more selective to copper. We can detect down to a nanomolar or even less of copper. And we could, we can employ in all sorts of environmental samples. And we did that. We actually took tap water, our lake water, we took some water from the sea. We did some characterization of that water with respect to dissolved oxygen conductivity, pH and all that. Those are not part of this study, but these are just trying to understand the background of the water quality. And then we use our same sensor for copper ions. We could detect down to a femtomolar in tap water. In lake water, of course, it was not. It was much. Tap water is much cleaner. The lake water has a lot of other junk in it. The sea water has lots of other junk in it. We could detect down to 100 nanomolars. Okay. Again, the standard limit is 5 micrograms per liter to 30 micrograms per liter. We could detect much, and look at the range of detection. The range of detection is from in tap water is from 1 picograms per liter to 1 milligrams per liter. I mean, the range is enormous for that matter. 10 to the power minus 12 to 10 to the minus 3. 9 orders of magnitude is the range, and this is the linear range of this sensor. We also used it for detection of copper in blood serum and also in soil, because in soil it is important for plant growth and all that. I mean, look at the range and look at the range of detection. It is perfectly within that scheme of things. Extremely highly, very sensitive sensor working in the range and a little bit beyond the range of sensitivities, yet and providing very, very linear standard outputs. So I don't want to go into the summary over here. We again took the same fiber and changed the coating on it. We used a chitosan capped gold nanoparticles on polystyrene sulfonate and tried to detect mercury in water, soil, and food. And we could detect mercury very, very strongly over all other heavy metals which can be present. So this is the scheme where you put BSA and you put chitosan capped gold nanoparticles. And what happens is that because of this, the mercury, the gold nanoparticles get deformed, and that is picked up by the sensor, and the LSPR response changes accordingly. We use that in DI water, and we found out a calibration. It was much more sensitive to, as I said, all sorts of other ions. And we did it with mixtures of other ions and with mercury. And as you can see, the moment we put mercury over here, the response is tremendous, which is much, much more than the responses with all sorts of other mixtures of ions. And we did this calibration in tap water. We collected soil and vegetables and fish and all sorts of other things and tried to detect mercury in that. And we saw that although the mercury in the seawater over here was less, the mercury in the fish was very high. That means there is a bioaccumulation of mercury in the sea fish in the Mumbai coast. I mean, I can go through all of these individually, but really, I mean, as you can see, this is the concentration of mercury indicated by ICP-MS, and this is with our sensor. It produces a beautiful linear line, and I would suggest that anyone from Mumbai should not eat shark and tuna. These are a little bit high on the mercury content in the fish flesh. Again, the same sensor. If we immobilize the beta-lactamase on the surface, the hydrolysis of beta-lactam antibiotics, I mean the typical antibiotics that we use, the beta-lactam antibiotics, the hydrolysis of that changes the pH in the environment, and we can detect antibiotics in water and food. We do not want antibiotics in food. We don't want chicken or milk or things in which antibiotics have been pumped. How do we know that? We can use these sensors for that. We detected ceftazidime. It works also for ampicillin. We could detect down to 1 nanograms per mil. And here we are detecting ceftazidime in milk. We could detect, we spiked milk with 1 nanograms of ceftazidime, and it worked very nicely with this sort of a sensor. We detected this thing we bought actually organic milk and did the same sort of studies, and we saw that we can get reasonably accurate results using a very, very simple setup, which does not depend on ICTs and GCMSs and things like that. So we actually did detection in cow milk, buffalo milk, packaged milk from wherever. We did it in chicken meat. And as you can see, the recovery, the accuracy was pretty high. When we say recovery, it is actually sort of accuracy. Here is 5% inaccurate. Here is 11%. But these are all within the regular parameters in which we can actually measure. So this optical fiber platform, it can work on a variety of sensors. It can detect specific bacteria, it can detect total bacterial load, heavy metals, proteins in serum, antibiotics in water, milk, and all of that. And none of these require a very big infrastructural investment. It can be fabricated with minimal training. For that matter, my daughter, when she was in 11th standard, she came to my lab to a project. She did bend these fibers, made gold nanoparticles, made a sensor out of it, and submitted some project report, whatever. I mean, so 11th standard girl can do it, 11th standard boy can do it. Anyone actually can do it with a very, very little bit of training. And all these are now packed in the form of an instrument. As you can see, I mean, this instrument is about maybe 3.5 inches by about 1.5 inches and by about 7 inches. There is a cap over here. There's a there's a cartridge, the holder over here, and this little green thing over here, you can see this is a bent optical fiber, and this instrument does all of this depending on what you have functionalized this event part with. So this is indeed a very simple sensor with a very high sensitivity and applicable for a wide variety of uses in environmental and health applications. We have also used it for detecting TNT vapors. I did not show the study over here, but this can be used for that also. So finally, I mean, really, I have to acknowledge my students who have done marvelous work. Reshma, who started, actually, Sai started the work, Reshma followed up. So the present work is what I showed here is Reshma, Nirmal, Sutapa, Kapil and Pooja, Arvind, Rosna. And earlier students who contributed, Sai, who is a faculty in IIT Madras, Amit Prabhakar, a faculty in IIT Allahabad, Jitendra is a faculty in VIT, Anjali Gaudi is a faculty in a local college here. Pallavi is a faculty in VIT, and many other students who have done all of this work, which I could present to you today. Thank you very much on behalf of all the students and myself of the lab.
Now, Professor Mukherjee, can you conclude? Can you conclude?
I'm done. I'm done. Professor Dhara, I'm done.
Yeah, Professor Dhara,
Very much. Unfortunately, we have.
Is it me or no, I can't hear Professor Dhara.
no, I can't hear as well.
Unfortunately, connection.
Yeah, Professor Dhara, we can't hear you. He's muted, or no? No, he's not muted.
Yeah, hello.
Hi, Jimmy.
Yeah.
Yeah, hello, Professor Joseph. Yeah.
Yes. Sorry,
From
that's
same
right.
US,
Yes.
but from the biomedical engineering, quite a widespread area. In the University of North Carolina.
Again, is it me or?
Yeah, I think something problem from IIT Delhi side probably.
No, sir. Joby sir was attending other session. He will be logging to the session soon.
I was parallelly attending another session. Sorry for that.
No, Professor Dhara's voice suddenly got cut off, and we can't hear him anymore.
Yeah. I see that he is able to hear us, but he is not able to. We are not able to hear him. Sometimes it happens in this WebEx. It has been noticed before also.
Yeah.
I think currently there are no chat questions, and in case anybody working and listening in this audience from the main podium, any question we can take. Yeah, Professor.
Yeah, I'm sorry. Now,
Yeah, Professor
now it
Dhara.
is back.
Yeah.
I don't know, but was there here. I don't. I'm sorry. Thank you for your excellent talk, and I but only I am happy to see your instrument, in fact, and this should be there in many of the, and it should be, I think, benchmark with the benchmark for different government laboratories where we require all this. As we are developing, going into a developed country, we must have this kind of benchmark instrument in our all standard labs, because there is a big questions of which I mean, people at the highest authority is asking about the standardization procedure. I hope that this is you can work on toward making a standard so that it will be very useful.
Yes, there are companies who have taken this up in, and they are validating this thing with standards. Yes.
Thank you very much. Sorry for a very interesting session. I have to switch because of this problem of net. Thank you very much. So now I hope Professor Vijay Kishore is there. Vijay Kishore
Yes,
Das.
I'm there. Yes,
can you load your transparency?
Yes, please.
Yeah. So while it is getting loaded, I'll brief Professor Das. He is from IIT Madras, where presently I am also geographically located, only another 40 kilometers away. And Professor Das is also, by that way, is from my own homeland, from West Bengal. Hope that he has finished his master's degree in Tagore University, Midnapur, in 1996. He's just junior to me. 1996, I joined my office, so he finished his master's, and then he did his PhD from Germany, Paderborn, in 2003, with having a lot of exposure in IIT Kharagpur as a pre-doctoral research, and he was worked in a while in CRNS, France. And since 2006, he is in the IIT Madras faculty, and he has more than 100 research publications. And so his talk will on chip pump rejection filters for silicon integrated quantum photonics. That group is quite strong, as I know, and I'll be happy to collaborate in future because I'm working towards this in this field. But your time will be there, so please you give your talk for your whole time. Thank you very much.
Yeah, thank you very much, and good afternoon to you all, and especially Dr. Dhara for nice introduction. And also, I'm really grateful to organizer for inviting me and giving me opportunity to talk something related to our close to our heart. Today, I'm going to talk about on-chip pump rejection filters for silicon integrated quantum photonics. So quantum photonics is a lot of hype, a lot of potential is there, and if you are talking about silicon, that means you can actually integrate, you can get some scalable integrated circuit, quantum photonics chip for various applications, particularly for quantum information processing. And since it is photon, it is quantum key distribution and entanglement, all those type of things you can get. And I will not go much detail about all these processing stuffs, but technologically some bottleneck is there for pump rejection filters. If you are implementing some quantum photonics chip on silicon, and I'll be concentrating on that. And yeah, so this is my talk outline. So as I mentioned, that introduction, I will give some overview, what is going on, state of the art technology across the world on silicon, using silicon photonics technology. And then the bottleneck, it is very difficult to have high extinction pump rejection filters, because high extinction pump rejection filters is a required essential component. I will tell why. And then we have been working for a while for integrating. So far, people are using off-chip high extinction filters, cascaded filters, so that they can get desired extinction. But we have been working for a while for integrating on chip, so that you can actually have source, quantum photon source, single photon source, and as well as filters, and then all other components like Mach generator, interferometers, splitters, so everything can be integrated for getting all sorts of quantum logic gates. So it's integrating a high extinction filter on chip. It's a challenge, and I will show some of our results and then summary and conclusions. And these are my PhD students right now. We have up to Riddhi Goswami 10 PhD student on roll, and first Riddhi is going to graduate. Some of our work also I will be presenting, and major portion of Arnav is already third year PhD student. His work will be presented today. Some major portion I will be presenting from him. So, so now, oh, I see that I can't change the slide. Yeah. So this is fine now. So you see here some I have taken some view graph from recently published in Nature Photonics, where actually it is shown that Alice and Bob basically two silicon photonics chip, and Alice that they will be communicating their data securely, so that no one can drop. There should not be any eavesdropper. If eavesdropper is there, you can actually detect that if someone is in the channel, and then you can discard that channel, and then you can re-establish. As long as you are not getting your channel secure by measurement, you cannot trust, and you should keep on working on that. And that is how actually the quantum key distribution or quantum communication takes place. But here you see in the Alice side, you need a laser and modulator, and instead of laser also you can have a special type of squeezed light source and entangled photon pair source. All those type of things you can actually integrate, and then you can have on-chip modulator, and then you can have a local oscillator you can mix with a certain signal, and then you can actually manipulate, controlled by different type of phase shifters, and you can have an electrical control circuit also. You can program them, and then the key or data you can actually communicate through a grating coupler, and fiber will be there, and long distance communication can be done, and then Bob can receive with a similar type of arrangement. Another fiber coupling system is there, and then again you can actually decode your data or key. And this is how it is there. So if you see that there are two chips, all these individual components, they have been demonstrated, and proof of concept is done. But here, unfortunately, if you see that people are using laser source, and they are using some kind of attenuated laser to create some key. But you know, in this type of situation, even though you attenuate, there is a chance that you can have a single bit, there will be multi photons, and there are some kind of loopholes still may be there. But if you can use entangled photon pair source through certain kind of physics like car effect, etc., then you can actually ensure that single photon and multi photon things can be discarded, and somehow you can ensure the security. So these are the all things are recently demonstrated, and here you see another demonstration. It is in Singapore, NTU, and you see this is their QKD chip, and this is, they claim that this is the smallest chip including electronics. That you see the scale, this is actually your silicon photonics chip designed for QKD purpose, and June version 3 to 4 millimeter only. And you see all the connections and PCB connections is there, so that electrical control, everything will be there. And this is said, they say that the smallest one so far demonstrated for QKD purpose, and that was a news in just beginning of this year, January 28, 2020, in Laser Focus World. All right. So if you go into the inside the chip, what is there inside actually? Normally, you can make it more and more complex, more and more scalable, more and more functionality, and everything, and key rate generations, computation purpose. You can just make more complex system. But here, what all we need in a chip, it is actually artistically it is shown. And if you see that in the beginning there is a photon source, as I mentioned, instead of laser you need a really quantum state of a photon to be generated, and then that quantum state need to be manipulated for making superposition, all this quantum logic gates or their interference, quantum interference, phase detuning, or everything can be done. But then that is actually passive and active elements we mentioned here. And then you need a single photon detector on chip integration is there, and then control and feedback electronics. So this electronics actually, since it is a silicon uninsulator, electronics can be co-integrated, and photonics things can be co-integrated, and photon source can be also demonstrated. I will just explain, and everything can be explained. If technology supports, everything can be co-integrated. So far, people are demonstrating this photonics in a different chip and electronics in a different chip, and they are controlling, as I have shown earlier in the previous two slides. And you have a photon source you are integrating, and this part you are integrating. But major challenge, one of the major challenges is that integrating single photon source. That is also some work, avalanche photo detector, everything is there, but their efficiency is low. So people are using this single photon source also off chip. Single photon source also off chip, and control electronics off chip. Only source and these components are interfering components, then interferometer, power splitters, and phase shifter, detuner, everything, they can be on chip. So when it is all these are on chip and photons are manipulated is there, along with that, if single photon source are generated by using your Fourier mixing process, spontaneous Fourier mixing process, then signal and iterator can be generated. But that generation is very weak. Does not matter, we need only single photon, weak is fine, but major problem is that unused pump source will be there. That unused pump source, you need sufficiently high, because this Chi3 process is very weak. So to significantly extract the photons and their superpositions and their manipulation, etc., you really need to, even though you can do their superposition in presence of pump photon, but at the end, before you detect things, that pump power should be actually filtered. So as I said that this single photon source is outside, so you can filter before you detect, you can filter pump outside, and that filtration needed up to 100 dB, because even 1 milliwatt residual pump is there. So if you have to bring it down to noise level, at least 100 dB pump suppression is required. So that is what is a very challenging task. So our intention is that, because single photon detectors is also getting evolved, it can be integrated, electronics can be integrated. How to integrate 100 dB pump extinction filters on chip? So that is a challenge. So that is what we have been working on. So, so another important thing is that here, if you see that a single photon source, instead of spiral waveguide, it's a long waveguide, millimeter length waveguide, so that nonlinear interaction can take place. Instead of that, if you are using a ring resonator, then pump field can be enhanced and nonlinear interaction can take place, and then signal iterator can be done. So instead of this spiral waveguide, a ring resonator also can be utilized, can be exploited. And we indeed try to do that so that we can see how our pump rejection filter is effective. So that is how ring resonator fabricated silicon micro ring resonator. We have our indigenous technology we have developed at IIT Madras. So here it is shown at 50 micrometer ring resonator, and there is a thermo-optic micro heaters are there, aluminum contact pads there, so that you can actually thermo-optically detune the micro ring resonator. Okay, so this is how this thing we have fabricated, and then we have a bus waveguide. You can launch pump, and then pump if it is in the resonant, then it can be enhanced, and signal and idler will be generated, and that can be coming through along with the pump, little bit the residual pump. It will come and you can extract, you can filter. So, however, one major problem of the ring resonator, because whenever you are even if it is for straight waveguide also, if you are pumping intensely at 1550 nanometer communication band, then two pump photon can be jointly absorbed and electron hole pair can be generated. Two photon absorption can take place. That is actually a problem. That is actually problem case. You cannot avoid, of course, that two photon absorption. Maximum what you can do that generated electron hole pair, you can actually, by giving a reverse bias with a PN junction, etc., you can actually drive away a free carrier. So if free carriers are there, what are the problems? One thing is that free carrier actually it will add losses, and it will add also some kind of plasma dispersion for refractive index change. Because of the plasma dispersion, not only that, the free electron hole pair, when generated, the electron also, because of the indirect path is there, it can be recombined again to valence band, then it will release some heat, phonons, and then temperature will rise, and because of the thermo-optic effect, refractive index will change. So all these effects together, what happens? There is certain type of bistability or hysteresis observed at a higher pump power level. So if you see here, we have just shown that if you just use a particular pump wavelength close to the resonant of the ring resonator, and then if you are increasing the bias and tune, then what happens? In the forward direction, you see this transmission will be there and then coming up. That means only this much extinction dropping will be there. But when you are returning back, whenever you are reducing the bias voltage, that thermo-optically if you reverse, then you will really see a dramatic extinction, large extinction. You can actually detune to laser wavelength, so that more power can be actually accumulated. Pump power will be, pump field strength will be enhanced in the micro ring resonator, and in that case, non-linear effect will be there. So in this way, we could somehow control, we can program this micro heater so that we can bring this laser pump wavelength close to the resonance in this position, in this operating point. And in that case, we could see really, we try to see that stimulated four-way mixing process. So the pump wavelength and this is the wavelength together just launched, just to see whether it is working or not. Then we see that idler is being generated, and conjugate idler also is generated, just because we don't have a single photon detector. So we try to see that this stimulated four-way mixing process, that it is working. If you stop this signal power, then only pump is there. That means you can actually generate this idler and signal entangled photon pair. But that photon pair will be, as I said, that generation rate is very small. You will not be able to detect them in a normal classical way in your optical spectrum analyzer. So you need to suppress the pump reasonably, at least 100 dB. Then only you can actually get the signal and idler entangled photon pair. You can just demultiplex them. Even if you demultiplex them, filter only just 30 dB, 40 dB, it's not enough. You need really 100 dB so that actual single photon can be detected, suppressing the noise level. But as I said, that if you are operating at operating point A and operating point B, there is a dramatic change. If you see here, idler generation minus 41 dBm, and here actually you could actually gain more than 7 dB. Minus 34 dBm you are getting when you are operating. That means that time electric field strength is more. So with doing that, what we see that even the stimulated four-way mixing process, where idler and signal entangled photon pair can be generated, but this pump is, even though it is resonant to the ring resonator, but it is still significantly high compared to your signal level. So it is a really challenging task to suppress this pump. So what we thought, other people already started doing, exploring that integrating the integrating the pump rejection filter on chip, and they have shown that actually if you are using a DVR source, DVR, After this one, if you are using a DBR, then this DBR for a particular phase matched wavelength, that will be reflected back, and then signal and radar can be coming out. So the technique they have used, if you are just simply using DBR, what happens? If it is just pump wavelength, if it is reflecting back, what happens in the return path? Again, it will couple to the ring. So that will again add some kind of noise disturbance to the ring resonator. So you need a filter which actually does not come back to the ring again. Instead of that, you can drop. You can actually, you should have a drop path so that you can filter out. So they have designed a particular DBR structure, both sidewall grating structure and 180-degree phase shift in both sides. Then what happens if you are launching a T0 mode of the waveguide? Then in the reverse path, the pump wavelength, if it is phase match, that will be coupled to T1 mode. So this T1 mode actually, it will support both T0 and T1, and backward direction it is T1 mode, and that T1 mode can be coupled with a special type of directional coupler, mode matching coupler, and you can actually feedback. This T1 can be filtered out. So that is how their technique. But they found that if you are using a single DPR, you know that longer the length reflection could be higher, but even it is increasing up to 1 millimeter, 2 millimeter, 5 millimeter also, they could not actually produce sufficient extinction because of some kind of forward scattering, coherent noise will be there, and that is why it is not possible. What they did, they have cascaded multiple DBR incoherently. That means it is first phase it will be filtered, and then next another filter will be there, and that will be again filtering, but that filter reflected back thing should not again interfere with this one, so that it should be incoherently. This length should be randomly chosen, sufficiently long, so that you can actually get. And in this way, they reported that about 60 dB, 4 different DBR structure, they integrated each of them more than hundreds of micrometer, and then they could actually deplete up to 60 dB. But that then you see that is actually length is increasing, and you have to do this zigzag path so that actually back reflected light, a lot of noise can be filtered to the substrate here. So we thought that why not try to get a single and well-designed DBR structure so that you can make a compact, very high extinction filter. So earlier we worked, one of our PhD student Parimolsa, he demonstrated a DBR structure. So it was actually demonstrated before this earlier thing, whatever we have shown here. This is 2020, but before that we had another type of DBR structure, one side grating basically, and also grating region it is multi-moded. But what we have designed at that time, that you are launching fundamental mode, and backward direction it is actually coupling to first order mode, but that first order mode will not be supported in the input side single mode waveguide. So that will be actually radiated to the substrate. So we don't need a drop, because this is an unused pump and that is a waste, and that we don't need to reuse that. It will be lost and it will not return back to the ring where your photon source is generated. So in this way, actually, we could, we analyzed with coupled mode theory, and we could demonstrate earlier up to 40 dB. Then our another PhD student continued to explore, redesign that type of DBR structure, and he actually designed two different type of architecture with a length control as well as width control, and the modulation, duty cycle, all those type of things, up to 450 micrometer getting structure designed and fabricated. And two types of structure he studied, that is actually, one is a sinusoidal modulation, another is just kind of a square modulation, and compare. Okay, and this is the fabricated device. If you see rectangular modulation with a duty cycle not exactly 50%, and then sinusoidal modulation here, it is shown ASEAN pictures, and they have been characterized and found that you see that as expected from our simulation, that rectangular square modulation, it is giving a very nice stop band, rectangular stop band. If you see, that can be aligned to your pump, and you see extinction up to going up to 75 dB from starting from here, maybe 25 to 75, so up to 50 dB extinction, 50 to 55 dB extinction it could be achieved. And sinusoidal case, actually, because modulation is less, and there we found that it is extinction is more and bandwidth is smaller. Somewhat, we found that that this is a sinusoidal rating structure is better suited, because you can actually use a narrow filter just to stop the pump only. Pump wavelength, and both sides, your idler and signal, can be filtered out. So here you see that with that thing, normally at this level here, if you see, sorry. So here, if you see, this is already reaching to the noise level. But according to our theory, we felt that the extinction should be more. Our optical spectrum analyzer could not actually resolve that because of the sensitivity issue, and also the source is not so high. So what we did, we just a little bit modified that. We use a tunable laser source and amplified, and then we just tuned from pass band to stop band, and then we compare, and then we found that it is actually about 60 dB extinction we could get, and even 800 picometer wavelength bandwidth, H56. So earlier we have shown that the 4 different DVR structures cascaded incoherently, and then only they could actually demonstrate about 60 dB. But here only single stage for 50 micrometer we could actually demonstrate 60 dB. But this thing is that we are also planning that this can be further improved by modulation, as well as a little bit longer length we have to test, and we could believe that whatever desired 100 dB extinction, probably it is possible to integrate with a single stage on chip. So in this way, your device architecture, entire thing will be very compact, and your things will be more scalable. Okay, and then we also did some other experiment. So like that, you see, normally what happened, in your ring, suppose your ring is sitting here, and then pump is actually decomposed into signal and idler into entangled photon pair, and this pump will come here, and then in this DVR structure, pump will be filtered. And this is relatively larger cross section, pump intensity will be dropped, only it will be reflected back. But thing is that if this pump, again, while deflecting back, then it is some kind of distributed structure is there. In this structure also, pump can again decompose into entangled photon pair source, and that will add as a noise to your original signal generated in your ring resonator or spiral waveguide. So that is actually a huge problem. But we thought that why not using DVR itself as a pumping, as a source generator. So you don't need a ring resonator probably if it will work well. So in that case, as pump propagates, it will generate a signal and idler in the forward direction, and the pump slowly it will be decaying because of the DVR structure and attenuation. Okay, so we did that study by taking that DVR structure, and this is our experimental setup basically. And then we have tried to test it, how it works for stimulated four-way mixing process. The pump is there and signal is there. We have a 50-50 fiber coupler, we combine together, and simultaneously we amplify them so that we have significant amount of pump and signal is there. And then we see that pump will be aligned to the stop band, and then how much idler will be generated because of the stimulated Fourier mixing process, and then we can use this thing. So with that, we just found that if pump is in the pass band, that means pump here, this is your, I think, AAC source it is showing. You can see the signature of the DVR structure. So this is actually the stop band of the DVR structure. That is there, and then pump you are just aligning just outside the stop band, and here idler the signal is also, it is outside the stop band, other side, other edge. Now you see, because of the presence of that one, both are traveling, it is like a straight waveguide, and as they travel, then stimulated four-way mixing process happens, so idler is generated here. And also you can see conjugate idler will be generated. So one will be 2 omega p minus omega s, that is actually omega I, otherwise another is 2 omega s minus omega p, that is actually conjugate. Both are generated. So that means if we stop idler, then lambda p actually can generate a signal and idler here as an entangled photon pair. That is the for sure. As if we can detect, we can do that. So itself, the waveguide, even though it is traveling through state, it will be generating. But we don't know what is happening in this signal idler conjugate. They are actually nonlinear interaction process happening before the DBF structure or within the DBF structure or after. If it is not happening within the DBF structure, after that will not happen because pump strength will be reduced. So what is happening, maybe most probably the preceding couple of millimeter length waveguide, there actually this nonlinear things happening, because in the DBR this pump will be actually supposed to be diluted and dissipated. So what we did, now we aligned the pump exactly to the stop band. So when you align the pump here, then you see idler is as it is, according to whatever level is there, we maintain that one, and pump, actually you see pump is suppressed significantly compared to, you see here actually it was at least you see 60 dB it's supposed to be suppressed. It is suppressed indeed. And idler is generated as usual, you see idler is generated, and that is more than the pump. So that's the beauty. So you can actually simple straight waveguide along with integrated DBS structure you can use, and you just pump, and then you can actually generate entangled photon pair, which is actually higher than the pump photon. But this pump photon, whatever residual things, also you can actually suppress further. If you just phase match DBR again, you can integrate one more, then you can use. So this is how we see that actually the entangled photon pair or single photon pair can be generated and detected by on-chip integration of pump rejection filter. So this is actually the gain, whatever we are getting, some data is there. So I think I am just setting time. I think this is all what I wanted to discuss. And if you have any questions, maybe I can answer. So our next intention is that this ring resonator as well as DBS structure we have to integrate together, and also we can just use for some complex Mach gender interparameters, so that Hadamard gate and CZ control not all those type of quantum logic gates we have to do, and perhaps we have to do all sorts of computation and QKD distribution. And we would like to actually acknowledge that DST for funding a quantum photonics project under COAST, Quantum Science and Technology Project. It's a network project, one of the project we have got for generating entangled photon pair, single photon source in silicon. So we have already done, and we are awaited for the single photon detector so that we can make all this type of operation, guard detection, etc. Thank you very much. Yeah, if you have any questions, I would be happy to answer.
Great. Thank you very much in finishing exactly in time, in the sense of full time of 30 minutes. That's praiseworthy, because it's a complicated subject, and you have covered it very nicely. Presently, I have some sort of interest in your subject, of course, but in advance and very complicated. But otherwise, because my son is working actually presently in Arizona, University of Arizona, this particular field. So I got an understanding what is the importance of your work, because we talk of Bob and Alice in lab, that's fine, but who are you? Otherwise, you cannot communicate. So all practical purpose. Yeah, because you see, Jagdish Bose discovered radio, but to make it really working, you have to have Marconi. Whether the credit goes which way is a matter of argument, but Marconi's contribution is remarkable. And here we find that your role is somewhat in that, but doesn't matter, nevertheless. So I wish you best of luck. Any questions from the participants? So I'll be very good. I'll be happy if somebody asks questions. Otherwise, I can tell that this is a immensely important field for today's quantum communications. Forget about computation, that is one level more important, complicated subject. But quantum communication, which is more valued, you can see from the first speaker itself what is the cost involved in communications. In 6G, you have $13 trillion. You can see if the quantum computation, then it depending on the security and safety, how much more manifold investment is expected in that, because every country is waiting for it, for the secure data. So I thank Professor Das for working such a complicated in a area, and I wish him success in contributing towards the world scientific community from Indian side.
Thank you very much.
So, are you aware?
Yeah, I'm in here. Yeah. Yeah, I think we could close. So thank you, Dr. Sandeep Chara, for chairing this whole session and taking care of all the different invited talks and contributed talks. So thank you everybody for joining this session. Thank you very much, and thank you Joy and all the other invited speakers. So we will have the next session starting at 1:30. So we have just around 20 minutes left before the next session will be starting in this hall. So thank you everybody, and
Thank you. Thank you very much, Joby. Thank you very much. Thank you all.
Thank you.
Please. So 5-10 minutes. Yeah. That's quite good, I hope so.
Thank you.
Thank you.
Yeah.
Welcome.
Oh, may I do a test with anybody who is already there in the session?
Hello, Cornelia. I'm here.
Hello, nice to see you. Good. Great that you're there. Yeah. And thank you for the invitation.
Thank you. How are you doing?
Fine, yeah.
So, the COVID situation is affecting you also there, and
yes, even more than before. Yes, we are again in a lockdown, so we can go to the university, but we give digital lessons, so there's no lecture in person anymore, and everything in the public life is very restricted. Many things are closed, and it seems that for December on it will be even worse, so that there will be more closings. How is it in India?
Oh, similar situation, but almost the same situation here.
Yeah.
Teaching.
So Delhi is a very big city, so perhaps this is even more difficult to handle such a thing then.
Yeah, correct. Thank you for coming, and just everything is, I think, going fine.
Yeah.
So maybe just the earlier session just got over. So,
okay.
Yeah,
So,
just now it got over. Yeah, so we are all waiting for the next session. Yeah.
So will it start on time or will it be done?
Yeah, it will start exactly on time. There will be no delay.
Okay, good. Yeah.
Okay, see you at 1:30 here.
Yeah,
Another
see you. Yeah.
15 minutes. Yeah. Okay, thank you.
1:30.
Nice.
Yeah, hello, Sandil.
Hello, Joby. Yeah. Yeah, where is my name here in this? I do not know. Okay, it is there on this corner. Yeah. Hello. Yeah.
Yeah, you can keep the video also on.
Good morning, madam. Cornelia Dens, madam.
Your video is not on.
Hello. Yeah. Nice to see you, to hear you.
Sandil, I was seeing you on video right now for some time, but now that is gone.
Oh, is it? No, it is there. My video is on only. Yeah. You can see that. Yeah. I can see my photo there. Yeah. It is on.
I don't see, unfortunately.
Yeah, that's right. For your videos, there seems to be a sort of warning sign. It's a tiny warning sign.
Maybe I will close the video and open it again.
Some bandwidth issue. So from your place, it is not coming well. Yeah. Anyway, no problem. No problem. It was good that if Professor Cornelia also could send the after communicated, but might not have seen your face.
The first time I am also seeing you, madam. Wie geht's, madam?
Sehr gut, danke. You speak many languages then.
No. I was a humble fellow in Jena.
I see. Okay, yeah. Jena is also a big city of optics. Yeah.
Optics. Yeah, I was working with the professor Frank Wyrowski.
Yes. I remember. So you made numerical simulations on optical systems. Yeah. I know him. Yeah.
Yeah, I worked in 2000, 2001. I was in Jena. Yeah.
Okay, that was the time when I went to Münster at this time. Yeah, long time ago. Anyhow.
Very good. Yeah.
Almost 20 years now.
Yeah, 20 years. Yeah, sure.
I was impressed about your conference. I entered yesterday as an attendee, and it's like a real lecture hall with different rooms. So that's very nice. Not everybody does it like that. But it was very nice looking, like an avatar. You walk around. That's nice.
Thank you. It's nice because without travel, we are able to still interact and large number of talks we could listen to. Very good. Yeah.
Yeah, you have the impression you really are more in a conference than if you only click on a video Zoom. Yeah, that's right.
One advantage I noticed when we listen to talks like this, we are more focused towards the talk. When we are in hall, sometimes we are distracted with many things.
Of course, you can also be distracted when you're on your computer and can do something else beneath. But that's right. You can listen more to the talk, and it's and more people can listen to it probably than typically. So people that cannot travel can still be at the conference. That's also good.
So, Joby, now the time is 1:25 here in India, right?
Yeah, it is 1:20, 1:23. We have around, we will start just after 1:30. Yeah.
Okay.
So here in Germany, it's 9 o'clock in the morning in a couple of minutes. It's early morning.
Yeah, here it is just lunch break in between.
That's right, yeah.
And Professor Kehar Singh was also here in the morning session for some time, but generally he is unable to join in the afternoon session.
Okay, yeah. So give him my greetings if you see him.
Yeah, I will. Yeah.
So how do you handle it with questions afterwards? Are there questions afterwards, or how does it work?
Yeah, right. It's basically you have to look at the chat window where because we see only the we don't see the participants because participants will be very large. We only see the people who are in the something like a podium. We all are in one separate link. So there will be many people who may be attending the talk, but they interact only through chat.
Okay, good. Yeah, yeah.
So if any questions are coming after your talk, just look at the chat, then we answer.
And then I read the questions and then answer. I do it myself. Okay, good. Yeah.
Or else the session chair, Professor Senthil, can also read the question, then you can answer.
Okay, yeah.
You mean it comes in the chat box, is it?
That's correct. The questions will come in the chat box, correct.
But the chat box can be seen by everybody, right? Those who are in the podium.
Can be seen, everybody. Chat box can be seen by everybody.
Okay, okay. Right.
But this is Dr. Dhara. Normally, I'll suggest the chair session should gist the question and give it to the speakers. Speakers going to the chat box is not convenient.
Yeah, correct. Chairperson.
But I see it anyhow, so we can share also, depending on how it works. Fine with me.
Yeah. It's whatever is convenient to the speaker, that is fine. I can also repeat the question. If the speaker wants to directly address, that's also fine with me. Yeah. So depends on them.
So perhaps after the talk, immediately you can read the first question until I open the chat, and then we can see how to continue. Yeah.
In general, the number of questions are quite less. That's what we noticed. Maybe maximum 1 or 2 questions only.
Okay, yeah.
Okay, right after Cornelia's talk is Sandeep Thara. Yeah, he's already in. He was sharing the earlier session. And the co-chair, Professor Anuj Thawan, will be late, Senthil Kumaran. So he is an IOE presentation of his department. So he just called me to say that he may come a little late. So anyway, Senthil is here, you can.
So on the screen, it is saying that next session will be starting soon. That will disappear. Is it, Joby? How do we know that?
Yes, it has disappeared. So shall I now share my screen?
Yeah.
So now I can put my talk on. Yeah.
Yeah. So I will also do the introduction. Yeah.
We can wait. We have another 2 minutes. Yeah. So by that time you can start.
Okay. I will introduce the speakers, Joby, then.
Yes, please. You can start. Yeah, you can.
Yeah.
So you see now my screen, is that right? Yes, you see it.
It is done. Yeah, you can put it in the full screen also. After
good. Yeah.
After the introduction, you could put it in the full screen. Yeah.
Okay, good. Very good.
Okay. Welcome to International Conference on Emerging Electronics 2020. And after lunch session, now we are having 4 presentations. The first one is an invited talk by Professor Cornelia Dens. Let me introduce the speaker. Professor Cornelia Denz is from Institute of Optics, University of Münster, Germany. About her biodata, she has received her PhD and tenure from Darmstadt University of Technology, Germany in 1990 and 1999 respectively. In 1992, she received Leis Meitner Award for her work in optical neural networks, and in 1999, the Adolf Messer Award for the development of nonlinear dynamic phase contrast microscopy. Since 2001, she is a professor for applied physics at the University of Münster, Germany, leading a group of about 25. She is head of the Institute of Applied Physics. She is an author of more than 300 publications and 5 books. Professor Cornelia Denz's main research theme is structuring light to tailor matter and includes nanophotonics, biophotonics, as well as solid state and information optics. Other interests include integrated photonics, artificial photonic materials, and complex optical traps. Professor Cornelia Denz is a Fellow of Optical Society of America and European Optical Society. She is also committed to foster gender equality and support young female physicists. Now I invite Professor Cornelia Denz to give her presentation. Yeah.
Yeah, Professor Senthilkumaran, thank you very much for this nice introduction, and thank you very much for inviting me. I'm very pleased to come so quickly to India and to give a presentation. And the presentation will be about something that has to do with structured light, with its topological photonic lattices, and I want to explain you how 2D materials can be photonics. Let me first introduce you the team, because the main author or co-author of this publication or this talk is Haitham Hanafi, who did a lot in this field, and I'm very indebted to him that he also helped me to prepare this presentation. So, of course, we are all now in this situation. We all are subject to COVID-19 precautions. So that's why we are here also in this nice digital conference that has a very nice appearance with all its conference rooms and feels like a little bit more like a real conference. So let us start to ask, what is topology? So most of you are very familiar with symmetry, and symmetry is a very powerful concept of nature because it defines its beauty, like you see here in the snow crystal, an Escher picture, or this graphical sketch from Leonardo da Vinci. But the question we want to ask is, which operation, for example, translation and rotation, reproduces the same system? And you know here, if you turn such a 6-fold structure from 30 degrees, it will be the same. Here you can mirror, or here it's a little bit more difficult how you can turn the system, and it's the same. Symmetry is also in physics connected to phase transition, because if you have an emergent ordered phase, then it can be understood as a phase transition. Think of temperature. An ordered state appears at lower temperature when the system spontaneously loses one of the symmetries. And you know all examples about it. Crystals break the translation and rotational symmetry of free space, or liquid crystals break rotational but not translational symmetry. And there's magnets and superfluids that break also different symmetries. So you're familiar with that. But in 1980, there was a strange discovery, because it was an ordered phase that was discovered beyond symmetry breaking. And this was the case that when you have an electrons confined to a plane and subject to a magnetic field, then it's shown that at lower temperature, then there is a sort of quantized conductance for one direction, and also a change in the conduction at the other direction when there is a plateau leaving. So the question was, what is that? And what type of order causes a quantization here? Because there must be also some sort of phase transition. And this phase was called topological ordered phase. So it's a strange phase that is insulating, but has conducting edges or surfaces when it's, for example, next to an ordinary phase or to vacuum. And there is a physical function that does not change, and that is called topological invariant. It's a quantity that also doesn't change under continuous transformation or deformation. And that is something very strange. and at first glance had nothing to do with lattices. But in 1988, Haldane proposed that also a honeycomb lattice, such a graphene here, would be something that can be subject to a quantum Hall effect without magnetic field. So it's a discrete system, and by the interaction of such a unit cell with its neighbors and next nearest neighbors, he could show that there is such a topological phase existing. And in 2005, Kane and Mele modified the model and then explained that as an insulator, a so-called Chern insulator. And this has led to the Nobel Award in 2016 for the theoretical discoveries of topological phase and topological phase transitions. And so our question for this talk is, what is a topological insulator? Why is graphene important? And what has to do with photonics? Can we exploit something for it for photonics? And for that, let me give me some more information about topology. We said topology is a smooth deformation that keeps the system the same, similar to symmetry, but somehow different. And some geometrical shapes can be classified as being topological invariant. And this is defined by a number g. And this topological invariant is the integral over a certain surface for a certain physical variable. And for example, if you see here in this structure, if you have, for example, a sphere doesn't have a genus, it has genus 0, but it would be the same, like, for example, this spoon. You can transform one into the other, but you do not change the topological invariant. The same is for this donut-shaped structure in comparison with a cup. It has one hole, and the number of holes is a topological invariant. Everything else is the same. Or this one, like a pretzel, and you see here that a cup or this object also has two openings. And even in art that has been played with, here's a sculpture from Henry Moore that also has two holes, whereas here, this is an open structure if you look at it from a little bit different side. So it is also a topological shape 2, genus 2 function. So if we now translate this to electronic band structures, then we see that there's also a topologically invariant number, which is called the Chern number. And equally, it is defined in a way that it is the integral over a certain Berry curvature, or you could say over the Brillouin zone, and then calculating that you also get an invariant number. And this invariant number can only be changed if there is a topological phase transition, which is the case if you close a band gap in a periodic material. And here's some examples to show how powerful this is. You see here a cylinder, and you see a Möbius strip. And if you look at both, they both have one hole, so they are of the same topological nature. And then you see, if you would see this as a sort of band structure, that you have here some edges that join together, but they join together in different directions, but they both are of the same genus or the same Chern number. So this is topology. And now I want to discuss with you in 3 chapters. First of all, what are photonic lattices and how can we realize photonic graphene, for example, in order to have the same situation as in the electronic state, in the photonic state. And then I want to discuss with you photonic B-layer graphene that has already some special features. And afterwards, we will discuss some other photonic lattices with special band structures, and we'll discuss if there is topological features like topological insulation. So first of all, what are photonic lattices? We have discussed about solid state and condensed matter crystals, and graphene is a very special material. It was first discovered as a first 2D material, and it has a honeycomb lattice of carbon atoms. And so this atomic monolayer has intriguing and unusual electronic features. And one of them is the intriguing band structure, because if you look at the band structure, you see that this has 2 fundamental bands, and they are touched in 6 points due to the symmetry. And in these 6 points, there's a singularity at the point of touching. And if you look around, the dispersion relation is linear around. And this is quite unusual and special and makes graphene especially attractive for many also investigations with certain band structures. And again, we want to see how we can do that in photonics, because if we could realize a material with that band structure in photonics, we could have a look at Dirac physics with photonics. And that could be very attractive because in photonics, we would expect that we can easily modulate such a system and can change its features. So what is interesting beyond the Dirac points at this graphene? If you look again at the Dirac point, I've told you that there is a singularity and a linear dispersion relation. But there's an additional degree of freedom, which is called a pseudospin, which is the direction of motion of quasi-particles determined by the spin rotation direction. And the spin can be pointing, for example, in that direction, inside, or in the outside direction. Also, you can think of that you have topological protected states that can only live on a surface of such a structure in one of the bands. And whereas this defines the so-called pseudospin, this defines a topological insulator. And this means that we have a lot of access in such a Dirac system to very exotic quantum effects, like half-integer quantum Hall effect, Klein tunneling, Zitterbewegung, oder reality or non-trivial Berry phase. So in a way, if we could realize these things, like pseudospin in photonic lattices, we could access all these exotic quantum states. And this can in fact be done. So what do we mean with photonic lattices? So photonic lattices in general mimic two-dimensional electronic materials. And so it's easy in photonics to realize complex 2D materials. We can control a lot of initial conditions, and we can have a direct observation of the wave dynamics. And typically you do that by structuring the refractive index by light, having a material that reacts on light to change the refractive index. And then as another approach, you can realize different electronic structures like a diamond or graphene by superimposing by light, for example, here 4 different K vectors, or here 6 different K vectors in 2 pairs, and they typically lie on a ring. And because they lie on a ring, this means that in optics, if the K vectors lie on a ring, you have a structure that in the propagation direction does not change. It's invariant, and therefore it's a quasi 2D material that we realize by that technique. And if we look at such a structure, then what would you see in a photonic graphene? We would have also a Brillouin zone, and in the Brillouin zone, we would have Bloch vectors. This is a description of propagation of light in such a periodic structure. We also would see that such a Bloch vector situation has some discontinuity and their linear dispersion relation and at the band edge. And we would see that light then propagates at this structure with the equal propagation speed in all directions. So group velocity is constant. So what would we see as a notion of such a band structure would be so-called conical diffraction. That is one feature where we can analyze such a photonic system like a photonic graphene. And here are some examples that other people did that. A very pioneering work from 2007 is this one, where conical diffraction was shown to take place and to spread as it should be. Also later on, people have shown that conical diffraction, if addressed with different polarizations, for example, can also lead to pseudospin and also to some vortices. We see here this sort of fork-like structure and then angular momentum. And finally, it was also shown that if you break the symmetry, for example, by having not a system that has straight structures, but having sort of one helical direction that breaks the time reversal symmetry, then such a hexagonal band structure this is degenerate, it breaks up and you have a band gap, and then you get a topological insulator, and because you have broken the time reversal symmetry, then this is a so-called Floquet topological insulator. And this has all been shown, and it's quite spectacular because you see that photonics in this way is a material you can use for this purpose. Here you see that the insulating in optics means that light propagates only on the edges of a material. So let me summarize. When we compare now condensed matter physics with optics, in condensed matter physics, we have the nonlinear Schrödinger equation to describe how an electron moves in a potential. In optics, we have the paraxial wave equation. And the potential in electronics is in optics the refractive index, or the photonic lattice. And if we now look at graphene, we know that in graphene, as I discussed, we have a conical intersection with a Dirac cone. And in optics, we can say that we also have a sort of photonics graphene. And the notion of this Dirac cone is that we see conical diffraction. And in that way, we can translate everything from condensed matter physics to optics. And nowadays, there are other questions open than only graphene. Beyond graphene, people are now looking in solid-state physics, for example, for van der Waals heterostructures that have loosely connected different sheets of one-dimensional structures, or they look, for example, at B-layer structures that are shifted against each other, like B-layer graphene. And the question is, can we realize this also in photonics? And especially B-layer graphene is quite attractive because as you see here, it creates Moiré superlattices. So a B-layer graphene is not only graphene, but it has also other periodicities that have the same symmetry. This is called twistronics because it allows to change band structures continuously, and in between there are very spectacular structures. And thus our approach is to transfer B-layer graphene to optics to get a photonics twistronics, and we will do that with photonic photorefractive lattices. Another question is there some special structures that have a flat band? So this is a Dirac cone and have a third band, a flat band, because in this case, there is a diabolic direct point, but at the same time, you have a flat band without dispersion. And there are two lattices known to do so. One is the Lieb lattice, the other is the Kagome lattice. And whereas the Kagome lattice is like graphene, one that has a 6-fold structure, the Lieb lattice has a quadratic or 4-fold structure, and therefore is very flexible and attractive. So we will look at the Lieb lattice and transfer this in order to look at photonic flat bands and topological states by femtosecond laser-induced methods. So in my second episode, I want to talk about twisted B-layer graphene, how we can realize it. So we realize that with the so-called photorefractive material, which is shown here, which can be shined on by a light structure that then creates a two-dimensional photonic structure, and this photonic structure then represents the analogon of an electronic one. And we can use, therefore, spatial light modulators to create it and cameras to detect it. And this is called optical induction of a material. So, for example, we can here realize a photonic graphene by just using amplitude and phase, shine it here on the material, and the material then creates this refractive index, and this is exactly the shape of the graphene. We can also use this to create quasi-crystalline crystals in the same technique, or even creating random structures where, for example, you can see that Anderson localization takes place. Overall, this means that we have a sort of structure that can be 1D to 3D band structures that are modeled by the nonlinear Schrödinger equation. And that's why we can realize discrete nonlinear physics, but also the same equation allows us to model any pattern, for example, 2D patterns, and then we can create complex photonic crystals by light and photonic 2D lattices. So this is also a toolbox for complex solid states or quantum physics. And in that way, for some years, this has been used as a test bed to demonstrate many things. For example, creating solitons in a photonic lattice. This is a diamond lattice. And if light propagates in this diamond lattice, it's subject to diffraction. But if we now go to a band gap and have light propagating here, light cannot spread in the band gap, so you get a discrete gap soliton. Also, it was shown, especially with hexagonal graphene lattices, that there is, if you have a certain incident direction, so changing k vectors, you can have, for example, here Landau-Zener tunneling, or if you look here at the Brillouin zone, you can also have Rabi oscillation between equalized state at the same energy level. So there's a lot of examples where you can show that these graphene or diamond lattices in photonics are very useful in order to realize different functions easily compared to the solid state counterpart. How do we do this in experiment? We typically use a laser beam, and this laser beam is then modulated by a spatial light modulator. The spatial light modulator then goes to the material, and the spatial light modulator modulates amplitude and phase in order to create such a quasi-crystalline structure, goes to the material. In the material, the light is changed into a refractive index structure, and we can now check if there's a refractive index structure. And one way is to illuminate the material with a plane wave, and then you see exactly the refractive index structure. So this is the refractive index structure in our now photonic material. And now you can check if this photonic material also changes the nature as it does. And here you see something we call Brillouin zone spectroscopy. By shining all K vectors into it, we can see the Brillouin zone of this material. And so we can check it with the Brillouin zone like in every solid state material. So what can we do? First of all, we have realized photonic graphene. And photonic graphene can be, for example, changed in its lattice constant by just changing the radius of the ring with which we fabricate that structure. So here, for example, you see different graphene sizes from 50 to 20 micrometer, and you see in the Fourier transform that this is perfect graphene. And you see here by plane wave guiding that we have exactly the refractive index resembling a graphene structure. Now we can also think of exciting the direct points. And that's what you can do. Here you see again the Brillouin zone. This is a calculated Brillouin zone of our material. And if you excite now exactly with the structure of the first Brillouin zone, so the K prime vectors of the direct points, this is the excitation then we see exactly such a conical diffraction. And conical diffraction in experiment is a little bit more noisy, but you see exactly that you have conical diffraction. So in fact, we have a real Brillouin zone of graphene with that conical diffraction. Now we want to go ahead, and what we want to realize is bilayer graphene, twisted bilayer graphene. And there we can exploit that in optics we can superimpose incoherently one lattice with the other lattice, and this gives immediately, by superposition in light, such a structure. And this structure, even in the smallest zone, gives this twisted bilayer graphene. And if we now put that into the material, we immediately have a photonic bilayer graphene, which is shown here. You see here the bilayer structure in the far field of the diffraction pattern. And also you see that it's important that in our material is in the Z direction, not changing. So in fact, we have a really 2D material. And this 2D material can now be investigated. And here you see different angles of this twisted bilayer graphene. You see that you have moire structures of different structure. You see that in plane wave guiding, we have realized all these structures. So we have really a photonic material. Then we have here the Fourier transform showing. And most important, we have here in simulations and experiments the different Brillouin zones. And you see that the Brillouin zones also in experiment show very well the moire structure. You always see that you have two graphene lattices with different orientations being superimposed. So in fact, it's very easy to make photonic twisted bilayer graphene with different structures. And here you see what happens if you excite all direct points of these single areas with different angles. You see how the diffraction changes and how this is modulated. And here you see the different angles. And if we excite all 12 points of this structure, we see even more fancy structures. I show that here in the next video. So that if the Dirac points are close together, only a few degrees are changed, and there is strong interaction. You see this also here. And if they go far away, they are more separated and can be excited independently. So by just changing the angle of the twisted bilayer graphene, you get completely different answers of the system in conical diffraction, and you can easily tune this in optics. Now at the third part, I want to look at Lieb-like photonic lattices. And let me introduce what that is. A Lieb lattice is one that has two lattice constant and a third lattice constant. So two lattice constant in a square configuration, as you see here by the green points, and one that has a larger lattice constant, which is the gray points. And this threefold structure gives a Brillouin zone that has 4 diabolic points, but also has a flat band. And if you enlarge this area, you see that you have, again, a linear dispersion, but in the middle, you have that flat band where there's no diffraction. So you can realize pseudospins by that, and wild states, and conical diffraction. And I want to show you that because we have realized that with a different technique. In this technique, we use femtosecond lasers to write such a refractive index structure directly into the material. And this is a very powerful technique. You can write tiny laser structures with it, or you can write integrated circuits into it, so integrated photonic chips, for example, in lithium niobate by it. But here I want to use that in order to write down photonic lattices into a material. And for that, we need to write a structure in depth, which is quite challenging because if you write into the depths of the material, you see that the focus is elongated and changes if you use a focus. And then there's a technique to shape the focus by, for example, using a slit aperture. This has been suggested by people in 2005, and we have done this, as was shown here in that video. I think now the video has sort of changed a little bit, but here you see again that the shape is now very well and better as before. So here is an example that we have now such a structure, and this is our structure for the elongated lattice, and here you see that the lattice voxel is almost two-dimensional so that you can have a symmetric structure. So here's one of the results. Here is a leap lattice we have created, and you see that the leap lattice unit cell is here, and this is a periodic structure. And then we can look how light propagates into it. And here you see experiment and numerics, and you see that first we have regular diffraction, and then you see a conical diffraction, which also is nicely represented. But because we have this pseudospin, now we can address here with our entrance field certain directions of spin by changing the phase of the input light beams to the certain to the Brillouin zone. And then we see that we have also here the possibility to have a pseudospin 1, which changes its conical diffraction, especially in the center, so we can identify that we can really have pseudospin in these leap lattices. Now I want to go a little bit further, because leap lattices are very nice, but they cannot be optically tailored and adapted. And this concept of adapting structures in a way to get a special Brillouin zone and a special features is now a very hot topic. And what we did here is creating a leap structure that has a certain configurations like that. So it has 4 unit cells compared to 3 in the real leap lattice, and the Brillouin zone is an elongated zone, and so this is a sort of square diamond-like structure. Overall, it has a slightly hexagonal structure, so it's a sort of graphene leap lattice modification, and that is very helpful in order to look at its lattice Brillouin zones. And this can be seen if you look here, for example, at this infinite lattice, and here in this sketch you see how now the Brillouin zone look like. And you see different things. On the one hand, you see that we have here again diabolic points, Dirac points that are available, but also you see that we have sometimes flat bands in between, and these flat bands with the 4 different bands here are, for example, tilted. So we have very exciting properties in that structure. We have diabolic points, but at the same time we have flat bands. Here you see, for example, diabolic points between different planes of the 4 bands. And so we have a variety of different features in one material. What we now want to have a look at if there's topological insulation. And if you look at that, we see that topological insulation can take place if you take a unit cell that is somehow elongated and quasi 1D. And if you look at this, we see such a band structure. And for topological insulation, we would expect that there is a state that on the surface has, for example, light propagation, but in the center has not. And these edge states would appear in the bulk bands. And we have to look at that a little bit more.
You have 2 minutes, madam.
Okay, so I will go a little bit quicker through that. So we can see here that we had at different positions, we have different situations of the light propagation. And this light propagation at one of these parts here is isolated, so we have only light propagation at the edges, which would be such an edge state. So edge modes in the center could be those that create topological insulation. However, if you want to excite them, particularly, we need to have other features. Here you see again the edge state compared, for example, to a bulk state. And what are the different features that can be realized by having different edge states? But we need to break symmetry. And we can break symmetry, let me show that, by having a time periodic structure. And here you see the change. If we start to have a time periodic behavior in the system, you see that there's an opening, and here we get the situation that we now have a symmetry breaking in the band gap. And this Floquet ansatz then brings us to the idea that we can realize topological insulation at these places. This is connected to a group velocity that is 0 at this part, and we looked at the Chern number and see that also the Chern number in these cases changes, which is a clear indication of a topological phase. And let me show that we have realized that by making these structures, for example here, by making time reversal and helical structures. And if the structures are flat, as you see here, we have isolation on the edges, but no topological movement. But if we now have a structure that is circulating, we see here that the 2 edges, the signal on the edges is rotating, and so we have really a topological insulator that propagates lights on the edges. And with that, let me finish. I wanted to show you that with optics we can realize photonic graphene, and that has many interesting features. We have realized bilayer graphene and have shown that we can twist with different angles and get a twistonics in photonics. And also I wanted to show you that special tailoring of lattices leads to certain structures like the Lieb lattice with a very rich band structure, and in this rich band structure you can create by optics topological insulation in a much more variety than in photonics, than in condensed matter physics. And with that, thank you very much for your attention, and I'm happy to answer questions.
Thank you very much. It's a very interesting talk. If there are any questions, I can allow 1 or 2 questions from the participants. You can also give the questions in the chat box.
Yes,
yeah.
I have to look and see if I see the chat. Yes.
No, chat box is empty. Yeah, now. So, any questions?
I have a question, Adam. I have a question. I'm sorry, I didn't put in the chat box.
No problem.
Myself is the next speaker, and very interesting talk. Just to ask you, do you require a special? Are you strictly? I mean, you require a special. How you do this optics in the graphene, because it is always on a substrate.
That's I know. Here you take a material. You can take either, for example, you take for this femtosecond laser writing. For this, you take just like a normal flat surface, can be glass, for example, where you write the refractive index with high power lasers. Or for the other perspective, for example, for the twisted bilayer graphene, we take so-called photorefractive materials where the refractive index is changed by a nonlinear optical process. So this is, for example, lithium niobate you can take as a material. So it's typical, let's say, transparent materials whereby light you change the refractive index. And that the techniques are there. It's more what you do with this change of refractive index. And here we create this sort of solid state structures with it.
Thank you very much.
You're welcome.
Are there any more questions? If there are no questions, we can tag the speaker and we will move on to the next speaker.
Thank you.
Thank you very much. Thank you very much. Yeah. Okay. Now the second invited speaker is by Dr. Sandeep Dara. He is going to give a talk on localized plasmon-assisted nanospectroscopy and nanoscopy. He is working in Surface and Nanoscience Division of Indira Gandhi Center for Atomic Research, Homi Bhabha National Institute, Kalpakkam, Tamil Nadu, India. About him, the Professor Sandeep Dara has completed his Masters in Physics from IIT Kharagpur in the year 1989. He finished his PhD from National Physical Laboratory, New Delhi in the year 1994 and joined IGCAR, which is Indira Gandhi Center for Atomic Research, IGCAR, in the year 1996. He is a Fellow of Royal Society of Chemistry. Presently, he is the head of the Surface and Nanoscience Division, Indira Gandhi Center for Atomic Research, Kalpakkam, and Professor Homi Bhabha National Institute. He was also visiting professor in University of Valencia, Spain, Technical University of Chemnitz, Germany, and Institute of Atomic and Molecular Sciences, Academia Sinica, Taiwan, these places. He was associate professor in Electrical Engineering Department, National Cheng Kung University, Taiwan, during 2007 and 2008. Dr. Dara has published more than 300 research publications, which include several review articles and 2 books chapters with several conference presentations. He has delivered more than 100 invited and plenary talks. He is a recipient of DAE SRC Outstanding Research Award in 2012. He is also in the editorial board of a number of national and international scientific journals. Dr. Dhara is specialized in studies of light-matter interaction in the field of near-field scanning, optical microscopy, and tip-enhanced Raman spectroscopy. At present, he is involved in several national and international collaborative programs. With this introduction, I invite Professor Dhara to deliver his talk. Welcome, sir.
Thank you very much, Professor Senthil Kumaran, and also for giving me the opportunity for speaking to the august audience of me. So this is now I'll be switching over to the very advanced applications of photonics to plasmonics. I hope that I can keep the standard, which is very difficult to keep, but nevertheless, this is my team. This is my team of who has contributed indirectly or indirectly in this the subject which we'll be covering. Most of them are students, and I'll be covering, if I can recall, probably I'll be covering the subject of Santanu, Kishore, Shivadashan, Avinash, and Prasanna Sahu. Prasanna Sahu is in presently faculty at IIT Kharagpur. So my aim of the talk will be just giving me introduction of subdiffraction, which this audience don't require, but just to mention, just to flash, and then the plasmonics, where we require the evanescent wave, where also we don't read much of the introduction, but still I'll just give a quick definition, and then I'll be speaking two different things, as it is evident from the talk. The nanoscopy, which is actually a smarter version of the word microscopy, because you now start seeing sub-micron structure, few nanometer structure, even for that matter, sub-nanometer structure using light. So that's why it is conveniently or confidently can be called as a nanoscopy. And then it is nanospectroscopy. Nanospectroscopy is about you have to do spectroscopy. So here molecular spectroscopy strictly means the Raman spectroscopy we'll be using. One can use other spectroscopy also, near field spectroscopy also. So I'll be talking mostly about the TARS. So your nanoscopy, and then nanoscopy I'll cover the near field optical imaging, and I'll be talking of the coupled plasma and polariton system. Plasma and phonon polariton system, and then I'll be talking TARS. Mostly I'll be talking in the I'll be talking on the silicon nanowire. We have given a proper definition of the broadening in silicon. Probably, as you know, it is one of the most open question for last 50 to 60 years. And then I'll be touch upon the 2D layer heterojunction, which is actually the contribution of Prasanna Sahu through his paper. Diffraction limit, that means the Abbe's, according to the definition, you can't focus light below lambda by 2 typically if you consider your refractive index to be to the power almost 1. And then you cannot go, light cannot pass strictly through a hole by lambda by 2 in its conventional way. And as you know that we are using different optics, so for different reasons, I've just given the typical calculations that if you use a typical available numerical aperture of 0.5 and use 325 nanometer light, you can see your 320. You can only see in principle 320 nanometer structures, and if you take a typically 0.9 numerical aperture and use 514 0.5, that means argon laser, then you can at the most can resolute 285 nanometer, but we'll be talking of nanostructures far one order below than this. So that I know basically the photonics, whatever you have seen earlier and whatever you are I'm going to discuss here, the plasmonics is both one common phenomena that's called confinement of light. And most of the phenomena, exotic phenomena, comes because of the, or nonlinear phenomena comes because of this confinement of light. And now there is a combined technique. As you know, the plasmonics is exhibited mostly by the metal nanoparticles, and that has a strong extinction coefficient. That has a strong scattering effect. So you lose most of the light, so you cannot really analyze at the depth. Whereas if you use photonics, then or the cavity or some kind of other confinement like cavity-related confinement, then you can use the light to propagate further and can analyze the greater depth. So if you can combine these two, that means nowadays there is, of course, the hybrid systems are going on, and then you can see now that when metal is being replaced by wide bandgap material, heavily doped wide bandgap material, which has low loss, at the same time very high electron density, to so exhibit the most of the confinement effect, which is desirable. So that's what plasmonics. So you have the conduction electron resonating with the exciting wavelength when the nanostructures are very small. And as you know, this same plasmon wave can propagate along the interface of the dielectric metal interface perpendicular to it. But this wave is basically called the evanescent wave, and it does not propagate further. It's 10 to 20 nanometer typically. But the beauty of this wave is that it interacts with the molecule. The interaction is short range, but finally the dipole moment, dipole moment carrying the information can be observed in the far field. So that's one way good that do most of the spectroscopy or so-called nanoscopy by collecting light at far end, even meters away. So that's the advantage of the whole field. And as you know that if you use a plasmonics, how the light line goes. Light line is normally the dispersion of the light. If you see that group velocity, the light is propagating normally for the say 500 nanometer light is propagating in normal conditions in omega k relationship like that. But once you introduce it in a hole, through a hole, strictly through aperture, which is equivalent or smaller, slightly smaller than the wavelength of the light, then you can make the light slow, keeping its momentum conserved, and then you can see the light is going, wavelength is increasing, and wavelength is decreasing. And then if you use the metal nanoparticles, then you can confine the light further. That means if you use one layer of the metal nanoparticles, then you can confine it further to make it a super lens. You can go 70 nanometer or even low if you have a specific condition that will be talking it. This typically the evanescent wave, you can see it when this very small aperture corresponding to the wavelength, and you can see a light. Light is no more a normal propagating light, it is a evanescent wave. And this is why first was used Aaron Lewis. It is quite an uncommon name, but he is one of the, I always say this, he is the discoverer of the ensom, and because he first saw the light through a hole much before the Epson did. Epson is around 2000. He is in 1984. He first showed one layer of PMMA and metal over silicon. You can control very small aperture of 330 nanometer and can pass the light easily. So that's the physics, that's the mathematics of it, how you can really go lambda by 2 to lambda by 4 pi easily, just exploiting its momentum part. And as you know that once you use the gold layer, you can the confinement of the light is confinement can be effectively used of the gold plasmonics. You can focus the light and can focus into a, if you make a gold cavity made of gold nanoparticles, you can even make a, or silver silver or gold, you can easily focus light down to few less than a micron. So that means you can, in principle, you can start writing in an object which is optical recording for that purpose. You can start recording in a smaller grain. That means you can, areal density in a optical recording goes very high, and that's how you can get a DVD or those kind of phenomena. And then, as you know, as I told you that this plasmonic wave can also propagate in the metal dielectric interface, and this is called SPP, and that has been first demonstrated in a graphene very successfully, that you see those waveforms in a very light layer of graphene being very light, and one atomic one atomic layer, it can propagate easily and it can be observed. We will show it in our case in case of a regenerate semiconductor like indium nitride. And then, as I told you, that the light can be confined with the metal nanoparticle, but you can also combine this technique. That's what I was telling, how you can go to the sub-nanometer level. If you can combine this plasmonics, that means you can use a AFM tip and on which you can coat the gold or silver metal, then this become a guided plasmonic tip. And this guided plasmonic tip is a typical electromagnetic confinement around this tip, and this electromagnetic confinement can be easily studied. It can help you in getting the Raman spectroscopic advantage. Like you can get because Raman spectroscopy is a very quite weak phenomena, but if you can confine light, that you can get the scattering factor much high, and then you can eventually can study a single RNA for his own chemical information. I'm not going all in these details, and also it can be done for a single carbon nanotube, and also can understand the strain involved in a single carbon nanotube of diameter of less than a nanometer. So even industrial applications are there, as you know, the indium gallium nitride, doping indium in gallium nitride is one of the most technological issues. So if you want to make a laser lasing material of indium gallium nitride to analyze the material industrially, even for quick analysis of the indium doping level or any precipitation has occurred, you can do a quick mapping with the deep-enhanced Raman spectroscopy, and you can get an idea of whether the indium phase, precipitated phase is there, or you have a perfect indium gallium nitride phase. So that is typically done in the 35 nanometer, and I'll tell you what is the difficulties in gallium nitride. 30 nanometer may not be very impressive, but it is one of the most difficult jobs. And final thing one can dream of, nanometer imaging of a single molecule, but you have to do at low temperature and in a specific condition. So that's the typical equipment we have developed, and we have used this for AFM tip attached to the light, the spectrometer here by telescopic arrangement, and this tip we can do both nanoscopy and also can do the spectroscopy, depending on the. In one case, we use optical fiber for nanoscopy, where you can do the near field spectroscopy, and light is collected here by a single photon detector. But in other case, we can send the light through a telescopic arrangement to the spectrometer to find out the. As I told you, that it can be meters away for the. Can do the meter away. So with this, I will go straight to the subject. As I know, as you told in one of the paper, we have shown how we can really resolve in the near field spectroscopy using 532 nanometer laser. Even one can, if we get eventually less than 5 nanometer. This is, you can understand, this is a topography, and this is a optical, is the AFM topography, 2D and 3D, and you can see this gold absorbs light 532 nanometer, so it's giving a black impression. So this is a image or the optical image of a gold nanoparticle. Of course, this is slightly bigger, 100 nanometer, 150 nanometer, but you can also always see that there are 10 nanometer structures are also there. So with this, then we observed for silicon indium nitride is a degenerate semiconductor. It has a large number of large amount of surface electron, and this surface electron we have used it, and indium nitride is a very controversial material, and that's how its band gap cannot because of the large content of the conduction, large accumulation of the conduction electron on the surface. And we can see that indium nitride, in case of indium nitride, we have seen the plasmonic wave. This is the ENSOM image, the near field scanning optical image. This is the typical topographical image for indium nitride clusters or the nanostructures. But when we start seeing optically, we see the ridges, and the ridges is allow the boundary of this. And once in a particular region, you can see that waves are interfering and making destructive interference. And this topographic wave is first seen in a non-degenerate semiconductor, a degenerate semiconductor like indium nitride, apart from graphene. This is a very vivid example how the wave propagates in case of a indium nitride. One can say that this is maybe the artifact of the indium nitride crystal. It is not so, because you can always see that there is black and white contrast even inside the boundary itself. And this is a typical image we have done when gallium nitride, which is one of the most difficult material because it's change of course, in this case, optical image. So you can see we have we would image even 10 nanometer. You see from the topo image, so even 10 nanometer gallium nitride nanowire we could image it. So with this, I don't know how much time I have. Okay, I think I have. So we have, as I described the system, and now we have used this technique. As you know, T-finance Raman spectroscopy is one of the most difficult experiment to do, and we struggled initially, and we of course made a gallium nitride nanostructures. This is a typical AFM image. We could not do very good spectroscopic image, but however, we solved the problem of magnesium doping in gallium nitride, where we try to locate the local vibrational mode introduced because of the magnesium being incorporated in the lattice. And we saw that uniform color is being shown along the nanowire, showing that there is a local vibration, that magnesium doping is successful in this material. However, eventually we improved our technique and we saw a gallium nitride nanowire. See, what is the problem on the 3 nitride? This gallium nitride, why I'm showing this example? If you see to the literature, whatever literature I've shown, except one case, it is all graphene or graphite or carbon nanotube. Carbon response to Raman scattering is enormous. So it is very easy to find even sub-nanometer, sub-nanometer carbon structure like a single wall carbon nanotube. But when it comes to the 3 nitride, which is one of the technologically important material, it is absolutely most difficult because its change of polarizability is almost negligible. And particularly in case of aluminum nitride, I show you. But in gallium nitride, it is same. It is the FIC, that fractional ionic component is quite low, quite high in this case. So there are more ionic than the covalent, and so that's how it's extremely difficult. Even there is no image so far except our image of gallium nitride nanostructures, gallium nitride, whatever you have seen earlier. Then that is of course with a lot of mathematics. Here it is no mathematics, simple spectroscopic data. We could image a sub 200 nanometer gallium nitride nanostructures by a Raman spectroscopy. So this is what I'm telling. This is just AFM image, no spectroscopic image. So that's how I was telling that even you can do a silicon nanowire of 60 nanometer here very successfully, but a 200 nanometer, this is a topographic image, remember. But when I'm giving these are a topographic 2D image, but when I'm trying to find out the spectroscopic image corresponding to silicon, you can get a very good image of topographic image of silicon. But in aluminum nitride, you don't hardly get any image. So that's very difficult to analyze. So this was understood properly and all those things. And now I'll come directly to the problem of silicon nanowire. As you know, the silicon is a very technologically important material. In the previous session, there are a lot of talk of silicon optics, fabrication on the silicon material as such for different modulators and all those things. Silicon, as you know, is very important. So silicon broadening in the Raman peak of silicon is a very well-known thing. There are many effect had been studied for over 50 to 60 years. They say it's a size effect. The size and safe effect has been studied. Then most of the important factor comes in the thermal effect, and then there is, as you know, the silicon. If you have a doped silicon, which is most of the case a device, then the Fano activity, that means the electronic contribution to the silicon Raman mode, also is normally assigned for those broadening. What I'm talking of the typical, this is a silicon nanowire commercially procured, and you see this is the typical. Since you have silicon nanowire, it is a typical peak. Not only there is a broadening, also there is a small peak shift, and it is of course in the ensemble of the ensemble system, and it is a bulk. If you see, this is the more or less a standard for any Raman. So you have a particular peak at 520. Yes.
Yeah, you have around 5 minutes, sir.
Okay, that's fine. So now you see that we can always find out two different lifetime for different if when you have a broadened peak, particularly for a ensemble measurements, and then we did the, as I showed you earlier, while showing the difficulties in the 3-nitrate system, and but in the covalent or covalent system, it is fairly simpler. Here it is a 16 nanometer nanowire is a spectroscopic image. Understand if this is the AFM image, it's corresponding spectroscopic image, and then if you this is a 3D image, and you see TARS is basically how it is done. As you know, I hope that everybody understood it. I'm going very fast. That every point you are collecting the spectrum, and this is a intensity map across the length and breadth. And while you are scanning, you are scanning also in the width. Superlensing phenomena. You had room temperature at least 10 nanometer, and you are assuming 60 nanometer nanowire. So at least 6 or more than 6 data has been collected in the lateral direction and the other direction. We have picked a few of them and we have analyzed it. And you see that if this data is collected for 1 second, their steps are different. If the data is collected for raw 10 seconds or 4 seconds across the a different point, so you have another lifetime incorporating in. That means your contributions are coming from other side. So what is the question? That is the and the what we did. Now we went for the lower, and then we picked up a 20 nanometer. I'll tell you why this is because there is a is a effect of a long time. If you do it, it is a fairly long. As I told you, across the sample you are doing it, there is some small temperature. We are working in the first floor, so those conditions are not there. But anyway, when I'm using, we have only taken this position of the spectral image. If you see, if it is 25, so it does not matter. The shape does not changes. That data is may not be here. Okay, 10-second data. This is 1 second collected, and this is a 10-second data. Understood that we have done the corresponding Kelvin probe microscopic analysis, and we found out that Fermi level, the Fermi level is shift position. Then we saw that 25 nanometer, actually below 20 nanometer, 25 nanometer, your normally silicon nanowire is completely fully depleted. That has been modeled out, and we found out that means there is no carrier level in 25 nanometer. So our conclusion was that presence of electron is the primary reason for broadening, which was there in the 60 nanometer nanowire. It is typically shown here. You have a typical depleted width, and it is completely low. So we solved this problem and was published in Nanolaters. And then I'll go. I think I know that I have no time, so I'll introduce a special material which has been published by Nature by Prasanna Shahu, my student. And that is a two-dimensional heterojunction. That means in a single pot technique, he can make 2D multi-layers continuously for few hundreds of microns. So then in this, you can basically make a single electron junction across the two dimensions, and it's strictly all monolayers. So now how to characterize it? You can go to TEM. It takes hell of time and costly. So you can you do it optically? Yeah, that's the question we have answered. Of course, he has taken the data from commercial things, but we have also answered it across the surface. If you do the deep-enhanced Raman spectroscopy, so this is a typical boundary is shown by the arrow. This is another phase. This is another phase. And then you can see here WH2, MH2, WH2, MH2, and you do the deep-enhanced Raman spectroscopy or deep-enhanced photoluminescence measurements, and you can find out the different interfaces. And wherever the interfaces are not okay, then you can find out there is a break in the interfaces, and from that you can easily characterize as a device. And these materials are all device-grade material, of course, within the limit of the time of a 2D material. As you know, there are other issues of degradation of this material. So this is studied, and we have used the tryons and all those things. And so you have a large area MOS to 2D material has been grown, and we have also measured qualified the junction. And I think that's the conclusion of the study. Thank you.
Thank you, Professor Sandra. Are there any questions? Very nice. You can also post your questions in the chat box, or you can directly ask. Yeah. Chat box is empty. Yeah.
I'm not finding out anything.
Question is not.
Maybe I am not able to see this. It's okay. Questions.
Yeah. If there are no questions, we thank the speaker, and we will move on to the next invited speaker. Yeah.
Thank you very much.
Sir. Thank you, sir. Thank you very much. Now we will go to the third invited speaker in this session. He is Professor Senthil Murugan Ganapathy. He is from University of Southampton. Professor Senthil Murugan Ganapathy received a PhD in photonic materials in the year 2001 from Indian Institute of Science, Bangalore. He worked as a postdoctoral fellow from 2001 to 2005 at the University of Bordeaux, France, and the Toyota Technological Institute, Japan. He joined the Optoelectronics Research Center at the University of Southampton in April 2005, where he is currently a principal research fellow, equivalent to associate professor. His expertise and research interests range from photonic materials to photonic systems, with current focus on mid-IR, high contrast materials and devices for biomedical sensing, on-chip nanoscopy, environmental monitoring, and optical communication applications. He has made pioneering contributions in the field of novel optical microresonators. He has received research grant income over £1.5 million as principal investigator. He established and runs a major mid-IR characterization facility worth about £1 million, which is unique for wavelength spectroscopy in a 2 to 13 micrometer spectral region. He has published more than 230 journal and conference papers with a H index of 33, including more than 25 invited talks at major international conferences, 2 patents on new photonic glasses, and editor of a book, Photonic Glasses and Glass Ceramics. He is a recipient of the Dean's Award for 2012-2013 for outstanding contributions in teaching for MSc Photonic Technologies, teaching at the University of Southampton. He served as program chair of Young Scientists Forum in the international conference ICOOPMA 14 held in Leeds, United Kingdom. He is also the international advisory committee. He is also in the international advisory committee of the Biennial International Conference ICOOPMA. He is on the editorial boards of MDPI's Photonics and Electronics journals. He is fellow of the Higher Education Academy of United Kingdom. May I now invite Professor Senthil Murugan Ganapathy to deliver his invited talk.
Good afternoon, everyone who are in India, and thank you, Professor Senthil Kumaran, for a nice introduction. I would also like to thank Professors Joby Joseph and Neeraj Kar for inviting me to this conference. I'm very glad to be, of course, participating in this conference, but it's a shame that I can't be in Delhi in person, but hopefully I can join in the next conference. So thank you all for making this happen. And I can see that this conference is going very nicely online. Very good effort. Thanks for the organizers. Okay, coming to my talk, I will probably give you some time, few minutes for questions. So I would like to, give the presentation only for about 25 minutes, hopefully. I normally speak quite a lot, and I will try to make sure I reduce that. So today I would like to introduce one of the research strands I'm engaged with in Southampton on mid-IR spectroscopy. But today I would like to talk about a couple of things on mid-IR spectroscopy. One on the device aspect, and the next one on the application aspect. So we have been working on mid-IR spectroscopy for the last probably about 12 years or so, because for Southampton, when I came, I was working on mainly micro resonators, but then I started developing interest on mid-IR spectroscopy because I'm basically from materials background. So that's then about 10 years back, the mid-IR spectroscopy had revived interest. So yeah, I also thank the other students and my colleagues who are contributing to this work. As an outline, I would first like to give a very brief introduction, and then I will start to talk about part one, which is spectrometer on chip, and part two on the diagnostic application. In both parts, I will initially start with the motivation and state of the art, and in each part, I will go through the basic design principle, for example, in spectrometer, and then an example potential application in the diagnostic application. Likewise, I will give you some preliminary results we have got in both the parts. Finally, I will summarize my talk. So just to give you an idea of why mid-IR spectroscopy is important, in the in the electromagnetic spectrum, this region from 2 to 20 micron, well, it varies. Somebody say 2 to 50 micron is mid-IR, somebody say 2 to 20 micron. It depends whether you are a physicist or a chemist or engineer. Engineers call, or in industry, it's mid-wave IR from say 2 to 5 and long wave IR from 7 to 12. So it varies, but in general, this mid-IR region has got very good information from molecules. That is, they capture the fingerprint absorption. That means this molecular selectivity can be used for detecting, for sensing without any labels. So this is the main attraction of mid-IR spectroscopy, and it's got huge potential in diagnostic application, in environmental monitoring, anything to do with sensing detection. You can always go for mid-IR spectroscopy. Of course, there are some limitations on the materials and the devices. This is what we have taken as a challenge, to develop new platform as well as showing you the potential application on the biodiagnostic side. Let me first talk about the spectrometer on chip. So the motivation here is that, okay, mid-IR spectroscopy has been done using FTIR for so many decades, so there is nothing new about it. But if you take a normal FTIR spectrometer, if you use cuvette, for example, you need large sample volume. That means your light has to go through a longer path. And that means your analytes are dispersed in a medium, for example, water. If it is the biodiagnostics, our body fluids are mostly water, then it has to go through all the water absorption. That means you will lose the actual signal from the analytes. For that purpose, FTIR has been combined with ATR, that is attenuated total reflection crystals, which has few bounces. At those bounces of the light, you produce evanescent field, and that is useful to interrogate with the analytes. So that way you are not going through the bulk of the liquid, so you are only sampling at the surface. So this kind of eliminate that water problem or the medium absorption problem, but then it's got only few bounces, and then again the interaction length is quite short. That's not useful. On the other hand, if you consider waveguides, they have maximum bounce density, or you can consider that as a, you know, an optical element of continuous evanescent field. So that way, you now get rid of the medium absorption, as well as you now get more interrogation with the analytes when the light is passing through the waveguide. So that way, the evanescent wave spectroscopy is quite useful. And that is also coming with the advantage of improved detection, and you need very less sample volume. All these benefits are added to that. So when waveguides are useful in that way, then it's always useful to combine the sensing element with also a spectrometer based on waveguides, so that it's miniaturized. You can move out of the lab, because the normal FTIR spectrometer is quite huge. So if we can have a miniaturized waveguide based spectrometer, then you can, go to remote places, or you can have it in the clinician's point of care place, or in a bedside environment. So that way, this particular work is so important, and also it's cost effective, because waveguides are mass manufacturable. So if you manufacture more, the per unit cost is less. So this is the motivation, and the miniaturized spectrometers are still not very common. It's not commonly available off the shelf, especially the broader bandwidth ones. So having said that, there are already demonstrations of tunable spectrometers, chip-based or miniaturized. For example, based on SOI, lithium niobate, or MEMS-based. But each of them have their own limitation. For example, SOI has got silica. Silica does not transmit above 3.5 micron. So that means you are limited to go to the longer wavelengths. Similarly, lithium niobate can work only up to 5 micron. MEMS-based devices are not, having the waves propagating in the material, but still, they are based on, mechanical movements. Then they have limitations with the mechanical tilting, and it's a complicated design, things like that. So having all this in mind, we have recently developed a new platform based on three-phase semiconductor. Three-phase semiconductors are not new, but this combination we have chosen is quite new. And as you can see, this material combination can transmit light from 1 micron up to 16 micron. So it covers the whole mid-IR spectral range, and the optical loss is very less, 0.5 dBs per centimeter at 1550. So you would hope when you go to longer wavelength, the loss further comes down. And we are going to use this as a thermo-optically tuned spectrometer. Therefore, their thermal conductivity and thermo-optic coefficients are quite useful and better than many other semiconductors. So we have chosen this particular waveguide platform, and then which is novel. This combination is novel in this field. To start with, because we are starting with a new material platform, so we have to start walking before running. So we have started with a simple configuration of a spectrometer. Just to give you a note that what I'm presenting is only the modeling results currently, but we have started fabricating. I will show you some preliminary results on the fabricated experimental measurements, but currently we are talking about only the modeling. So we started modeling a simple spectrometer, which has got, of course, it should have a source and then a sensing region. But what we are now worried about is the spectrometer part, which is highlighted here in this box. So it has got two different arms, two different spiral arms forming a Mach-Zehnder interferometer. And then in one of the arm, we are providing heat so that that particular arm is introduced with refractive index change through thermo-optic coefficient. So when the light comes out, you have an interference pattern, which you can again further do Fourier transform to get back to the source spectrum added with the absorption of the sample. So this is what is the aim, and then the device specifications we have taken are here. So we would like to cover 3 to 4 micron wavelength. You may wonder, okay, this is going to be replacing the SOI or lithium niobate, which has limitation up to 5 micron, then why 3 to 4? Of course, as I said, we have to start with like a simple modeling. If it works at 3 to 4, of course, it will work up to 16 micron. And as you will see from the measurement we have done, the loss is coming down. But the initial fabrication needs to be simple, because if you go to the longer wavelength, you need to grow thicker layers. So we were starting 3 to 4 as a proof of principle, and therefore the modeling results I show is only from 3 to 4. For modeling, it doesn't matter whether it's 3 to 4 or 10 to 12. But this is, as I said, it's a proof of principle. Then for that, we establish the single mode condition at 3 micron, because if it is single mode at 3 micron, it will be obviously single mode at 4 micron. And then we also model the cladding thickness needed to reduce the loss. And these are the set parameters. That is, we target 10 wave number resolution. For that, we need 1 millimeter optical path length difference. That requires 500 pi shifts at 4 micron wavelength, and that gives us a 6 centimeter spiral overall length, and the temperature excursion needed is about 84 Kelvin. So that's what it is. And then, so I'm going to show you two types of modeling results. One is on the optical structure, and the other one is the thermal modeling. So optical modeling was done using numerical, and COMSOL is performed using, thermal modeling was used using COMSOL. I'm just conscious of time. I was looking, so I already crossed 15 minutes. Okay, so here we establish a single mode condition for the particular layer structure. We have taken a thickness of 1.5 micron gallium arsenide layer, and we ran a simulation with waveguide width varying, and we found that below 1.6 micron width, they are single mode. As you can see, why it is important, because here I'm showing you the single mode condition as well as multi-mode condition with zero phase shift and pi phase shift. You can see that with pi phase shift, it's nicely, properly, destructively interfering, whereas in the multi-mode case, even at pi phase shift, you still get some light out, which is not useful. So single mode condition is quite important. And there are two types of loss in any structure. The first loss is due to the absorption of the material, and the absorption can happen in two ways. One, because of the nickel heater on top, and two, because of the high index substrate. And then the second category loss is due to the bend, especially those within the interior of this spiral. Of course, for the modeling, we have not taken into account the propagation loss due to the fabrication. We have taken into account the material loss and the bend loss, but not the fabrication, because that's variable. Okay, so the metallic heater loss we calculated into polarization T and TM. As you can see, TE gives rise to 0.06 dBs per centimeter at 5 micron upper cladding and 5 micron lower cladding thickness, whereas TM gives huge loss. You may see that, visualize this here, because by the nature of the polarization, TM is extended to the the nickel heater, therefore it's quite lossy. And the second category, bend loss, we have also calculated, and we found that for a bend radius of about 200 micrometer, that's a 180 degree bend, we get loss of about 0.1. Well, it is quite a bit bigger compared to SOI because of the contrast we have is only 0.26. Therefore, the total loss for our whole device is the combination of these two categories. So we have 0.06 dBs per centimeter, and totally we have 6 centimeter. Therefore, it's 0.36 plus 2 bends 0.2. Therefore, on average, you would expect for the whole structure only 0.6 dB loss. As I said, the thermal modeling was done using COMSOL. For the thermal modeling, as you can see, this is the active spiral which has the nickel heater on top. This is what we are modeling. We are not showing the other arm, but this is a little bit offset to reduce the thermal crosstalk. So that is the periphery of the other spiral. And as you can see, there is a detector we put here. That is what is measuring the temperature to measure the crosstalk. And we have used two different conditions for the bottom surface. One is thermally insulated, and the other one is placed on a heat sink. So the heat sink will constantly radiate the heat. So the thermally insulated one and the heat sink both were going up to 88.5 Kelvin in this particular, the temperature rise, not the absolute temperature. In two cases, with a rise time of 12 and 10 milliseconds. So you will see that in a thermally insulated case, the power needed to go to this 88.5 Kelvin is only 26 watts, whereas it's 41 watts in heat sink, because the heat sink case, it's constantly radiating, so you have to keep heating. Whereas on the other hand, the crosstalk is better, much less in the heat sink case, because before it's reaching the other arm, it's getting radiated out. So there's a balance. So it depends on, whether you want to reduce the energy consumption, or you want to reduce the crosstalk to have a better performed spectrometer. Okay, anyway, so as I said, the whole device fabrication in progress in Sheffield, but we have already fabricated the waveguide, the straight waveguides, and have characterized using the mid-IR waveguide characterization setup we have in-house, with equipped with all the mid-IR optics as well as mid-IR thermal imaging camera sources running from, as Professor Senthil Kumar said, from 2 micron up to 13 micron. But we have initially characterized a few different wavelengths. As you can see, we characterize these waveguides at 3.5 micron. You will see a very good light in output at the end of the waveguide, and from the streak of light, we have measured the loss, which is about 2.5 dBs per centimeter. But mind, this is the very first fabrication run, so we would certainly get much better transmission or lower loss. But you will see that at 7.7 and 8.3 micron also it's guiding, and you see the actual loss, the measured loss is only half a dB per centimeter, which is encouraging, right? So we estimated at 4 micron or 3 micron about 0.6 dB total loss. So this is quite encouraging. So this material platform is having potential to be useful in longer wavelengths. So with that, I end my first part, and then, well, probably I will take another 5 minutes to explain you some of the potential application this mid-IR spectroscopy is having in medical. Yeah. Okay. So the motivation here is that very often, the clinicians are depending on the clinical, medical diagnostics to give you a good treatment. But very often they don't have such quick diagnostic information, and some health conditions require very quick diagnostic result, and you need to have probably preferably a rapid bedside diagnostics. One such condition is neonatal respiratory distress syndrome, which is quite common in prematurely born infants. When they born prematurely, they suffer from lung immaturity. Their lung is not prepared to breathe normally. Therefore, they have huge issues breathing. Therefore, we have to the clinicians have to decide whether they need to be treated artificially with surfactants or ventilators. Well, the ventilators we have been hearing quite commonly now because of COVID-19, but this has been used for infants also. But currently there are no treatments. Sorry, there are no diagnostic method to give you this the treatment decision. Therefore, we have chosen this as an application, and there are lots of biomarkers, but the two main biomarkers for this symptom is lecithin and sphingomyelin. And the ratio of this sphingomyelin to lecithin to sphingomyelin gives you an indication of whether they are requiring treatment or not. They are deficient of surfactant or not. So LS ratio, the lecithin to sphingomyelin ratio of less than 2.2 says that yes, this particular infant needs treatment. There are methods like mass spectrometry, chromatography, but it's time consuming. You need to prepare the sample and you need highly skilled personnel. So you get the result out only after half a day or 1 day. So it's not useful. On the other hand, mid-IR spectrometry is quick, easy, and you can get this result less than 10 minutes. Just to show you the molecular structure, there is sphingomyelin, and there are lots of functional groups and fingerprint absorption. We are interested in amide-1 at 1645 wave number. Similarly, DPPC, we are interested in 1735. I'll show you how this is useful. So we have done a serial dilution of sphingomyelin from 0.01 millimolar to 10 millimolar, and you see various bands, and we have assigned them here. Similarly for DPPC. So now comes our actual ratioed measurement. So we have taken 1 millimolar sphingomyelin in a ATR FTIR to start with before we put it on our spectrometer on chip. So you can see we increase the concentration of lecithin. So that forms a ratio of 1 to 3.4. And you can see nicely that the DPPC, when it is increasing in the ratio, it's quite nicely increasing here. So based on this, we have used automatic curve fitting on so many different spectral processing and used the peak height and area to ascertain the ratio. As you can see, we are still working on the post-processing. The peak area is still a bit all over the place, but the peak height based estimation is quite clear. We have been doing at least 3 measurements on each ratio, and you can see a nice curve established, which gives almost exact ratio detected for the ratio applied. So this gives us the confidence that mid-IR spectroscopy, of course, with our improved waveguide platform will be much better, but even currently with ATR, it gives a nice indication of whether or not an infant need treatment, like prematurely born infant need treatment. So with that, I will summarize my talk. So I have given you kind of preliminary result on 2 aspects. One on the spectrometer on chip with a new platform based on 3.5 semiconductor, as well as I have given you an overview of application specifically for NRDS. And we can confidently say that mid-IR spectroscopy will be really useful to alleviate lots of pain in many infants. With this, I will complete, and I acknowledge my colleagues who helped in both parts on the fabrication side from the University of Sheffield 3.5 Semiconductor Center, the UK national facility, and also thank Professor Howard Clark as well as doctors. in University College London Hospital in London, and also Tony Postle and my students and postdocs and collaborators. And I gratefully thank the funding received from Engineering and Physical Sciences Research Council. Thank you very much. I'm very glad to take few questions if time permits. Thank you, Chair.
Yeah, we have time for a few questions. Yeah. Any questions from the audience? I have one question I can ask if there are no any other questions.
Please.
Professor Senthil Murugan, you have mentioned on your chip, you have shown the Mexander setup.
Yeah.
Where the spiraling of the fibers I could see. So you talked about the bending losses in that when you are bending into a very curvature when you are changing it, But there is also accompanied to that there will be the polarization also gets disturbed, the launching. So
true.
Both the arms may have end up with a different polarization changes. So how do you tackle
There is
that?
always a minor component introduced when it is going through the bends, but we have made sure the bends are quite large enough. So in our, even though I have chosen 200 micrometer for the modeling, our fabricated structures are 350 micron in radius of curvature. Now, it is a good point. There will be added loss. As we have seen, TM is quite nasty with loss. But yeah, you are right. There will be some added loss, but we have to minimize by increasing the curvature. Thank you.
Okay. Are there any other questions? Let me check in the chat box. It's also empty. If there are no questions, further questions, we can thank the speaker. Thank you very much, sir.
Thank you very much, Chair and the organizers. Thank you.
Thank you. Thank you very much. Now we are having one oral presentation by Mr. Kamal Lohani from SSPL Laboratory, New Delhi. And the title of the presentation is Effect of NaAU and PdAU peak contacts on optical performance of indium gallium nitride and GaN MQW edge emitting. May I now invite Mr. Kamal Lohani to make the presentation. 15 minutes, please. Stick to 10 plus 5. 10 minutes for presentation, 5 minutes if there are any questions. Please.
Right, sir. Right. Sir, am I audible?
Yeah, sure. We can hear you.
Yeah. Good afternoon, sir. Good afternoon, audience. Myself, Kamal Lohani from Solid State Physics Laboratory, Delhi, and I'm presenting on effect of nickel gold and palladium gold pre-contacts on optical performance of InGaN multi-quantum edge emitting laser diodes. Semiconductor-based photonic devices are being used in various applications. One of the excellent example is semiconductor laser, which is being used in various applications like healthcare, space, and military applications. The wavelength range starts from around 300 nanometer to micrometer ranges, and if we include quantum cascade lasers, it covers the terahertz range. In case of conventional semiconductor lasers, the emission wavelength depends upon the active layer direct semiconductor bandgap. With modern technology of bandgap engineering, precise wavelength can be achieved by tailoring the bandgap with different alloy compositions. With the tremendous progress in the long wavelengths, for example, in case of high power, we have already achieved 20-25 watts from single emitter laser diodes. Now the trend is also towards ultraviolet blue-green lasers, where gallium nitride is the material system. It's shown in this diagram also. The gallium nitride is a direct bandgap material with bandgap of around 3.42 electron volt, and its alloy compositions can be made with aluminum and indium with the edges of 0.7 electron volt and 6.4 electron volt. So it can cover the blue-green region, that is the 400 to 530, 550 nanometer region. Except this zinc selenide and cadmium zinc selenide may also be used, and earlier research was carried out for development of blue-green using these materials, and but due to the shorter lifetime, these materials could not be used further. This material has a few issues. Gallium nitride has have few issues, like growth issues, because you have to have a compatible substrate. For example, initially you have sapphire substrate on which you grow gallium nitride, but it has lattice mismatch, which may lead to defect generation. Right now, the substrates, the bulk gallium nitride substrates are available. So you have very low lattice mismatch with the L-GaN and N-GaN, and you can have defect-free layers. Just for the introduction, the edge emitter lasers are lasers having epilayer structure on bulk substrates, as shown in this first diagram, which have substrate, then cladding layers, active layers, and presentation shared. Sir, excuse me. Hello. Hello.
Yeah, okay, unmute. Okay. You need to share your slide. Share. Slide should be shared. There must be a button on your screen. Share button. Third on the bottom row. You can see that. Yeah. Yes.
Sir, is it there?
Yeah, you are in the which slide? Fourth slide, right?
Yes, sir.
Okay, because you are not shown the earlier slides, you can anyway go through them once more. I can give you 2 more extra because there are no more speakers after you.
Okay,
So
okay, sir. Okay.
you can go
Okay,
through
sir.
the 2 slides faster because you are
Yeah.
only fourth slide now. Yeah. Yeah.
Right, right. Just I have shown, sir, on the first slide, this diagram where gallium nitride could be used for blue-green lasers because of its direct band gap and having the emission wavelength in the region around 400-500 nanometers, with the band gap tailoring from 3.42 to 6.4 and 0.7 electron volt. You can have from blue-green to near IR region. So I will be discussing on edge emitting laser. Otherwise, other type is vertical surface cavity emission laser, where the cavity is perpendicular to the substrate. And in case of this edge emitting laser, you have the cavity formed parallel to the substrate. So the basic processes which are there in lasers for the radiative emission: spontaneous emission, absorption, and stimulated emission. And in case of laser, when stimulated emission dominates over absorption and spontaneous emission, you achieve lasing. So as shown in this figure, there is a substrate over which multiple epi layers have been grown by metal organic chemical vapor deposition. In this, you have a quantum well layer where light is generated, and which is sandwiched between 2 waveguide layers, because the quantum well is so thin that light should be guided within some active volume material. So waveguides are grown. Then you have cladding layer to guide the light, and finally a top contact layer to have the ohmic contacts on p side. The substrate, when grown, is fabricated for lasers by lithography, surface passivation, ohmic contacts, etc. And finally, naturally, cleaved facets are formed. These are the facets, and light is emitted from these edge emitting laser. The minimum current from where you achieve lasing, that is called threshold current. So this is just for the introduction. In case of gallium nitride, we have few issues like spontaneous polarization because of the difference in the electronegativity of gallium and nitrogen atoms. So inbuilt spontaneous polarization is there. And when you grow the InGaN or AlGaN layers over gallium nitride, you have some lattice mismatch which lead to piezoelectric polarization, and this lead to an inbuilt electric field which due to which there is a band bending and there is a separation of charges, which ultimately reduce the radiative recombination efficiency. Why I'm talking of gallium nitride lasers is because of its application in underwater communication or underwater applications, and the civil applications like welding of the materials, because of, as shown in this figure, that the absorption is lowest in case of 400, 500 nanometer wavelength. So this wavelength can be easily transmit through water, and the absorptivity in the metals is maximum near 400 nanometer. That means that if you want precise welding, then these blue near blue wavelengths can be used effectively. So that's why we go towards gallium nitride lasers. We have simulated in this direction. We have simulated the laser structure just shown here in this table. So this was simulated using Crosslight's Pix 3D software. The numerical simulations have been carried out, and we have estimated the threshold current density and slope efficiency with the increasing number of quantum wells, and found that with increasing number of quantum wells, there is an optimization where 2 or 3 number of quantum wells, we have a minimum threshold current. The trend is this one, and we have a maximum slope efficiency. Similarly, we have also simulated for electron blocking layer because in gallium nitride the p mobility is quite low. So when we have current injection, the carriers can accumulate at one side. So what we want to do is the fast moving electrons, we want to block them. So we have one electron blocking layer. So we try to optimize this electron blocking layer for aluminum compositions, and found that around 0.1 composition we have the minimum threshold current and maximum slope efficiency. The reason behind this is when we increase the number of quantum wells for the first this figure, when we increase the number of quantum wells, what we found is there is reduction in spatial overlap of electron and hole carriers, as seen in this figure. That electron, for example, for this, for one for this 3 quantum well structure, we can found that the third quantum well, the spatial overlap is quite low. That means that with the increasing number of quantum wells, the quantum well can be act as a parasite. So we have simulated and optimized for 2 and 3 quantum wells. The structure was grown and characterized. From XRD, it is clear that the structure was good in quality, as the experimental and the simulated XRD curves are matching. Then we have reactive ion etching to make the mesa or the ridge over this substrate. We optimize this RI process, and finally fabricated the laser device, as seen in the last SEM, the SEM figure. Then we have the thinning of this material. It is quite difficult because of the fact that this has hexagonal geometry, and if you want to thin down this gallium nitride, it can break towards its natural planes, M plane or A plane. So we have thinned down this material and finally polished it, and then cleaved this using the scriber to make the laser device. So around 12 nanometer of facet roughness has been achieved, which is good for making a laser. As can be seen in the last one, that blue lasing action have been achieved, and the conversion from LED to lasing action at around 4 ampere of threshold current. One of the challenging issue in case of ohmic, in case of gallium nitride is formation of ohmic contacts. In addition to the various other issues like facet coating or material quality or cleavage planes, etc. So P contact plays a major role in having high power lasers because of the if this ohmic contact resistance is high, then you have very high joule heating, which may lead to high threshold current, and finally non-lasing of the device. So why this was challenging is we make the contact by using either by work function definitions, like for P contacts we should have the work function of metal larger than semiconductor work function, or we can have a highly doped contact layer so that a tunneling contact can be made, as can be seen in these two figures. So with the requirement of contacts, as the contact resistance should be low, thermally stable, and should have better morphology and the process compatibility. In case of gallium nitride, already the band gap is high, 3.42. The electronegativity is also high, 4.1. So we have to overcome around 7.3 electron volt difference. So the maximum the work function metal available is around 4.5 or 5 electron volts. So we had used nickel and palladium, which has high work function as P only contacts. So mostly the contacts can be made only by highly doped contact layer or the tunneling contacts in case of PGAN because of non-availability of high work function metals. Now the issue is in making the tunneling contacts, we should have highly doped contact layer. But for gallium nitride, when you have a doping for making the carrier concentration high, you have hydrogen passivation of acceptors, and the P mobility of the carrier mobility of the holes is already very low. We have already a high N concentration, so we have to compensate first this N concentration, and finally when you dope, generally magnesium is doped, so when you dope magnesium, you have almost 1% of carrier concentration available. So
Kamal,
high doping.
Kamal, in 2 minutes. 2 minutes.
Right. So just to make the context on PGAN, we have two methods. One was nickel gold with 10 nanometer thickness and oxidation at 500 degrees centigrade. And second method was the palladium gold method, where again we did 10 plus 10 nanometers. And then we did a circular TLM method to find out the contact resistance of these two metal schemes. For nickel gold metal scheme, we had in the range of -2 ohm centimeter square, and for palladium gold, we could achieve -3 ohm centimeter square contact resistance. Then this was on PGAN only, not on the actual laser substrate. Then we apply the fabrication this method to actual laser structures, where we could find that the from the IV that the resistance was lower in case of palladium gold contact scheme. Then in Li measurement also we could correlate it with the lower contact resistance, that the threshold was somewhat lower than the nickel gold metal scheme, and the slope efficiency were almost equivalent. So later we did 10 measurements for this. For nickel gold contacts, we found that a P nickel oxide layer was there, which come in between gold and PGAN, and which facilitates the movement of carriers for making a low resistance contact. And in case of palladium gold, we could correlate with the large work function of the palladium to have these contacts. Thank you, sir.
Very good. Very good. You have finished in time. Are there any questions from the audience? Please. So let me check in the chat box also if there are any questions. There also there is no questions. Yeah. So, well, in that case, I thank you, Kamal Lohani, for your nice talk. So, with this, in this session, all the four presentations are over. Now, I think there will be a break, or any announcement is there. The organizer may make an announcement if it is there. Otherwise, this session is concluded. Yeah.
Thank you, sir.
Now, the organizer may like to say something. Yeah. Joby Joseph. Yeah.
Okay, thank you, Sendil, for chairing this session and smooth conduct of this session. And so we will have a poster session. This is the time for poster session. So that will be ending at 5 o'clock. So the next oral session in this hall will be at 5 o'clock. So thank you very much for all the speakers and chair and all the attendees. Thank you, and see you at 5 o'clock.
Thank you. Thank you very much. Bye.
क्या
Good evening to everyone. So there are some instructions regarding to your poster presentation. So as you know, there is a poster number assigned to you. So I will call your poster number. You have to share your posters there, and everyone is allotted 4 to 5 minutes for their presentation, and then we take questions for 1 and 2 minutes. So I will start from poster number P167. Now you can share your poster. Hello, poster number 167. Miss Meenakshi Patwal. Are you there? Okay, then we are moving to the next poster. Poster number 168, Dr. Richa Goel. Now you can share your poster, please.
Saurabh,
Yes, ma'am.
you got the instruction from and
So those who are present here, we can announce her name and his name. They
so
can
you
present.
got the instruction that you can start right now?
Hmm?
You
Ah.
got the instruction?
Yes, the people are starting here from the other chambers.
Okay. But Meenakshi, I can see her. She is present.
Yeah. Poster 169, Pariksha.
Hello,
Are you able to
sir.
listen?
Yeah, I'm able. Are you?
Yeah.
Yeah.
You can present your poster.
Okay,
There are
okay.
no.
Okay.
So you have a 4 to 5 minutes for your poster. If there are any questions, we can take for 1 to 2 minutes.
Okay. Fine. Are you able to see it?
Yes.
My screen? Yeah.
Yes.
Okay. Hello everyone. Good afternoon to all of you. And my poster presentation topic is on enhanced efficiency of thin film silicon solar cell. Yes, ma'am.
Excuse me, Pariksha.
Yes, ma'am. Yes, ma'am.
There is echo.
Echo.
Is it same for everyone?
Just a minute, ma'am. I think there is a background some. Okay.
No, you
Now is
are
it okay?
from team system.
Yes, ma'am.
How we log in from two system or?
No, ma'am. I'm not login. I log in from the browser and the app.
That both are in the same system?
Yes, ma'am.
I think then you have to log out from one.
Okay. Yeah. Yes, ma'am. I log out.
Yeah, right now I think.
Okay. Thank you. And my poster presentation topic is on enhanced efficiency of thin film silicon solar cell with nanoparticle atop silicon nitride anti-reflection coating. And here in the introduction, when the incident light resonance with the surface plasmon oscillation causes the free electron in the metal to oscillate. And for the smaller size nanoparticle like gold and the silver, here you can see like silver and gold nanoparticle absorption phenomena is dominant, and for larger size particle, for the size of the nanoparticle is greater than the wavelength of the incident light. Scattering phenomena is dominant, and as LSPR is localized surface plasma resonance, can concentrate incident light into narrow areas around a nanostructure that enhances electromagnetic near field. Here I use the design methodology is using the FDDT simulation method, in which she solves Maxwell equation in the time domain using the finite difference approximation. And here I did the optical simulation, which shows that how many photon do we absorb and where are they absorbed. As we know that for the photovoltaic application like solar cell, absorption of the photon, charge generation and charge transport and collection of the charge does matter. And here I'd used silicon as a substrate and the silicon nitride as an anti-reflection coating layer, and see the comparison of the single and the double layer silicon nitride. In this FDDT, function value is assigned to a specific point within the grid, and it's all grid by grid. And here this is a reflection spectra. This is for the silicon nanoparticle on the top of the silicon nitride ARC layer, and with the radius is vary for a fixed period. Period is the distance between the two nanoparticle on the top of the ARC layer. And this is the reflection spectra for the silver nanoparticle for the different period for a fixed radius of the 20 nanometer. And I also did the simulation for the single layer and the double layer, which shows that there is a reflection minimum for the double layer, and also short circuit current density is greater for the double layer. So it's a good method to place the double layer of the silicon nitride ARC layer, which increases the short circuit current density, and indirectly or directly you can say the increases the efficiency of the solar cell. And I also try for the gold nanoparticle on the top of the and it doesn't affect so much because reflection is almost same for all the period. And here the absorption spectra, from here absorption spectra we can see for gold nanoparticle for a fixed radius 20 nanometer with varying period, and maximum absorption is for 160 period due to the field enhancement of at the edges and the sharp points and the gap between the nanoparticle and silicon nitride due to the localized surface plasmon resonance is occur, or the enhancement of the field is occur in the gap or the edges or the sharp points and the gap between the nanoparticle and the silicon nitride. Here this is the absorption density. Here in the this is it shows the without the nanoparticle, and this is the with nanoparticle silver with the radius of the 20 nanometer and the period 180. And here the red reason we can see it is due to the field enhancement due to the LSPR. And here presence of the metal nanoparticle leads to the increase in the electromagnetic field and consequently to an increase in the photon response. And here the short circuit current density contour graph, which shows that the here for the gold nanoparticle for the different radius and the different period. So we can conclude here metal nanoparticle coated silicon rich silicon nitride thin film were designed using the FDDT simulation, and least reflection is visible was obtained for the silver nanoparticle of the radius 25 and the period 140 deposited double layer silicon nitride, and whereas highest short circuit condensity nearest 137%, 0.13% increment to the bare cell was obtained for the cell with the gold nanoparticle of the radius 35 in the period 160, and optical properties of the gold nanoparticle of radius 35 and the period 160 at top of the silicon, such as the absorption, silicon, reflection and transmission are responsible for better GSC value connected with efficiency, and gold shows a broad resonance frequency in the visible range and is highly stable, and also have the broader resonance peak as compared to the silver. Acknowledgement, this is a CSR UGC sponsored project, and would like to my friend Mr. Avasti who helped me during the simulation, and references are. Thank you. Any question? Hello?
Yeah, if anyone
Yes, sir.
asks you question, you can speak directly or type in the chat box.
Okay.
Hello, Parikshit.
Hello. Yes, ma'am.
Yeah, I would like to also did you consider the role of lattice resonance in this?
Ma'am, can you repeat it?
Have you considered the lattice resonance effect in this, because you have arranged this
No,
nanoparticles in the
ma'am.
lattice?
No, ma'am, I didn't consider lattice resonance. I just consider the resonance between the incident light and the metal electrons, free electrons of the metal on the surface.
LSPR is there, like one resonance will come
Yeah.
because of the LSPR, which you have shown like it is a broad spectrum and a broad one. But
Yes,
still, I
ma'am.
think like if it's a 30 nanometer radius, you will have a sharp peak around 550.
Yeah.
Because of interband scattering. I was just like curious to know, like, have you considered lattice resonance, because it will
No,
give much
ma'am.
more absorption.
Actually, I didn't consider in the simulation the lattice effect, lattice resonance. I only focus on the LSPR phenomena. Yeah.
Okay, thank you.
Thank you.
So then we can move to the next poster. Poster 170.
Yes, sir, I will share my screen. Yeah, is it visible?
Yes,
Mr.
yes.
Sara?
Yes.
Yeah, okay. Good afternoon, all. My name is Jinal Thakur. I'm PhD scholar working with Professor Naresh Yamani at Indian Institute of Technology, Hyderabad. Broadly speaking, our main goal was to design a nanophotonic light source, basically a nano laser with some exceptional properties. So basically, whenever you hear about a laser, the first two terms comes to our mind is the gain media and the cavity. This is well known from the invention of the laser that we need a gain and a high quality factor cavity. We were basically interested in exploring a different kind of cavity which can give us flexibility to tune the scattering and the other directional properties of a light. So we focused on the parity and symmetry. So basically, the topic of my poster is the exceptional scattering in the parity and symmetric gallium phosphide nano antenna meta surface. So what was the big thing, like over this past decade, the non-Hermitian physics of parity and symmetry has led to has manifested a lot of intriguing effects. Apart from the normal lasing, we can have a topological lasing which is robust and can have a non-reciprocal directional emission, then unidirectional invisibility, and the existence of coherent perfect absorption as well as laser at the same spectral wavelength. Basically, till now, what has happened, the research in this context has been focused on the micron scale structures, basically the whispering gallery mode or the waveguide structures, which are quite bigger than the visible spectrum wavelength. So the main problem here is like when we scale down our optical structures to the nanoscale dimensions, the losses become significant. Basically, the absorption, material losses, and the radiative losses, and the requirement on the gain, it becomes stringent. So it's difficult to realize parity and symmetry in the structures. So basically, first I will just go through like what is parity and symmetry so that our work is more clear to audience. So basically, parity times symmetry is like from our elementary knowledge of quantum mechanics, we generally consider Hermitian Hamiltonians because that guarantees real eigenvalues in a complete set of eigenvectors. And generally, it is believed that non-Hermitian Hamiltonian leads to complex eigenvalues. But the work from Bender and Boscher, they showed like that even in non-Hermitian Hamiltonian systems that possesses the parity and time reversal symmetry can show real eigenvalues. Basically, this parity time symmetries under the inversion, the spatial inversion, suppose x is changed to minus x and momentum p changed to minus p, it retains in this way. The system is said to possess the parity symmetry. The time reversal symmetry is like we have one more operator here, that's a complex conjugation, that is I transpose to minus I. The spatial inversion remains same and momentum is also reversed. Now the basic implication of this complex conjugation is that gain turns to loss and loss turns to gain in terms of photonics. If you want to incorporate this parity time symmetry in terms of photonics, it implies that we should have a complex refractive potential in our design structure such that the refractive index potential is a complex conjugate. So the real part of the refractive index should be should be the even function of the space, whereas the imaginary part, where the positive imaginary part conveys loss and the negative imaginary part leads to gain. So we should have a balanced gain and loss in the system. So what like in our earlier work already, what we published in the 7th reference was that we have considered this kind of structure, a two-dimensional lattice array. Basically, what we have done is we have considered gallium indium phosphide material with the gain and the loss, and the coupling between them is decided by the SiO2 layer in between them, and the complete system is embedded in the SiO2 environment for the homogeneous environment. So what we observed was when the light was shined from the gain side or from the loss side, the far field scattering pattern was asymmetric. So consider just the single case of the single gallium indium phosphide meta-atom, not in the periodic structure. So what we observe, like if we have an incidence from the gain side, you see the green curve, we have a forward scattering to be dominant here. Even in the loss side, in the case of single, even here the forward scattering is dominant. So what we like try to analyze is in terms of the multipole decomposition. You all are familiar with the Fourier transform. Any given signal can be expanded in terms of its Fourier harmonics. In the same way, a far field scattering can be expanded in terms of dipolar, quadrupolar, higher order electric and magnetic poles. The same thing what we did is here, the multipole decomposition. So as you can see, from the gain side incidence, we see the magnetic dipole component is most dominant, and the another one is the magnetic quadrupole. So that's visible in this 3D scattering spectra. But when the light is incident from the loss side, we see the multiple higher order poles, basically the fourth order electric pole and the magnetic octopole and quadrupole are dominant. So we see this multiple kind of spikes in this far field scattering. But as soon as we arrange this single meta atom in the meta surface, two-dimensional meta surface, basically we have considered the periodicity to be px equals to 400 nanometer and py equals to 550 nanometer. What we saw, like there was a sudden rise in the scattering efficiency. You just see the y level 10 raised to the power 5. And basically these are called as the spectral singularity. Basically they correspond to the lasing regime, where we have a purely outgoing amplifying waves. So particularly at 640 nanometer for our given geometry, we observe the spectral singularity where all the multiple components have blown up. And now here, if you see here, in both the cases, forward scattering was dominant in case of single meta atom. But in case of gamma for the meta surface, what we observed was if light is incident from the gain side, you see the forward scattering is dominant. But for the light incident from the loss side, the backward scattering was dominant. And even there was a difference in the magnitude. So on analyzing the phase term of this multiple decomposition, what we saw is for the gain side incidence, the phase difference between the even and odd parity poles was around 0.1 pi, like it's almost pi. So they are out of phase. And according to like general, it's like kind of just 0.1, it's like kind of in phase, like 0. So the forward scattering is dominant. But in the case of loss side incidence, what we saw, they were out of phase around like 0.959 pi. and that's why the backward scattering is dominant. Basically, the base of our study was on the base of generalized Tucker effect. So, like in the literature, like over in the photonics community, people have widely explored this electric dipole and magnetic dipole interference, where they say if they are equal in magnitude and in phase, forward scattering is dominant, whereas equal in magnitude but out of phase, backward scattering is dominant. And what they call is as Kirk first condition and Kirk second condition. The same thing has been generalized for the system which incorporates higher order force. What was the case in our structure? We have higher order force, dipole, quadrupole, octupole, and the fourth term force. So we have segregated them in the even and odd terms and then check their phases, either they are in phase or out of phase. Basically, this was the main message of our study, that we can analyze the scattering, far phase scattering, asymmetry scattering of this parity times symmetric systems based on this generalized Kircher effect. So basically the conclusion is we have shown that in this kind of meta surface, the lasing spectral singularities do exist and they are robust. The far field scattering is highly asymmetric and it depends on which side the light is incident, either gain or loss side. And our multipolar analysis showed that all the constituent, the electric and magnetic force, get aligned at, in our case, 40 nanometer, and they amplify largely, corresponding to lasing. The future work, like we would like to carry forward this study and try to, with the proper combination of geometry, the gain and the sub-wavelength resonances, we aim to design a tunable and directional nanophotonic light source. It will be interesting to even explore the temporal response, how the Gaussian light pulse behaves at the spectral singularity. So basically, these are my reference, and we acknowledge this work to be like funded through the SERP grant. Thank you. Any question?
Okay, thanks. I think there are no questions.
Okay.
So we are moving.
Okay.
So there are some requests. So I put a question number 174. Now you can share your screen, please. The poster 174, Kritika.
Hello. Am I audible?
Yeah.
Okay. Yes, sir. I'm just sharing my screen.
Ah.
Is it visible?
Not now.
Okay. Now is it visible?
Yeah, it's appearing.
It's there, right? Okay.
Yeah.
Hello. Good afternoon, everyone. I'm Kritika Bhattacharya, and my work highlights the possibility of using nano antennas as low-cost polarization sensor for remote sensing. Remote sensing mainly uses intensity-based IR detectors, which show lower contrast when compared to polarization-based detectors. At night or in foggy weather, object identification becomes difficult in the intensity-based detectors. Polarization sensors based on semiconductor materials, along with polarizers or edge sheets, they need cryogenic cooling. First of all, they need cryogenic cooling, as well as they have high manufacturing cost. Also, with additional polarizer, infrared detector suffers from low coupling efficiency, alignment inaccuracy, and difficulty in miniaturization. Like there is difficulty in miniaturization. So to overcome all these issues, monolithically integrated polarization sensor array has been developed. Now, polarimetric imaging using various metallic grating and nanowires, they produce compact, less complicated and less expensive and uncooled imaging system, but they show lower efficiency. So here we propose a nano antenna structure with the X and Y periodic boundary conditions, with possibility of application as low cost polarization sensor. I say low cost because these nano antennas can be fabricated by various low cost printing techniques. As we can see, this is the electrical distribution, which I've done and perpendicular polarization. It is clearly visible that distribution within the gap is 100 times higher in case of parallel polarization as to perpendicular polarization. The electric field enhancement at the gap of this is 50 nanometer gap, which I have taken between the bow tie nano antenna. The electric field enhancement at the gap of 50 nanometer shows the similar behavior. The enhancement is the 50 nanometer gap that I was talking about, and the enhancement noted here. So at parallel polarization to the nano antenna axis, that is 0 degree, and perpendicular polarization to the nano antenna axis is 90 degree, and also the unpolarized light. Now, there is a resonance that we can notice at 2.04 micron, which is according to the length that was taken. Now, there is an enhancement at 2.04 micron wavelength in at 0 degree polarization, but there is no such enhancement noticed with 90 degree. That is the perpendicular polarization. But with perpendicular polarization, there is a blue shift that is noticed, and the enhancement in that of the parallel polarization. So overall, if we see a detector polarization like polarization based infrared detector, they are mainly rated, or their FOM is based on PER, that is polarization extinction ratio. So with parallel polarization, we have achieved it at 20 and 80% respectively. That is PER to be 20 and absorption efficiency is 80%. Better than various reported polarization that were based on metallic grating and nanowires. So now for sensing and imaging, the conversion of electric field enhancement to electrical signal, which can be processed to produce pixel output with a frequency proportional to the field through an appropriate design, would be the next logical step. Like the enhancement we have achieved here, if this these enhanced field can be converted to some fruitful current or any signal with a frequency proportional to the field that we have achieved, now that could be a next logical step. And if we need a broadband detection, which is also one of the requirement for infrared detection, varying length nano antennas can be fabricated on the same substrate. This was the proposed design, and this was the proposed idea behind this. Now I would like to acknowledge MHRD and YERF, NES, and NSERC, and these are my references. Thank you.
Any question? So now moving to the next poster. P172. Oh, it's mine. Are you able to see?
Yes.
Okay, so we are proposing a gradient pitch helix structure which are arranged in a hexagonal fashion by using a multiple beam interference lithography method for the broadband light trapping. So what we do here, we are interfering the 6 plus 1 beam. The 6 beam are arranged conically as shown in figure 1a. and they are like an umbrella geometry in which the 6 beam are like a spikes of the umbrella, and theta is the tilt angle which are making be the z-axis, and phi is km dot r minus omega t plus phi m. Here phi m is the initial phase offset of individual beams, and km dot r minus omega t is the phase of the beam, 6 beams. So these are modulated by using a SLM. So what we did here, we have a 6 beam which are plane wave in nature, and the central beam is along the z-axis, that is a spherical wave in nature. So be looking into the equation 7. So Vij is the contrast factor that depends on the polarization of individual beams. So here what we assumes here our prediction is that the all the 6 beam are interfering at a very low angle, so that the polarizations are are the same for the each beams. So Vij is almost 1, and the interfering they are such they produce a helical with a gradient pitch. It means that the pitch between the two turns not remain the same. It will be changed with the z direction. So the helicity, it will be left hand helix structure or a right hand helix structure. We can tune it by modulating the initial phase offset, that is a phi m. Suppose we are phi m like 0, pi by 2, like 0 to 360 divided by 6. And if we are in the anti-clockwise direction, we get right hand helix structures. So this gradient pitch helix structure provides a unique feature that it has a effective refractive index that is gradient in a z direction. So we try to calculate the effective refractive index in a z direction by using the formula as given here. So what we do, we take a strand of a helix structure, and first we measures the core cylinder, that is the figure D here. We count the number of pixels in which they are arranged, and where HC are the area of the helix, that is the cross section of halo cylinder, that is the figure D. That's count the number of a pixel, and AS is the area of the substrate. So we count the pixel for each. When we are moving in a z direction, the halo core cylinder cross section are changed to the moon crescent direction, moon crescent shape, and then change it to the a point shape. So here we can see that an effective change from 275 to 3.27. So as we go to the z direction, the effective refractive index will be changed. So here we propose the application for the light tripping application. Here our simulation model is that the gradient helix structure is embedded in a atom medium of refractive index 3.6 that are placed on a very thin metal layer. You can see the from figure A that the 4 inner ring, that is the cross section of the helix structure in XY plane. As we go from B, we can see that here the green portion is the metal reflector, and the red portion is the our atom medium in which the gradient helix structure embedded. So we measure the absorption of each case. In the figure C, we can see that there is an enhancement in the absorption with respect to the wear medium about the 400 to 1200 nanometer broad range. So, and the second figure, we try to detect the decay electric field time with the without the gradient pitch helix structure and with the gradient pitch helix structure. So we find that there is a enhancement. There is the gradient helix structure slows down the decay time of the electric field, and light will trap inside the medium for a longer time. Then the different structural parameters like helix radius, helix fiber radius, and the number of turns are calculated for the absorptions spectra. For the first figure, we did for the helix radius of 200 and 400 nanometers with a constant fiber radius of 100 nanometers, and we found that for the 200 nanometers, the absorption are more prominent in nature with respect to the 400 nanometer radius. And the second we did for the different fiber radius with the same helix radius, and we found that the low value of the fiber radius will be more efficient for the light tracking applications. Then we go for the number of turns for the n equal to 2 and n equal to 6. The number of turns are increased in a such way that the helix structure will be remain embedded in the active medium. So what we find here that the low value of n is more good, more excellent for the light tracking application. Then we measure the effect of periodicity of hexagonal structures in the absorption. So the first one we see figure C is done for the period of 1600 nanometer. So here in the figure H, we did for the 400 nanometer, 800 nanometer, and 1200 nanometers fiber periods. So what we see that for the smaller period, the wavelength for the range of 400 to 800, the absorption are more prominent, and as we move to the longer wavelength, the larger value of periods will be will give the more efficient light application. The reason is the simple is that the embeddedness of the helix structure in a medium will provide a grating texture on the in the top surface of the active medium. When the light incident on it, if the wavelength of a light is comparable to the grating period, it will be diffracted. Since the diffraction depends on the refractive index, the air medium has a refractive index of 1, as we know, and the active medium has a refractive index of 3.6. So the transmission is more than the reflection, or we can say that it will induce a anti-reflection property at the top surface. So here we conclude that by putting the by adjusting the fiber radius, helix radius, and with a low number of return, we can tune our absorption for different periodicity with different helix structures. That's all the reference. Thank you. If any questions, please ask. Can I stop sharing and move to the next presentation? So I am moving to the next presentation, poster 173. Are you here?
Yes, sir. Yes, sir. I'll share the screen.
Yeah.
Sir.
Yes.
Good to everyone. I am Namrata Shetty TG, and the title of my poster is Modeling and Analysis of Far Field Intensity on Light Emitting Diode to Reduce Surface
Hello.
Plasmon Losses.
Yeah. Sorry. Can you go for the full screen? Is it full? Is it in full screen mode?
In my mobile, can I just
it's good.
so that you can see?
Okay.
So, the organic light emitting diode is nothing but when an organic material is placed between the anode and cathode, and when we apply a suitable voltage across anode, protons are emitted from anode and electrons are emitted from cathode. Due to recombination of protons and electrons, the excitons will be generated, due to which the light will be emitted. But due to different kinds of losses, only 20% of the light will be emitted out, whereas 80% of the light is trapped inside the OLED. So the different kinds of losses in conventional OLED is substrate loss, which occurs at substrate and air interface, and waveguide loss, which occurs between glass and ITO, indium tin oxide, that is anode, and the surface plasmon loss, which occurs at the cathode metal and the organic or the emissive layer. In this poster, I deal with surface plasmon losses. Surface plasmon loss is the delocalization of electrons at the interface of any two material. It will have a faster decay rate. The maximum amount of light generated by OLED is lost, that is about 40% due to surface plasmon. The surface plasmon loss occurs at the interface of cathode metal and the organic or the emissive layer, as you can see in the proposed OLED structure. Hence, that is nano grating of cathode metal to avoid the surface plasmon loss. Here, figure the modeled OLED structure. Here, the grating pitch of the structure is calculated by Bragg's law, that is 2d sine theta is equal to n into lambda, where d is the pitch, which is also called as lattice constant. Theta is the viewing angle, which varies from 0 to 90 degree. Lambda is operating wavelength, that is chosen as 540 nanometer. And n is the net refractive indices, that is average of all the refractive indices of layers in the OLED. The grating pitch is then found to be 4 nanometer. Then the cathode metal used here is aluminium. In figure 6, you can observe the graph where we have the far field intensity is maximum for aluminium among magnesium, silver, aluminium and lithium fluoride. And it is aluminium is the most suitable metal for the cathode. And the height of the pitch varies from 120 nanometer to 160 nanometer. In figure 7, you can observe that the far field intensity is means enhanced for 160 nanometer. And we use FTTD simulation to check the far field intensity. The far field intensity is nothing but the amount of light coming out of air. Then the organic layer used in OLED is AlQ3, which is aluminium trisquinoline, which emits green light. It is the green organic light emitting diode. In figure 4 and figure 5, you can observe that there is more green light, that is due to AlQ3. And comparison of conventional with the nano-graded OLED is carried out to check the maximum far field intensity, and we have found that the nano-graded cathode structure will have 1.05 into 10 power minus 5 volt per meter, and that of planar cathode is 4.08 into 10 power minus 6 volt per meter. Hence, far field intensity is enhanced for the nano-graded cathode structure. Thank you.
So if there are any question, you can ask. Otherwise, we can move to the next poster. Okay, the next one, poster 175, Dr. Praveen.
Okay. Hello.
Yes.
Can you hear me?
Yes. Yes.
Okay, I will share my screen. Can you see my screen?
Not now. Yeah, I did. Yeah.
Okay. So is it visible for, or should I make it full screen?
Yeah, if you are able to make a full screen, you can. Otherwise, it's okay.
Yeah. So yeah, so I'm Dr. Praveen Vaiti. I'm working in TFR as a postdoc. So today I'm going to talk about polarization independent excitation of quasi-bound state in continuum, which we generated in symmetric metasurfaces. So what is this bound state in the continuum? So this is a unique state which is localized in the continuum. Hello. So this state was first proposed in quantum mechanics. So we all know about a quantum well, where we have a bound state and the particle which have energy larger than quantum well potential, they form continuum. So if we modify this quantum well as I shown here, then you can get a one localized state in energy continuum. So they proposed this in quantum mechanics, and in around 2010, this state was realized in optics. Um, so it was first realized in some complicated structure, but later they found it in simple grating kind of structure. So generally, in grading, if we study its a dispersion curve, then we can find some profile like this. So there you could, if you record the quality factor, then you will find that at a continuum there will be one frequency where the quality factor get become infinite, and that state is called a bound state in continuum. This state also realized in metasurfaces, which are the actually two-dimensional high-index grating, but mostly at the gamma point. Means one can see this when one illuminate a light on grating at a normal incident, and we the but main important thing is this BIC have infinite quality factor, but near to BIC there is a another high Q resonance which is called quasi BIC, which can be helpful for many application where we need high Q resonance, because BIC have infinite Q and we cannot we cannot employ that BIC to real application, but we can use a quasi BIC. So this quasi BIC have large or strong high Q, but we do not have control over it. Means to get that quasi BIC, you need to give small angle where BIC is present. So we do not have control. So people propose a different structure where they break the symmetry, and by breaking symmetry, they could see the quasi BIC. So they use this kind of different structure where they use a nano cylinder which having hole at the not exactly at the center but slightly away from the center, and when that hole is moving away from the center, then symmetry get broken, and one can see the quasi BIC. So here also, here the issue is it is a polarization independent, because symmetry is broken. So one can see the high Q resonance either for T or TM polarization, but not for both at the same time. So what we did, we design this new meta surface where we interlocked two square lattices, and we form this kind of structure where two square lattices are interlocked, and we control the property of one property of one lattice, and we observe the high Q resonance. So here you can see the reflection spectra where we measure reflection spectrum as a function of radius difference. Means what we did, we changed the radius of the one lattice structure and keep other lattice structure as it is. So, and this radius difference is the difference between the radius of these two structures. So we observe that as we change the radius, the means for example, if I am decreasing the radius difference, then I can see the quasi BIC is forming. Means it's a line width is getting smaller and smaller, and at the one place where the BICs exist, this line width is a disappear, and line width is disappear means Q factor is infinite. And then we also plotted a quality factor as a radius difference. So we numerically study the quality factor measurement, and then later we just choose one quasi BIC position, and we what we did, we changed the different polarization state and study how this resonance is appearing. So it is matching very well for all the polarization. So here, we can say that we can make a quasi BIC state with the any polarization. So this may have application for white light spectroscopy, and where we need we can use a white light. Thank you for attention. And if you have any question, please.
Hello. Hello.
Yeah. Yes.
Yeah. So you have shown that you have merged two different lattice constant in a
Hmm.
small lattice, so that you obtain the BIC condition. But this is also
Right.
possible that even if you consider a single lattice, and for certain parameters, this BIC
Yes.
condition is
Yes. Yes.
invisible.
Yes. Yes.
Yeah.
Here
Then
in here this is for single crystal, and you have BIC at the gamma point, but you do not
yeah.
have control.
So your screen is not visible. I think one more thing, you have login with from two different two site. So actually the disturbance was coming. So you can check it. Now your screen is actually not visible. I just want to see the
Okay.
lattice also once.
Should I try to share one more time?
Yeah, please.
Now, can you see it?
Not it.
Oh, maybe it will take us.
Yeah. It can.
Okay, so here in where I have written BIC in meta surfaces, this structure shows BIC, but we do not have control over the quasi BIC.
But
It will
actually,
appear.
if you go with an oblique interaction, probably you
Yeah,
can
you
access
will.
the
Yeah,
BIC.
yeah, with the oblique incident, but you don't know what exact angle, right?
But
And
if
you
simulation,
cannot control that angle.
but a simulation study, that's true. But a
Hmm.
simulation study can approximately tell about the angle where the BIC
Yeah, but
crosses
in
the BIC.
real experiment, you do not have a control over the that
Yeah,
value,
definitely.
right?
When you go for
So,
the experimental thing, the problem is that you need to have a very small divergence angle. Then only you can
hmm.
detect, because this
And
BIC will come and appear. It's for a very small, like 0.1 degree or something. It will
hmm.
come or then disappear. So that is true, but
Right.
you will have an idea that what angle it will this can happen.
See, for example, if you want to want some specific quality factor, means if you want controlled line width for your resonance,
Yeah.
then you cannot control your incident angle, right? But if you design your structure in such a way that where you have control over the line width, then you don't need to illuminate exactly. Means you can always illuminate normally. You can always make a normal incident, but you to make a particular angle incident is a very difficult task in experiment. Am I satisfied?
Yeah. And what about the quality factor? How much it's coming?
Quality factor is getting higher and higher as the radius difference is getting shorter and shorter, and at one point it disappears.
But can you mention some number in terms of
Yeah, for example, when the radius difference is a 0.05 nanometer, then I have quality factor around 10 power 4.
10 raised to 4. Okay. So this calculation you have done using which tablet?
I use a RCWA method, which we write a code here, means in Python.
Okay.
So all the calculation was done in RCWA, rigorous coupled wave analysis.
Yeah. Okay. Okay. Thank you.
You're welcome. Any other question?
Okay, now we can move to the next.
Okay.
Yeah, poster 177, Jagriti. Poster 177, Jagriti, you can share your screen.
Yes, sir. I will. Am I audible?
Yeah.
Okay, I'll share my screen. Okay, is my screen visible, sir?
Yes, yes.
Yeah. So, good afternoon, everyone. The topic of my poster presentation is gallium indium alloy nanoparticles for deep UV plasmonics. So, before starting with the details and the methodology, I would just like to give you a brief. What is plasmonics? Plasmonics is basically the confinement of the light, the technology in which confinement of light occurs. It is derived from the word plasmon. Plasmon is a basic pointer associated with the collective excitation of the free electrons in the metal. So whenever we impinge any electromagnetic radiation on the nanoparticle, it causes the metal electrons, the electrons in the metal nanoparticle to oscillate. And when the frequency of the impinging light matches with the frequency of the electron oscillation, then at that particular frequency, there is a very high absorption of light. That frequency is known as surface plasmon resonance. Okay, so my main aim was to harness this particular principle of plasmonics and to use this surface plasmon resonance in some electrical applications in the UV region. As we are all aware that gold and silver nanoparticles were in use from past 10 to 15 years, but these gold and silver nanoparticles only show the plasmonic response in the visible region. There is no plasmonic response of gold and aluminum, gold and silver nanoparticles in the UV region. My main aim was to find such nanoparticles which can show plasmonic response in the UV region. So some of the metal which shows the plasmonic response in UV region are aluminium, gallium, indium, rhodium. Among these, gallium and indium suits the best metals that shows the plasmonic response in UV region because of their very less oxidation tendency when they are exposed to air. Gallium only forms an oxide layer of 2 to 3 nanometer when it is in the presence of oxygen. So in my research work, I have fabricated the nanoparticles of gallium indium alloy. Why I've chosen gallium indium alloy? Because its melting point is just 15.3 degrees Celsius. Uh, So at a room temperature, it is purely liquid in state. Okay, so how I fabricated? I fabricated by the process of sonication. I've taken 75 gram of gallium and 25 gram of indium, heated it and placed in a glass vial, suspended in ethanol, in 10 ml of ethanol. Uh, After this, I've sonicated this sample. Ultrasonic waves causes the formation of nanoparticles, formation of the gallium indium nanoparticles in the solvent. After the sample has been prepared, I have characterized my samples uh, with the techniques known as SEM, EDEX, nanoparticle tracking analysis, and UV visible spectroscopy. Okay. After this, I have characterized 7 different samples at 7 different sonication time and power to check the effect on the time of the sonication and the effect of the sonication power on the size of the nanoparticles. Coming to the results section, these are the 7 samples which are fabricated of heated gallium indium alloy. All the samples are of 200 milligram by weight and are suspended in 10 ml of ethanol. The, okay, and I varied the sonication power from 250 to 500 watt and then to 750 watt. Also by changing the sonication time, starting at 10 minutes to 12 minutes and then to 18 minutes. The results shows the efficient results for the samples shows the nanoparticles are of spherical shape, each having a diameter of 100 nanometer to 300 nanometer. The nanoparticle tracking analysis shows that most of these nanoparticles in the sample are in the range of 100 nanometer size, and the UV visible spectroscopy results shows that there are 2 predominant peaks in the UV region. There are in the UV visible spectroscopy. The first peak is at 217 nanometer, and the second broad peak is at 259 nanometer. The first peak lies in the UV region, which signifies that these nanoparticles will work properly in the UV region and will show high optical response in the UV region. Okay, after that, I've compared the dependence of sonication time on the size of the nanoparticles. So as we increase the time for the sonication, the particle size decreases. The less will be the particle size, the more will be the better will be the optical response of these nanoparticles. Also, as the size of the plasmon, as the size of these nanoparticle decreases, the local surface plasmon resonance or the peak in the UV region, the peak in the absorption spectroscopy shifts towards longer wavelength. As a, therefore, there is a red shift in the plasmonic energy. So when the size of the nanoparticle decreases. So these gallium nanoparticles are tunable to specific plasmon resonance ranging from 0.7 electron volt to 6.5 electron volt. The absorption spectrum of these gallium nanoparticles lies in the UV region. The plasmonic properties of euteric gallium indium make it more suitable for applications such as solar cell and photodetectors. We can fabricate these nanoparticles on some UV visible in the photodetectors which significantly work in UV region. So when we fabricate these nanoparticles on such photodetectors, there will be very high optical response. This will increase their optical performance of any device which works in the UV region. So that's it. That was my work. So,
Jagriti?
Thanks.
yes, ma'am.
So this is basically a solution method, no? The preparation of particle is based on a
Yeah,
solution method.
yeah, this is a solution-based method.
So how did you prepare it? Just to sonicate the solution, just after the sonication, the nanoparticle is formed.
Yeah, ma'am. Just by mixing the alloy of gallium indium in the ethanol, and after performing the sonication for 10 minutes, we can get the nanoparticles in the liquid state.
Okay. So the size can control.
Yeah, we can control the size by the sonication time. If we increase the sonication time, the particles will be form of very small dimensions. Like if we do the sonication for 1 hour, we can get nanoparticles of 50 nanometer size.
But you have not tried for 15 nanometer.
No, I haven't tried, but some of my lab mates have tried this. They got this. They got the nanoparticles for 50 nanometer.
Uniform distribution. How
No,
was the distribution?
there is no proper uniform distribution. That however, the mean number of particles lies in the range of 50 to 100 nanometers.
Okay. Okay, thank you.
Thank you, sir. Thank you, sir.
Moving to the next, P176. So we have 20 minutes left, and there are 2 more posters, including yours.
So the screen is visible now?
Yes.
Okay. So I'm Sharina Joseph. We'll be talking about a grating coupled surface class 1 sensor designing with a large penetration depth. Design have been fabricated. This design particularly. So this is like dielectric grating made up of high index refractive index constant 2.7 beneath uh, a thin metal layer of 40 nanometers, and the whole structure configuration has been immersed in a transparent resin that is NOR 61. This geometry can be identical to a prism coupled mechanism, because light will be coming out from this grating side, and we can have a plasmonic mode at the other side, that is the metal and a light interface. Now, this structure fabrication, this is a complicated structure, and we have introduced a new kind of deposition, new kind of fabrication procedure. So it can see in here. Initially, we have considered a glass substrate and coated gold, then thin nanometer chromium to have a good adhesion. Then we have coated a negative photoresist, and using a laser interference lithography method, we have recorded a grating pattern of 110 nanometer on the photoresist. After that, we have developed a sample. So optimized, uh, optimized dosage of the illumination as well as the developing time can give perfectly undercut wall grating, photoresist grating on the god layer. Further, we have coated the high index layer using thermal evaporation method. So the structure would be like this. Everywhere there will be deposition or above the photoresist as well as on the gold layer. So by if you we can do a litho process, so successful ethanol. Ideally, all this material deposited on the photoresist, and the photoresist should go away. So we'll get a final structure of arsenic arsenic selenide grating on gold layer. However, there was a problem because the adhesion between the gold and the glass surfaces is not good, and we cannot use any adhesive layer here. So what we did, we have used consider the whole structure as a grating, and then we have immersed in the resin. So we poured the resin over the grating, and it's a UV curable medium, and it is cured. After that, using a tweezer, we can peel off the glass substrate from the remaining structure. So we'll have a structure, we'll have the grating and the metal. The grating will be immersed in the resin, and the flat metal layer we can update. So the reflection from the metal layer shows that without much problem, we can easily remove the, or we could peel off the structure geometry from the substrate, and the illumination from the grating side shows color, so we can ensure that the grating is still present in the medium. Now this geometry, we can have a customized cavity, and this on the cavity we can fix a sample, and we can introduce different analyte medium, and we can measure the spectral response. Further, if we come back to the structure, and the structure actually supported a number of resonance mode. In order to understand the mechanism, if you see light coming from this side on the grating side, and it diffracted at the grating, there will be propagating orders within the grating, and there can be evanescent orders also. So the propagating order can give some photonic modes, because if you consider the grating and the resin as an homogeneous layer, then the propagating diffracted order can excite certain guided mode resonance modes. So that's what also we can expect on this structure. Also, there can be evanescent order coming out from this different diffracted order. This evanescent order can excite surface plasmon polariton mode on both the interfaces of the metal. Now, if we calculate the response, if we simulate the response of the optical response of the structure, the reflection spectra, it is shown over here. Now, out of there are a number of resonance mode. We are interested to see the SPP mode, which excited on the metal analyte interface. So here we have shown the reflection spectra of different analyte medium ranging from 1 to 2. So in order to identify the, because there are other resonance modes, in order to identify the particular mode of interest, we have circled the particular modes. Now, if we see the electric field distribution of this particular mode, we can see that there is a huge enhancement of electric field distribution close to the metal layer, and the evanescent field is actually extending into the analyte medium. So, and if you change the refractive index from 1 to 2, so the resonance modes are actually redshifting. However, the nature is same, except the maximum value of the electric field intensity has reduced. However, further, the hello. Further, the decay length of the medium has been extracted from this particular electric field plot. So the electric field lines are actually plotted over here. So the decay length or the penetration depth has been defined as it is the distance over which the maximum amplitude decreases to 1 by E of it. So it can see that in all the case, the particular symmetry supported a large penetration depth. The field is highly penetrated into the analyte medium. So we expect that the structure should definitely give a high bulk sensitivity. The other proposed structure, this is a particular characterization of this characteristics of this structure, because it has a high evanescent field penetration in the analyte medium. Further, the bulk sensitivity has been experimentally detected using commercially available software, for spectrometer. But the problem is that the spectrometer which we actually use will not work in the normal incident. So we have calculated the reflection at a minimum angle of 6 degrees. Now, from this expression of the surface plasmon excitation process has been explained over using this particular expression. So this is the grating. This left side part is coming from the grating expression. So there is M is corresponding to the different order of the diffracted order. So we go for normal oblique interaction. There can be non-degenerate mode. So we have a number of modes are increases at the angle of 6 degree, because all resonant mode are getting non-degenerate. However, what we try to calculate.
Please conclude. We will have the next session starting soon. So please conclude. And
Okay.
right, speakers are here already.
Okay. So we calculate the sensitivity by considering two different refractive index, and we could obtain a bulk sensitivity of 100 1133 nanometer per refractive index unit. And so the structures are particularly showing a bulk sensitivity as well as a high penetration depth. That's it.
Thank you, ma'am.
Yeah.
Be able 2 or 3 minutes. So there are one more poster, Ms. Meenakshi Patwal. You can wrap your poster within 2 minutes, please. Please share your screen. Poster 167. Yeah, please try to wrap it as soon as possible within 2 minutes.
Hello.
Yeah,
Good
you can
evening,
start now.
everyone. Am I audible?
Yes, yes.
Good evening, everyone. I am presenting poster on the topic of simulation studies for mode profile analysis in single mode high power asymmetric optical cavity laser high power asymmetric large optical cavity laser structure. Here in LOC, that is in large optical cavity structure, the quantum value is asymmetrically placed because here the thickness of uncladding is quite large. If we look at the diagram here, the thickness of uncladding is quite large as compared to the p cladding, which is thin. Because in gallium arsenide here, the free carrier absorption is more in the case of p cladding. So that's why we have given the uncladding of around thickness 6 micron. So that's why there are less losses and high power. And I have done simulation. It is actually the structure is for 2D mode solving because both the Fabry-Paro and laterally coupled DFB laser have same 2D cross section. The difference in their grating width, the difference in their bridge width in the longitudinal direction. So here I have done a preliminary analysis of DFB structure, basically for Fabry-Paro bridge wave structure. So in this, we had done analysis of nodal distribution, confinement factor, and effective for residual So here, if we look at the diagram, at very high residual thickness, it means at very low H depth, planar kind of planar modal distribution. The modal distribution is kind of planar. In this, we can see that it is that an increasing ridge width, it is not making any substantial difference. So but we cannot use it for our grating designing because though it provides high fabrication tolerance, but in these devices, mode confinement is large, which will provide lower coupling with the lateral grating. So and if we move towards the high residual, if we move towards the low residual thickness or the high H depth, here it is more prone to higher order modes. So it means it is more it is highly sensitive and it is not fabrication tolerant. So at the H depth of 1 micron, that is at the 47 nanometer, we get optimal. Hello. At the H depth of 447 nanometer, it can provide better flexibility in terms of coupling with the grating and with the mode field. In the grating, we can have residual thickness of ridge width 1.5 and 3 micron, and
and I have to do the future work has to be done in optimizing the other grating parameters by optimizing the coupling coefficient of the grating. So, sir, I had done.
Oh, yeah, okay, thanks. Dr. Richa Goel, are you here? Dr. Richa Goel, poster number 168. Okay, she is not here. So thanks for sharing your wonderful talks and experience. And now transfer to the session co-chairs.
Thank you so much. So we have the co-chairs for the session. So I'm Dr. Anuj Dhawan, and we have Dr. Jian Yu, so Professor Jian Yu, and myself are the session co-chairs. So I will briefly introduce Professor Jian Yu. Professor Yu is a professor of engineering, science, and mechanics, and an adjunct professor of electrical engineering at Penn State University, and his research area is in optoelectronic materials and devices. And he obtained his PhD from University of Michigan, Ann Arbor, and is NSF Career Award winner in 2009. And he works primarily in the area of photonics, optoelectronic materials, and he currently sits on the editorial boards of Journal of Electronic Materials and SPI Journal of Nanophotonics. He has been the chair of the fall meeting of Electrochemical Society Symposium on Semiconductor Nanocrystals and Nanostructure Enhanced Photonic Devices. So Professor Yu is here with us at IIT Delhi. We thank him for being the co-chair for this session, and he will introduce Professor Jean-François Masson. As Professor Masson joins in, he will be introducing Professor Masson, and then later I'll introduce Professor Magnuson, Professor Robert Magnuson. So Professor Yu, I give the stage to you. It's very nice seeing you after a long time.
Sure. Thank you. Thank you for the introduction, Professor. Is that clear to you?
Yes.
Okay. So I think it's time for start our session presentation. So our speaker, our next speaker was Professor Jean-Francois Masson. The title of his presentation is Plasmonic Nanobiosensors, Therapeutic Drug and Environmental Monitoring to Optophysiology of Living. Professor Jean-Francois Masson is a professor of chemistry at the University of Montreal, Canada.
Anuj, can you just mute yourself? There is some noise from.
Oh, how about, is that better now? Can you hear me?
Yeah, now it is better.
Now it's better.
Okay, so I will. Well, in that case, I will just start from the very beginning. Sorry, I hope it is getting better. Okay, so our next session, we would like to invite Professor Jean-Francois Masson to give a presentation on plasmonic nanobiosensors from therapeutic drug and environmental monitoring to optophysiology of living cells. Professor Masson is currently a full professor of chemistry from the University of Montreal, Canada. He got his bachelor degree in chemistry from the University of Sherbrooke, and then his PhD degree from Arizona State University in chemistry. he also received the postdoc training from Georgia Tech, also in chemistry. Professor Mason has received numerous honors in his career. In the past 5 years, he became the top 100 in analytical science, the analytical scientist from UK, and then the McBride Medal of Canadian Society of Chemistry, top 40 under 40 in analytical science, Fellow of Royal Society of Chemistry, Travel Award of the Canadian National Committee of the International Union of Pure and Applied. He has published more than 125 research articles, filed more than 100 patents, presented more than 100 invited lectures, and he is also the associate editor for ACS Sensors. Okay, so I would like to give the time to Professor Jean-Francois Manson to start his presentation.
Professor Masson, I think he is. Yeah, I think he is not logged in yet. So there's some.
So let's wait a few minutes.
Yes, we'll wait a few minutes and then. Yeah, so he is not connected. Just 1 minute out.
Yeah, so let's wait a few minutes. I think this could be due to the time difference between Canada and our current.
Yes. Yes, I think this is probably, so we'll just wait a few minutes and it's the very early morning but we've gotten a confirmation from him that he will be joining, but essentially we just will have to wait for a couple of minutes. I think it's like 5:30 or 6:30 in the morning over there, so we'll just confirm.
Right.
Yes, I.
So looks like it's already
Yeah,
8 minutes.
8 minutes into it. So the next speaker is Professor Robert Magnuson, but his talk is at 5:30 here. Professor Joseph?
Yeah, I think he will join only exactly on time because.
Yes, he'll join. So we have no option but to wait because he will join on time. And it's very early, and so
I think let us come back after 20 minutes or so.
After 15 minutes, we can all be here.
Okay. So let's
Thanks,
speaker.
Yes, sir. We'll just wait for the next speaker because.
Thank you.
Good seeing you. Is that you?
Yes.
How's everything?
Yeah, everything goes well so far.
Very nice.
We can meet in the conference and do presentation over the internet.
Yes, yeah. We were looking forward to having you here in Delhi. This summer and then now winter, but hopefully next year, we can have something. So it's a good. Sure. So I think in 10 minutes or so, or 15 minutes, we can join back.
Okay. That's great.
Thanks, sir.
Thanks.
Welcome, Professor Magnuson.
Yeah, good morning. How are you?
Good morning. How are you, sir?
Are you Joby?
No, I am Dr. Anuj Dhawan. I'm one of the co-chairs.
How are you?
Good talking to you here. Very.
Okay, so everything is okay here?
Yeah, everything is okay. Actually, Professor Jian Zhu, he is also a co-chair. He also came in. We had one of the speakers, I think, had a problem logging in the session.
Oh, yeah.
Professor
My old friend Kehar Singh, does he there?
Yes, he's here. He's logged in, but they may have stepped out for some time because we decided to take a 15. Oh, yes, he's here.
Hello, Professor Singh. How are you? Long time no see.
And Professor Joseph is also here. Joby Joseph is also here.
Hi
and
there. Good morning.
Professor Jian Zhu, Penn State University. And so Professor Jian Zhu he's from Penn State University, and he's a co-chair of the session along with me.
Very good.
Hello, Professor Kier Singh, Dr. Anand Dhawan here. Nice to see you.
So I have to share my screen here, right?
Yes.
Right.
So we'll be starting in around 10 minutes. Okay. But Professor Zhu, do we wait? We wait for, because he's listed at 5:30, but we can start earlier too if,
that's fine. But I have to just make sure that my slides show up. So I open my slides on my desktop. Do I open my slides on my desktop? Shall I try it?
Go ahead. Yeah, go ahead. Give it a try.
Yeah, exactly. So you can open it on your desktop and then share. That's the third button at the bottom. And then when you share, you can select the slides. Yeah, I think, yes, you can see your slides.
Yes.
Okay. How about now? Can you see the slides in display mode?
In display mode. You can see the slides in display mode.
Okay, good.
Great.
I don't see them.
So, Professor Zhu, do we wait for 5:30 for 10 minutes, or do we start?
Yeah, we can start now.
I will wait a few minutes. Let me get some coffee.
Yeah, okay. Great. Okay, great. Yeah, we can actually wait because if somebody logging in at 5:30 for his talk, then they would miss it. So.
Sure.
So I think we could wait for 5 minutes and so how is everything in Penn State?
Yeah, well, because of this that is a problem.
Right.
Online. So it's definitely not as Europe.
Right, it's not.
So I hope next year everything will be better.
Yes, in 3 months, I think, 3-4 months, hopefully, with the vaccine coming in, that should be good.
That's the plan.
That is excellent.
So if are the classes offered as remote?
So yeah, the classes in IIT Delhi are being offered remotely, through either live session or pre-recorded lectures. So that is what, because a lot of students won't have the bandwidth in small cities and villages. And so what we're doing is we're recording the lectures and also putting the recording lectures like printouts online and through Impartius, then students can access the videos whenever they want to. They can access them, and so that's what mostly. Sometimes, if all the students agree, then we're having live sessions too in between. Like if if they can all log in, and that's smaller classes, that's also happening. But when the class is big, then we have a lot of students that don't have the bandwidth in their cities and villages, or so.
Right.
Other constraints.
Yeah, and there's
Yes, so that's Professor Magnuson. So that's one of the issues where we're facing the bandwidth problem. So it's not equal for everybody across the country, and so how are things in Texas? Things are
Okay here. We have, of course, this virus raging here. It's a big problem. University is basically closed now because it was Thanksgiving yesterday, and then we have exams in about 10 days. And then it's basically hiatus until mid-January.
Oh, great.
Hopefully we'll come down on this virus curve very quickly.
Right. We hope so too. So Arlington must be better off than Houston, right? I'm guessing that Arlington would be.
Maybe a little bit.
Okay.
It's just a terrible situation. Very boring. I haven't been anywhere since March. I've been here since March.
In the house, or in the city is that's I think.
Yeah. It's not fun.
Yes, it's.
But my research group, we still we come in every day and we still work because we have labs and stuff to do.
Oh, that is great. That is great because in IIT we suffered because the students were sent home in March and they were allowed to come back in, but a lot of them don't want to come back because Delhi has a very high rate of coronavirus, and so we have choices with the students. So a lot of them don't want to come back, and some of them who've come back, they're getting COVID also, and but a lot of them don't want to right now take the risk, and the newer students they haven't allowed also. The people who have joined within the last 1 or 2 years, they're saying that you have to wait. So it's only the older students, the senior students, they've allowed that they can come and finish their PhD if they want to. But the choice is with the students, like basically that they have to sign an undertaking that they are fine with coming in, and their family is okay that they come in, and so that is good in a way because they have the choice to come, and so.
So how many people have registered for your meeting, for this conference?
So we had a lot of registrations, like basically overall, because it was online, we've had a very good response. So even the number of invited speakers is very large, and presentations, so it's been a very large number because plasmonics and photonics is one of the symposia, but we have other symposia, like other 8 symposia that are there. So overall response has been very good. So even in photonics and plasmonics, we had 25 invited speakers, and
I saw that.
So the number of people, so this wouldn't have happened, if everybody was traveling. It would have been a little bit less because everybody coming in from flying in and time wise. So it kind of it turned out to be better because of the online. We got more speakers and more participants. And so
yes,
that's
it's true. It does have some advantages. I've noticed in faculty meetings in my department, there is nearly 100% attendance because everybody is just logging on and it's more convenient than coming to the meeting.
That's right. So I think
I like conferences. I like the personal face-to-face better than this.
Yeah, exactly. I mean, personalism. In fact, it would have been great if you and Professor Zhu and everybody, would have been here. I think Professor Zhu is speaking tomorrow and is giving his talk tomorrow. And that was the original idea. In fact, we wanted all of you to be here for more partnerships, for more, collaborations and things. But it just happened so that the coronavirus was supposed to have gone, but it's not, yet gone, and so we have the online. But yes, if in a year or two we have it again in Delhi, then we'll definitely, hopefully have a live conference. And so that's the objective.
Okay, so now it's 5:30.
Yes.
After presentation. So, should I go ahead and start to introduce?
Yes, sir. Please, Professor Zhu can introduce Professor Robert Magnuson. So please.
Okay. So I think it's time for us to the speaker. Our invited lecturer. The invited speaker is Professor Robert Magnuson, and the title of his presentation is "The Guided Mode Resonance Fundamentals and Applications." Professor Robert Magnuson Texas Institute's Texas Instruments distributed. Professor Robert Texas Instruments distinguished university chair in nanoelectronics at the University of Texas at Arlington. He directs the UT Arlington Nanophotonics Group. Current theoretical and experimental research, theoretic nanostructures, nanolithography, nanophotonics, nanoelectronics, nanoelectronics, nanolasers, and optical bioelectricity sensors. Professor Magnuson has published scientific journal and conference papers, more than 40 patents. He is a fellow of OSA, IEEE, the National Academy of Engineers. He is co-founder and the CEO of Predator Sensors, a company that provides next-generation sensor systems for biochemical science, including the COVID-19. Okay, so I will pass the time to Professor Magnuson for the presentation.
Thank you very much for the introduction. I want to thank the committee for inviting me. I have some feedback, but okay. So I'm going to talk about the field, which is guided mode resonance nanophotonics, fundamentals and applications.
Mute your mic. There is some noise from the group here. Anuj?
Yes. One second. Yes. 1 second.
Yeah, good. Then there is no noise. Yeah, good. Thank you.
Okay. Can you hear me now?
Yes.
Okay.
It's good.
I think everybody else needs to be muted. That's why the feedback is coming in. Okay, thank you very much. I think, I can start again. Guided mode resonance nanophotonics, fundamentals and application. That's my research area. I've been doing that for a long time. This has to do with wave propagation and periodic materials in general. You can see on the cover here some examples, some nanophotonic devices that have been produced with the tools that I will discuss here in this lecture. This is a silicon array. This is a metal wire grid, and so on. I'll introduce that further as I go along. But anyway, I'm pleased to be here giving this talk. It's not too bad. I'm not there in person, but that's how it goes. The virus is dominating the world. Hopefully, we will conquer it in 2021 and we can all get together again. My outline is here. I'm going to give a brief introduction to the basics. of resonant photonic lattices, basically how it works and what's going on behind the scenes. I will then give some examples of computed and fabricated resonant lattices with total reflectance or reflection approaching unity, both narrowband and wideband varieties. I will discuss the resonance driver, which is basically lateral leaky block modes, and I will show demonstrations that prove that from multiple points of view. I'll say a few words about what I call lattice band dynamics and how that whole thing works, band flipped and so on. And then I give a couple of examples. And so the basis is basic resonance interaction referred to the excitation of leaky eigenmodes in one-dimensional or two-dimensional dielectric waveguide gratings. As we all know, if we shine light on a periodic structure with an arbitrary period or arbitrary relationship between the period and the wavelength, typically we will see multiple diffraction orders propagating based on the fundamental laws of diffractive optics and the grating equation and all that good stuff. So that's what happens here. Now, if this is a waveguide grating, that means the refractive index of this layer is higher than that on the average in an effective medium sense than the surrounding media. Then we can couple to waveguide mode inside this layer. And when that happens, there's a sharp resonance that takes place, a glitch in the spectrum in general. Now, this is a very wasteful regime because we have all these higher orders propagating and stealing energy off of the main orders there that are going to be the zero orders in reflection and transmission to have a major impact. And this situation is brought about by going to the sub-wavelength regime where we have only zero order diffraction. Namely here, the period is smaller than the wavelength, so these higher diffraction orders do not propagate. So this is a simple one-dimensional explanation, but we can make it more complex and couple light into a two-dimensional lattice with a two-dimensional general wave vector describing it, and then we have multi-directional leaky modes and resonance effects associated with those generated. So when I explain this to my students, I want to go home to the basics, and the students, they understand a waveguide that you can shine light on the end and you can propagate light down the waveguide. They're familiar with the fiber optics transmission and all that good stuff. But we know that we can never shine light broadside on this structure and couple light to a waveguide mode. So we have to do something else, and that's basically the periodicity comes in. But fundamentally, residing in this waveguide film, there are the set of modes supported by the film. The fundamental mode, the first one, second mode, and so on. So we are coming in here in this periodic regime with an effective waveguide here, and we're continuing. There's a continuum of frequencies coming in here, coupling to discrete states. These discrete states are the modes. And so this is, when this happens, called the Fano resonance. Fano is a very general situation of coupling a discrete state, or coupling a continuum to a discrete state. This is just one example of that. So that's what's going on there. And now in my lab, we have a number of design and fabrication methods. We do everything in the lab. We do design, fabrication, and characterization. So that's very satisfying to the students, and usually the students who have the most hands-on experience with tools are the ones who are most sought after by industry. So I emphasize teaching the students how to use complex design methods, but also full fabrication tools. We use the rigorous coupled wave analysis, which is a full numerical solution of the Maxwell's equations. We use rigorous modal methods, finite difference time domain, and particle swarm optimization quite a bit to calculate, to do inverse design, namely specifying the spectrum, what parameters provide that spectrum. That's very powerful. We do E-beam evaporation, sputtering, and so on for film deposition. We pattern with nano-imprint lithography, electron beam lithography, and UV laser holographic interferometry. This one is our workhorse method here. And then we have electron and atomic force microscopes to characterize our periodic structures and films. And of course, ellipsometry is very important to know what you actually deposited when you put down a film. Then the spectral analysis is basically from 300 nanometers out to 30 microns, because we're doing work in the long wave infrared as well as in the visible and the near infrared. So here is the nanolithography lab. This is for mostly my students, but colleagues also can use it. This is an automatic nanolithography system. It's a UV laser sitting on a floating table here, covered to prevent any air current from disturbing it. So we can take long exposures with nanometric stability. So here's a processing area, standard stuff, plasma lab, reactive ion etcher, an SEM, and an AFM, the ellipsometer, and then some part of the spectroscopy. So this is our laboratory setup here. And with this UV laser interferometer, we can record large, there's a 6-inch wafer with more than 100 1 centimeter squared samples that we wrote sort of just for fun in that big wafer. We've also we do nanoplasmonics on some occasions, and here is an example of a large array of gold nanocups that was fabricated with this UV laser interferometry setup. We can shoot one-dimensional structures by just taking a direct exposure, but if we rotate the sample between exposures, then we can create these two-dimensional structures very easily. So showing an example of a narrowband guided mode resonance lattice. This is an old paper from 1998, but it was remarkable in the sense that it provided the highest reflection efficiency at the time. This was a world record for a while. And here shows the experimental data. This is in the 800 nanometer region, appropriate for a titanium sapphire laser. And so this is the experiment here. The solid line and the dashed line is a theoretical calculation using a 1 millimeter diameter Gaussian beam input on this thing. So, so that's the resonance response at normal incidence in this device here, which is simply a hafnium dioxide film on glass with a photoresist coupling grating. And as we angle, we split this resonance. As you can see here, this is theta 1, theta 2, theta 4.5. So that's what happens. And computing the situation here in the blue patch here, this is wavelength versus angle. So at normal incidence, you can see only one line here. That's where the two modes are propagating against one another and interfering and forming a standing wave in the lattice. And so that's the guided mode resonance edge. I call it guided mode resonance edge. So that's a leaky edge. But there's another edge there. That's the big edge, or bound states in the continuum edge, that is not excited at normal incidence. It's basically symmetry protected, and it cannot radiate. So this we call them leaky edge and non-leaky edge, but the terminology of bound states in the continuum has come into the fore in the last 10 years. You can clearly see what's happening here. These two loci correspond to the experimental results there. So switching to a wideband resonance lattice, here shows a 3x3, 5x3x3 array of 5x5 millimeter squared silicon structures shown here on the SCM and close up down here. So this is silicon on quartz, crystalline silicon on quartz, a very beautiful structure there. We reference the reflection spectra shown here to gold. So we put gold down here. Gold is basically a perfect reflector. So this normalize the spectra. I'm just moving the beam to the gold patch there. And so computing the objective was to design a very wideband reflector. In theory, you see that worked very, very well. And then we did the experiment. The experiment and theory agree extremely well. TM is the design polarization state. TM means that the electric field is running this way, and TE means it's running along the grooves. And so, and we can check the orthogonal polarization, which is a random spectrum, but the experiment and theory agree very well. For the design structure shown here, we had about nearly 500 nanometer high reflectance band there. We had a 90 nanometer band in here with 99.9, and a 40 nanometer band with 4 nines, 99.99s relative to gold. So this is a very nice broadband reflector, single layer reflector covering nearly 500 nanometers in the near the telecom band region. You can see the wavelength spectrum out here, or wavelength scale, I should say. So the workhorse effect is this lateral block mode resonance, and people have talked a lot about Fabry-Perot resonances in structures like this, Fabry-Perot or Mie scattering or Mie resonances in these isolated particles here. And they've been saying that, some people are saying that's the reason why we have this perfectly reflecting effect. But I contend that that's really not true. What's really going on is this excitation of this lateral block mode here, no matter whether these grids are isolated or connected. So to annihilate any local resonance, we can add a sublayer there to a situation like that. Now this interface is gone, and nevertheless, we have this result here. So if we take this structure on the left-hand side with these parameters and vary this homogeneous layer thickness, TH, and plot the spectrum, we get this result here. Red indicates perfect reflection. As you see, this is a wavelength scale versus TH. So when TH is 0, that's the situation up there, you see a wide band. But as DH increases, meaning that there's no local resonance doing anything here, well, this high reflectance persists, and so that shows that we don't need these isolated particles or Mie scattering or anything like that to implement high reflectance. So this is a demonstration of the physics that's going on. Here's a fabricated device showing wideband and so on. So basically, that we published this a few years back here, in that paper. So we can experimentally observe the lateral block modes as well. This is an experiment where we have an aluminum grid on an aluminum oxide waveguide film. We were interested in pixels, display pixels there. And so you can see just changing the period, we implement these 3 pixels, the blue, the green, and the red. Now looking at the transmission here, you can see the transmission going straight through and measuring that, that's T0. You see for the blue pixel, we have the blue, but we have the red also transmitted. So the blue plus red, that's purple. So that's what measured here. But if you look at the leaky mode going out of the edge, that's purely blue. That's a purely blue mode. So that shows that the leaky mode doing the work is coming out of the edge, is being very color pure. Same for the green. The green is better in the transmission, sort of a compromise. And then in the red, we have it orange again, because we're passing the whole spectrum there. But again, the red line is very clean. So that's the lateral mode coming through, being very clean in color. So we can show this on a, let's see, I have to take, and I can play a pulse, a femtosecond pulse coming into an isolated silicon lattice. You can clearly see the lateral propagation that is going on. So this is a numerical movie showing the lateral activity that's going on, which is really doing everything in this business. So taking a look at the band structure, because this lattice can host a number of modes, is limited by the waveguide, fundamental waveguide properties of the affected structure. We have a band structure. This is frequency versus beta. Beta is the wave number of the leaky mode. And so the TE, the fundamental mode and the first mode and higher mode, they all have these bands there because they live on the lattice. And at one edge, there is at the leaky edge, we have the high resonance reflection, and the other edge, the non-leaky edge, is closed at normal incidence. So that's what I just described for the experiment. And so we have been studying what we call band flips, published here in Physical Review last year, Physical Review P. We're talking about band flips in the leaky mode photonic lattice, taking just a simple structure like that and talking about having a complex frequency to measure things in. We can vary the rho or the delta epsilon, where delta epsilon is the difference between epsilon high and epsilon low. These are dielectric constants here. I'm switching between the refractive index and dielectric constants. And then rho is what we call a fill factor, shown here. So as we vary these parameters, we can have a start out with a leaky mode downstairs here, showing the resonance there, reflectance, and no resonance at the big edge. And as we vary these parameters, this band closes, and then the leaky mode comes upstairs, and the big edge goes down. So we have a band flip. We flip the two states, and that's an interesting effect. And here shows a computed example of what's going on there. Here's the lattice again hosting TE0 and TE1, and here's the schematic band diagram. Here's the frequency versus K. And so this is the first initial state that you vary the parameters, and the band, those two bands close, and now the BIC has moved downstairs and the GMR has moved up. And so this is actually a numerical example with parameters that are given in this paper here, showing that here at the upper band, there is asymmetric. The fields are asymmetric in the high, in the yellow high film there, or segment. So they cannot, this state cannot be excited because of that. But the leaky edge is symmetric, and it will resonate there. And then as we change this delta epsilon, the band closes and then it reopens with now the leaky edge upstairs and the closed edge downstairs. And what's interesting, this is a TE0 mode, and this is the same thing for a TE1 mode. See the mode structure in these computed diagrams. But an interesting thing is, as you would expect, the band closure for these different modes, it does not happen at the same parametric values, which probably obvious. Taking an example device, we've been studying resonant polarizers. We got a very good result last year, shown in this paper there, in optics letters. This is again a silicon on quartz lattice. This is transmittance of TE and TM state. You see the transmittance is high for TM and low for TE. And so that is the basis for the polarization discrimination. Here's an estimate of the device, and here's a bunch of devices that the student and postdoc actually fabricated. And we actually put a few of those together to realize this high extinction ratio of 100,000 across about a 50 nanometer bandwidth there. This is the structure, basically two modules with two resonant gratings each. And the total module here is 2 millimeters thick, same as a US dime there. So this is a very nice result, demonstration of a polarizer using these resonance phenomena. Another interesting effect or utilization refers to the sensors. As far as I know, the sensors are the only commercialized version of this resonance technology. We invented this and patented this more than 20 years ago. Me and one of my graduate students, Dr. Waro, started a company called Resonance Sensors Incorporated. So for a sensor, you can have all kinds of different sensors, but it really doesn't matter unless that sensor is mass producible and cost effective. That's the only thing that's ever going to hit the marketplace. And these are mass producible and cost effective. The plates are imprinted with nano imprint technology, basically injection molding, and coated with in large scale deposition chambers. And that's basically the production of the paper. Very simple. There are lots of markets here. Obviously, COVID-19 is a market. The physical principle is shown here on the right, where there is a lattice, resonant lattice, or a grating, or whatever you want to call it. And so there is a baseline reflectance at a given wavelength. And as an analyte binds to the surface, properties of the waveguide change. So the supported mode then switches to a different wavelength. So the captured biomolecules change the color of the reflected light or the frequency of the light or the wavelength of the reflected light. And of course, the one beauty about this sensor technology is that both polarization states, TE and TM, are supported and excitable by an incident white light beam, cheap, unpolarized source that will, and the sensor itself will basically select the polarization state it wants to operate in. When you're trying to commercialize something, there has to be a pain point. And the pain point in this case is that tag-based systems are expensive and slow. One has to have fluorescent chemical or other types of labels to show that something happened. So a typical double antibody sandwich immunoassay has the target analyte to bind to the antibody loaded with a fluorescent detector antibody. So, and then when this binding takes place, this guy says, hello, something happened. So there's a flash of light. And so that's a single point data acquisition to report something happened. In contrast, the painkiller would be label-free bioanalysis, where you can actually take data across time, not just a single flash point, but collect data across time and look at how the bioreactions or any reactions that you're interested in builds up over time. There are no secondary antibodies or chemical labels needed. And so this is a very practical way of doing bio sensing, and we have here a reader and a sensor plate that can be used for that. And so there's a commercial system that's very beautiful here. Inside, there's a robotic stage that scans the plate across the white light source beam. And we have both 96 well plates and 384 well plates. And this system scans the 96 well plates in less than 20 seconds. So it's really useful. And we've used this, I have used these systems in some of my contracts with the Air Force and other agencies. Here's a detection of neuropeptide Y with high sensitivity, which is of high interest to the Air Force. We have to do the devil is in the details. We have to do the silane chemistry on the surface, and then we have an avidin-D and attached to that, and then the anti-NPY binds to that, then the NPY binds to the anti-NPY, and then we close the sandwich. It's called the sandwich assay, where we close the sandwich by putting another anti-NPY on top. The NPY is very small and anti-NPY is big, so it's easier to read the sandwich situation than just here. So this is data taken over time. You see that from the time this starts till it ends, about 2 hours. And so you can get the readout that's shown there. And finally, I'm going to mention COVID because we're all stuck at home and in our offices here and there because of the COVID. As you know, the COVID virus has S proteins on the surface. Those are the spikes. And on the cell surface, there are the ACE2 proteins or enzymes, ACE2. And you can see the virus links to that. And when that happens, the virus can go inside the cell, replicate, and then be released to cause more trouble elsewhere. And so here's an experiment. The 96-well plate is loaded. There are 4 samples per patient. On the bottom of the plate, there is the immobilized COVID-19 antigen, and the antibodies come in. And as the antibodies come in from saliva or serum, then you see a response. And this is a confirmed positive patient. We're reading about 300 picometer shift in these cells. And so this basically confirms that that this patient has these antibodies, whereas a confirmed negative one shows minimal shift, less than 50 picometer shift there. So basically, there are 24 tests in a single run, 30 minutes per run from here to here. So that's about 2 minutes per test. So this works really, really well. Finally, a few other applications that we've published. For example, the unpolarized wideband reflector using a serial orthogonal grading trick. The early polarizers we make here, resonant band pass filters, and then a spatial spectral filter shown here. This is angle, this is wavelength, so there's a delta function in wavelength and angle, so that's spatial frequency at the spatial filter without focusing. In summary, I've discussed properties of resonant photonic lattices that are governed by lateral leaky mode driven by evanescent diffraction orders. I showed you many examples of how this lateral effect is actually what's driving everything in this business. The isolated particle grids, they do sustain resonant block modes, but nevertheless, Fabry-Perot local resonances such as Fabry-Perot or me are not really causative effect. We talked a little bit about the band structure and band dynamics, and these resonance lattices are foundational for many meta devices, meta surfaces, meta materials, meta devices that people are talking about nowadays, and there are some promising applications. So here's my research group, current group, and some of the sponsors, and that's it. And thank you.
Okay, that's a great presentation.
Thank you, Professor Mang.
It's the time for us to take some questions. So any questions about Professor Magnussen's presentation?
So I have a question. How much is the smallest feature size that you have achieved through the UV lithography? Interference lithography.
What's the smallest feature? What's the smallest feature size?
Yes.
Okay. Yes. That's a very good question, because we're always concerned about the feature size. In this example here, you can see the bar is a micron, 1 micrometer. So this is a couple of 100 nanometers there. This feature, but we're just publishing a paper on the same device, but in the visible region. And in that visible region, that feature size was 80 nanometers. So that's the UV laser has a wavelength of 266 nanometers. So, but you know, if you do orthogonal propagation, and the periodicity of that is theoretically 133 nanometers, or half of 266. Of course, you cannot get that in practice because you have to have an angle between them. So in practice, we can record about 300 nanometer periods. That's about the smallest period we record in practice. But when you etch, if you expose your photoresist and then you etch, and if you control the etch processes, you can control the features that you see. So that's a hands-on experience that those postdocs and the students have to develop to be able to make beautiful devices like these. And that's really valuable for them when they need to go to the real world, get a job. You know, you have to be able to control the tools and know how to operate them and play them like a fiddle or a guitar or whatever.
Professor,
Professor Joseph, how are you? Nice to see you.
Good, how are you? Thank you very much for coming live, even though you had to wake up very early.
I wasn't sure I could make it, but I'm happy now. It's better this way.
Okay, thank you so much. And
yes.
I have one question, and as you know, and when you compare, generally GMR structures are compared with SPR structures.
Yes.
Sometimes. Okay, so one disadvantage in the literature is that the sensitivity of GMR in general is less than that of SPR, but the full width half maximum of GMR is much better than SPR.
Exactly right.
Right. So, how do you compare when you are going towards the same application? For example, biosensor. What is your take on between the two?
Okay, you know these let me see. These plates here are mass produced in injection molding chambers very conveniently and very rapidly. So it's a huge machine that occupies a fraction of a room that just bangs them out. These are 3 inches by 5 inches plates. They're large plates. This is not small. And so we imprint to 100 nanometer depth or about that, and then we put 100 nanometer titanium dioxide on top, and the period is on the order of 500 or 600 nanometers. So we have clean resonances in the near infrared region. So this is a very cheap way. So I think this is probably cheaper than some of the surface plasmon resonance systems. I have nothing against the surface plasmon resonance. I have enjoyed working with that and studying that for a long time. And I know they're very, very sensitive. And but another advantage of the dynamo resonance methodology is that both polarization states are allowed to survive. There is no polarization selection like in the plasmon. The plasmon only allows the TM or P polarization to survive. And also the field profile of the plasmon is simple. It's just a simple surface wave that hugs the surface. Whereas in the modal sensors, you can have all kinds of different modes. You can have the fundamental first, second modes. And these modes, they have actually different sensitivity because the weakly bound modes have a larger evanescent tails hanging out and so on. You can play the mode structure, you can design the structures, you can have this polarization, that polarization, you can take multiple data, you can take data with multiple resonance peaks. And that's why I call this sensor a complete biosensor, because in every bioreaction there are 3 fundamental unknowns, no matter what you're measuring. It's the thickness of the biolayer, the effective thickness of the biolayer, the density of the refractive index of the biolayer, and then anything that changes in the background solution. So the background solution could be changing. So if you have multiple probes like that, with different evanescent tails monitoring each one of those, that's a very nice solution. So like everything in life, it has, pluses and minuses. Typically these resonance sensors, like you said, they are, maybe they're a couple of hundred nanometers per refractive index unit, REU, whereas a surface plasmon resonance sensor might have 1,000 nanometers per REU. But you can play with that. Recently, we've been playing with a Gaussian beam that focuses into some of those sensors, and that Gaussian beam creates an inverted resonance peak because it resonates in angle. It's a little difficult, but that peak has 3 times the sensitivity than the other peak that does not so behave. So you can play with it, and people are designing all kinds of different sensors that have different resonance sensors, guiding resonance sensors that have different sensitivities. I think it's an open field.
Okay, good. Thank you.
Thank you, Professor Magnuson, for a wonderful talk. And we actually have Professor Jean-François Masson back, so he had some difficulty earlier logging in, but he's here, so we can have his talk right after. So Professor Zhu, we can, so he's logged in from Canada.
Thank you very much. It was very nice.
Thank you very much.
Thank you so much.
Thank you very much.
Thank you so much.
Okay,
bye. Wonderful talk. Thanks.
Bye.
Okay, so looks like we still have some time, to for Professor Jean Masson to do presentation. So I'd like to introduce Professor Jean-Francois Masson, who is a professor of chemistry at the University of Montreal at Canada. Jean-Francois Masson got his bachelor degree.
You will have to mute your mic. Somehow I noticed that it is Anuj's mic is creating. Yeah, good. Thank you.
Okay, I will continue. Sorry. Okay, so Professor Jean-Francois Masson got his bachelor degree in chemistry from the University of Sherbrooke, and then his PhD degree from Arizona State University, also in chemistry. He also received a postdoc training from Georgia Tech. Professor Masson has received numerous honors in his career. In the past 5 years, he became the top 100 in analytical science, the analytical scientist from UK, the McBride Medal of the Canadian Society for Chemistry, top 40 under 40 in analytical science, fellow of the Royal Society of Chemistry, and the Travel Award of the Canadian National Committee of the International Union of Pure and Applied Chemistry. Professor Masson has published more than 125 research articles, filed more than 10 patents, and presented more than 100 invited lectures. He is also the associate editor for ACS Sensors. Okay, so I will pass the time over to Professor Masson for his presentation. Thank you.
Yeah, thank you very much. So thank you very much, and I'm really sorry. I forgot that there was no time change in India, so I had the talk pen at the wrong time for Canada. So it's really my mistake, and I really apologize for that. Thank you very much for staying online for the presentation. And so what I will present to you today is a bit of an overview of our research in Montreal. So we are a group in chemistry, but we're doing a lot of instrumentation, a lot of nanomaterials, surface chemistry, spectroscopy, of course, surface plasmon resonance-based and surface and Raman-based, and also lots of applications. So we have developed a surface plasmon resonance instrument, which is portable. So this is about a 9-inch laptop, and the system is right next to it. So we have the SPR chip inside. We have 4 channels. And we inject samples with essentially about a couple hundred microliters. The way surface plasmon resonance works, it actually is it's one of the guided modes type of sensors, such that you have a wave, surface plasmon wave on the surface of the gold film. You have a light response, and you measure changes in either wavelength or angle at which the surface plasmon actually occurs. In function of what binds on the surface. So essentially, the surface plasmon resonance sensor works with a capture molecule. You essentially sieve out the analyte in the sample. You see a wavelength change in our SPR system, and thus which is related to concentrations.
the way we use the SPR is we focus a lot on therapeutic drug and response monitoring. The reason why is that there's not so many sensors that focuses on therapeutic drugs or response monitoring. So I'm going to show you therapeutic drugs today, but we do both. The reason why it's a good opportunity, in my opinion, is that the drug concentration is in the nanograms per ml to micrograms per ml. So it's actually a relatively high concentration. If you compare that to biomarkers for disease, they will be in the picogram per ml and sometimes even femtogram per ml, which are much, much more challenging, of course, to detect. The second reason is that there's often a rapid response needed if you're monitoring therapeutic drugs. If a patient has too high of a drug in their body, then you want to adjust the dosage immediately. You don't want to wait a couple of days to get the lab answers back. So for these reasons, we have been focusing on this in the past few years. So one example is that we analyze methotrexate using SPR. So we have methotrexate, which is a small molecule. So methotrexate is hard to detect with SPR, especially with a portable SPR, which is even harder to detect because the sensitivity is not exactly as good as a benchtop SPR. But we can detect methotrexate by binding an enzyme on a surface, which methotrexate binds to. Combined also with a competition assay using a nanoparticle that is coated with folic acid, which also binds on the enzyme. So by doing so, we can actually have a sensor for methotrexate that is a competition assay. So we have a decrease in the SPR response as concentration increases. We have a dynamic range here in the clinical range. So we can also compare the response of the SPR system with the commercial assay. And we see that both systems actually give the same response. And we have here the diagonal line, which will be the perfect match response, which is essentially the cross-correlation of the two systems. We also field deployed this SPR system. So we have here some pictures of the system in the field on a military base. So we developed a sensor to detect explosive a number of years ago. So we've deployed it to one of the military bases in Canada. So this is a well that we pumped out of the well the water into a spill beaker into the SPR system. The spill beaker is only because the flow rate you need to pump 5 meters down is too high for the SPR system. So you just need some kind of a flow reduction device here. And thus you can pump afterwards in the SPR system and detect the RDX concentration, in this case, in the well. To detect RDX, we've created a nanomaterial-based polymer. So we have gold nanoparticles inside a polymer, which we co-polymerize with a template molecule that looks a lot like RDX. So we created a molecularly imprinted polymer. We essentially washed off afterwards the template from the polymer, and we were able to extract selectively RDX from natural water into the polymer to detect the concentration of RDX. So we field deployed a number of times. So here we have essentially a lab on a sled. So we went in what was supposed to be springtime in Canada, but actually winter can last a little bit longer up north in Canada. So in mid-April, we had a snowstorm. So we had to sled the whole system and gear close to the wells, put it in a tent, and be able to measure on site the concentrations of RDX, which we've correlated with the standard techniques. So in black, we have the HPLC, so that's the EPA method of choice. We have here in gray the SPR on-site, and we have in darker gray the SPR in the labs. And we see that we have a good correlation within about a part per billion correlation between the SPR and the standard methods. So this is our work on SPR. So if you want to know a little bit more about the SPR work, please feel free to ask questions at the end. I'm going to spend most of the time actually on our newer work on surface-enhanced Raman spectroscopy. So our motivation is to detect molecules that are being secreted by cells. The reason why it's important is that cellular communication is one of ways where you can either have essentially brain functions, so neurotransmitters drive brain function, but also it can be used to detect, for example, anomalous cells like cancer cells. So since cancer cells have a different metabolism and higher metabolic rate, you should see differences in the chemicals close to cancer cells. So if you want to detect molecules in cells, well, you can use fluorescence spectroscopy. So fluorescence does give exquisite image of where molecules are in cells. But as soon as a molecule is released by the cells, we sort of lose track of it. Of course, we can use electrochemistry to detect these molecules outside of cells. And while electrochemistry is highly powerful, it does capture only a subset, the molecules that are electrochemically active close to cells, and they don't capture some other molecules that could be important. So the way we based our method is that we combine the knowledge based on patch clamp type of techniques, which is essentially a pulled capillary that is close to a micron at the tip and that you can put near to cells. They measure activity of cells. But now we want to make a molecular version of that. To make a molecular version of that, the way we work is that we use surface enhanced Raman scattering. So SIRS, in brief, is a molecular technique. So you get the molecular fingerprint of molecules binding onto a plasmonic particle. So if the molecule binds in that high field region close to the plasmonic particles, you get a massive enhancement, of course, and thus get a molecular signature of the molecules binding on the surface. In some occasions, it can work in single molecule regime such that the molecular spectra is essentially a fingerprint of what is on the surface. So to create sensors on a glass capillary, the way we work is that we use a block copolymer chemistry. So the block copolymer is a long string of polymer that has two different chains. We have polystyrene in blue, polyfluorovinyl pyridine in red. And so we can bind this onto a silicon or silicon dioxide, which is glass surface, and thus be able to bind a single layer that is a brush layer on the surface. The polyfluorovinyl pyridine is more hydrophilic, binds to the glass surface. Polystyrene is more hydrophobic, it stays in solution. And thus it creates essentially a template to bind nanoparticles, because nanoparticles like to bind to polyfluorovinyl pyridine that is on the surface. So we have gold particles that can template essentially on the surface of the glass capillary. You see here it binds very well all the way down to the tip. These are well dispersed but dense areas of particles. If you compare that to aggregated particles on the surface just by using silent chemistry, you'll see that they tend to clump with silent chemistry while they're very well dispersed with the polymer method. Sorry. So we get much more signal from that. So the well dispersed method actually gives us much more signal. And the reason why we think it's giving us more signal is that we think there's a lens effect and maybe also a ring resonator effect. So when the light actually is shown onto the sensor, it's shown on the side of the sensor, so that the light can actually be focused at the exit of the cylindrical sensor. And so we've verified that with simulations. So we did see with the field simulations that the output here is on the exit side of the light beam. So the light beam goes from left to right. And thus, we get much more signal on one side of the sensor, and thus we get further enhancement by this lensing effect onto the surface of these nanoparticles that are on that side of the sensor. We did verify that experimentally, so we did cross-section analysis, and if we do a sideways cross-section, we see on the first interface that we hit on the sensor, we get a lesser signal than on the output interface of the sensor. So this is the Raman peak intensity for a Raman dye on the surface of the sensor, and we see that there's more signal on the second interface than we have on the first interface. If we scan in the other direction, then we don't see any effect. So when we scan on essentially the cross-section depth here, we see no influence. So we only see it when we scan from one side to the other. So that means also that we get a lot of signal focusing. So in addition of the antenna effect from the particle, we also get the lensing effect. If we illuminate the tip at only 5 milliwatt at 633 nanometer, we can actually even melt the glass fiber. So this is only by illuminating the tip for a very short amount of time. We go from a nicely pulled tip to a molten tip because of the high field and the plasmon, the photothermal effect. Now, if we do the same experiment just on a glass capillary, we don't see any difference, such that it's really a plasmon effect, a photothermal effect. So now we want to apply this, of course. What we do is that we've investigated cancer cells and healthy cells. The reason why we compared these two cells is that the metabolic rate is different from the two cells. So if we can monitor the molecular components really close to the cells, we should be able to have a better idea of what is the metabolism of cancer cells compared to healthy cells. Briefly, the chemistry of that is that you have glucose that acts as a fuel of the cell, so that's the energy source. You have lactate that is the waste product of that process. So if you measure glucose and lactate to cells, you'll be able to see what's the energy consumption of the cells. Same thing with glutamine, which is the nitrogen source of the cell, and we have ATP and ADP, which is the also energy source of the cell. So what we've done is we've constructed a slightly modified Raman microscope. So our Raman microscope had an AFM attachment to it. So we use a piezo stage to hold our pulled fiber close to the focal point of the microscope objective. We have the 633 Raman laser that is focused on the tip. And we've used the white light channel to actually excite fluorescence at 488 nanometer to get the broad field of view, which is measured with a fluorescence camera here. So we have a mirror that will deflect the fluorescence image to the imaging camera. And once we're set, we flip the mirror off, and then we have the Raman signal that goes through the Raman spectrometer. So what we can do is that we can use the piezo stage to move the SIRS sensor closer to cells or farther away from cells. Now, in a stepwise approach, so we can actually get a gradient of molecules close to cells. So we can essentially monitor in 3 dimensions the response close to cells. We can guide this with fluorescence. So the fluorescence imaging here is performed using the 488 nanometer. So we have here neurons from a brain slice. So we have the neuron body here, we have axons prodding out, and we want to really place a sensor close to these axons. This is where there's the most neurotransmitters being released, and such that we can use the fluorescence to guide our sensor to the proper place. So by using the fluorescence imaging, we know exactly where we are in the sensor, and by using the focal plane of the microscope, we can also know the distance. So we place the sensor in focus, we move it far away from the surface, we place the neurons in focus, and then once we move back the sensor, we can know exactly the distance within actually a few microns accuracy, the distance between the sensor and the cells. So it provides us a highly precise way to guide the sensor location close to cells. Then we turn on the laser and we see a dynamic response from molecules binding on the surface. So since it's essentially a single molecule regime, we see some null signal and some active signal. And once molecule bind on the surface, you see a rise in the Raman signal that is associated with the molecule. So you see a stronger signal at the moment. And thus, you can actually get a single molecule spectra of what binds on the sensor. So therefore, you can actually sort out molecules doing so. So you can actually detect whether it's glucose or lactate that is of interest in our case by assigning the spectra to reference libraries. So we did collect reference libraries of spectra, for example, for small molecules, for pyruvate, lactate, urea, and ATP, which are the molecules that are of interest to us to monitor cancer cells. And you can see that each of them have different barcode, essentially, where you have essentially a different vibrational spectra for each of the molecules, such that we can use higher data processing methods. Because one of the things with single molecule spectra is that each spectra is different. So depending on the orientation of the molecule, you'll see a different vibrational signatures because the modes will be more or less enhanced depending on the orientation of the molecule. So essentially, it's like taking a picture of someone, but from different angle. It's the same person, but the picture don't look exactly the same. So that for that reason, we have been implementing machine learning or artificial intelligence data processing. So the way we work is that we've implemented TensorFlow, which is a Google open source algorithm for spectral sorting of Raman spectra. So we build large libraries of surface spectra of pure compounds. Since we can easily get pure spectra by just having a pure solution of a compound, we can let the system run for a couple of hours and acquire tens of thousands of spectra from a single molecule spectra from let's say ATP in this case. We can do this for a number of molecules, and then we can train the machine learning with this training sets and test with experimental data. So we just essentially take the spectra and use them as pictures of the molecules from different angles for single molecule data. Then we train the neural network, and then we get an output, whether it's ATP or ADP. Then when we apply to actual data, we do the reverse process. So we have a spectra with no label. We assign the proper label from the machine learning, and then we identify, for example, this spectra as being ATP. So we can do this with a number of spectra and also a number of molecules. So in this case, we have different metabolites from cells. So pyruvate, lactate, ATP, ADP, glucose, glutamine, and urea are all molecules of interest for us. And we also have the CO2 independent medium. So we need to get the background as well into the calibration, as the media can also give some Raman signal. So in this diagonal here is a percentage of proper assignment, which is in the 90% range. So that means we get 90% of the spectra correctly assigned in this case. So we can then monitor molecular gradients close to cells. So in this case, these are the molecular gradients from carbon-based energy sources. So we have glucose in the black or dark here data points, and we also have lactate, which is the waste product from the glucose consumption in cells. So when we are far from cells, which is the shaded area, this is the bulk response for glucose and lactate. So there's barely no lactate in the bulk because the cells are producing the lactate, and it has to diffuse far away from the cells to reach a sensor. But then we can move the sensor stepwise closer to cells. So at 100 microns, we get essentially the bulk response. So we get at 50 microns, but from 20 microns and closer, we start to see a divergence. We start to see less glucose close to the cells and more lactate, which makes sense. Glucose is the fuel from the cell, so it will be consumed, and then the waste product will be the lactate. Therefore, we can use the Raman sensor to get chemical gradients close to cells. And we can compare the gradient between HeLa cells and UVEC cells, and we see that there's a little bit more lactate close to cancer cells than there are from healthy cells, meaning that the consumption of glucose is actually higher from the cancer cell, which makes sense. The cancer cell replicates faster, it needs more energy, it will consume more glucose. Can do the same for ATP and ADP. In this case, ATP and ADP are produced by cells. So we do see a higher concentration of ATP close to both UVEC and HeLa cells. The gradient or concentration is higher close to the UVEC cells because it has an enzyme that synthesizes ATP on the cell surface. And then we can also measure the nitrogen-based gradients of urea and glutamine. So glutamine is the fuel and nitrogen source. Urea is a waste product. We once again see that glutamine drops close to cancer cell. We did see a slight rise in urea close to cells. One of the important aspect is that all 6 of these molecules were measured in the single experiment, such that we could get the full picture of the concentration profile close to the cells in a single experiment. Therefore, we can measure complex gradients close to cells. We also measured a reference cell line which does not secrete molecule, and we did see no response. So we just as a good control. In last, it was mentioned that I'm a editor for ACS Sensor. I just want to take about a minute or two to just provide you a brief overview of ACS Sensor. In case you're not too well aware of the journal scope. So it's a journal that is based at the American Chemical Society, where anything related to molecular sensors are published. So it can be biosensors, chemical sensors, gas sensors, cell-based sensors, or single molecule sensors. We strive to publish papers that are new theoretical concepts that are demonstrated experimentally. So we do place a good emphasis on experimental data as well. Finally, in conclusion of my presentation, essentially showing you that with the proper nanomaterials of chemistry instrumentation, we can monitor clinical samples. The instrument can be field deployed, which we've shown on Army bases in summertime and wintertime, actually, I should mention. And also dynamic serves measurements on the plasmonic nanofiber nanopipette can serve to monitor cells-based processes. Lastly, I need to acknowledge the people that are actually carrying the work. Actually, I need to mention two Indian students that came to Montreal last summer. Shefali and Arshita came to Montreal last summer, and I did host a number of interns from the IITs in the past, which I always welcome opportunities to welcome students to Montreal. We have a diverse group of people, so we have people from Asia, North America, Caribbeans, India, and also, of course, Canada. So lastly, I need to thank also the funding agency, and thank you very much for staying put. And I'm once again really sorry of the time difference mix-up. So thank you very much.
Thank you, Professor Masson, for this wonderful talk. And no problem. Yeah, the time difference, 1 hour change happened, but wonderful, talk by you, and great seeing you, here in this conference. We were hoping that you would be coming here to India, and which was planned, but because of the COVID, we have this conference, which is, virtual, but we're so glad to have this wonderful talk by you. But now we'll take some questions by Professor Zhu. You can invite questions.
Okay. So again, thank you for the speaker. But give the very, very nice talk. So it's the time for questions. So any questions for our speaker?
If not, I have a question, Professor Masson. So this RDX detection. So what is the actual molecule that actually binds RDX? Because do you have a kind of a specific molecule that really?
So we based it on the molecular imprinted polymer. Let me take this slide. So the polymer we have on the surface is the polyaniline that is electropolymerized. So it's based on the, let's say, molecular interaction between the polyaniline with gold nanoparticles, and we template that. So essentially, what is not really shown here is that the cavities here are selected for RDX. So it's not a classical molecular detection, but it's a MIP-based molecular detection.
Oh, great. So it's very specific. The cavity would just accommodate RDX size and shape.
It may accommodate some of the metabolites of RDX. So once RDX is in nature, it can degrade it to some extent. But if you detect the metabolites, we still know that there was RDX there. So it's not too much of an issue for environmental monitoring. But yes, it does bind to the whole selectively compared to TNT. TNT does not bind.
Oh, TNT does not bind. So you did a specificity test, and
yes,
yes. Okay, excellent. And also another question was about when you bring the probe, the fiber optic probe, close to the cells. And so you were saying that it comes within a few microns, or even within a micron. But then the nanoparticles, they would have a penetration depth of a few nanometers. And so how would the field, interaction happen? Or you get really close, you get further close within nanometer range.
Yeah. So we don't measure the cell directly. So what we measure is the cell-based relief of molecules. So essentially, you need to see the cells as being a point source of molecules, and these will diffuse and sometimes will bind on the sensor. And that's a diffusion process-based measurement. We can put the sensor on cells or inside cells. So I didn't show our work inside cells, but you can still puncture the cells and get a sensor inside. In this case, you measure intracellularly. But in all cases, it's a diffusion-based process. So molecules have to diffuse on the surface.
So it diffuses from the cell and goes and binds. But obviously the diffusion will have a diffusion length, only up to a set. So you have to get it close. You have to get the probe.
Exactly. And what we've done is you have to be within microns, to tens of microns from the cell.
Oh, great. But great work. This is to actually make it happen at this level and, using machine learning to decipher exactly what is there. So that's excellent. And so
thank you. Yeah.
Any other questions?
I think that it took us 10 years to publish the first paper on this.
Oh, wow. Yeah. I said that. Yeah, please. It's a question.
Yes, yeah, that was a very interesting talk. And I was impressed by your use of inverse or machine learning to sort the spectra. And I wonder, wasn't it very laborious to build the spectral library? How did you take all these different views of those different molecules and collect them together? Wasn't that a big undertaking, or how did you do that?
So this is the wonderful part about Raman is surface-enhanced Raman is the fact that the molecule diffuse on the sensor and diffuse out of the sensor because it's an equilibrium process. So it's actually to collect the single molecule spectra with different orientation, you just let the system run for hours. Because the molecule will bind and unbind and will come at different angles every time. So essentially, you just let the system run for a period of time in a pure solution, and you'll collect on average the different orientations. So we collect the spectra at 20 millisecond time frame. So that means essentially 50 spectra per second. So in an hour, then you get tens of thousands, essentially almost 100,000 spectra.
Thank you. Very interesting. Very nice.
Thanks.
Okay. Any more questions? Well, if not more questions, let's thank our speaker again. Thank you for the wonderful talk.
Thank you very much. Next time I'll meet you in India.
Yeah, next time we'll see you live. And also, Professor Magnuson, thank you for your talk too. So both the speakers, we would like to thank them for their wonderful talks this session. And hopefully next year or next time when we have ICWE, we'll have it live in person. And so thanks, Professor Masson, and thanks, Professor Magnuson.
Thank you, and bye-bye.
Thanks for co-chairing the session, and thanks to all of you for coming in so early in the morning in the US and Canada. This is extremely early, and we appreciate your coming here for this. So thanks. With this, we would like to end the session. Thanks.
Bye-bye.
Thanks. Bye. Hi, Jean-François. Bye.